খুব
ওইটা কিন্তু আমারও লাগলো, মানে ওটা বেশ অ্যাচিভমেন্ট মতন লাগলো কি ওই লোকটা যা কাজ করলো কি ভীষণ সুন্দর কাজ করেছে।
খুব সারপ্রাইজিং ছিল, কারণ এক্সপেক্ট করছিলাম না, হঠাৎ একটা প্যাকেট এলো, প্যাকেটের ভিতরে প্যাকেট, তার ভিতরে প্যাকেট।
হ্যাঁ, প্যাকিংটাও ভালো করেছে না, দেখো ওই কার্ডও দিয়ে দিয়েছে নিজের ওর ভেতরে কোথায়।
প্যাকিং খুব ভালো হয়েছে।
দেবাইশ তুমি বলে দিচ্ছ।
হ্যাঁ হ্যাঁ, আর তো এখানে তো সব সুভাষিস অনির্বাণ সবই তো বলতো আমার, জাস্ট আমি বলে দিই।
সকালের দিকটায় জয়েন করতে একটু সময় নেয় লোকজন।
হ্যাঁ, তারপরে আস্তে আস্তে বাড়ে, আবার একসময় একটু কমে, বাড়ে, এই করে।
কি একটু 5 মিনিট পরে শুরু করবো কি?
না না না,
লোকজন কম আছে, একটু
সময় শুরু করে দেবো আমরা, ওই করতে করতে চলে আসে সব,
চলে আসে।
হ্যাঁ
ঠিক ঠিক।
আবার দেরি করলে আবার দেরি হয়ে যায় সেশন গুলো পর পর।
হ্যাঁ হ্যাঁ, ঠিক ঠিক ঠিক
আছে তো,
ঠিক।
ওই সুভাষিস,
হ্যাঁ বলো।
কন্ট্রিবিউটর যেগুলো আছে 20 মিনিট, তো 20 মিনিটের মধ্যে ওই 17-18 মিনিট বলবে, আর 2 থেকে 3 মিনিট তাদের ডিসকাশন, ঠিক আছে?
ঠিক ঠিক। তো অনির্বাণ একটু দেখে নিও, 38 মিনিটস, 11:38 এ একটু টুকে দেবো। হ্যাঁ, ওইখানে রুকে যাও, হ্যাঁ ওইখানে অব্দি রুকে যাও।
So we begin the morning session of our 7th day meeting. 7th, yes, 7th or 8th day. Professor Subhashish Banerjee from IIT Jodhpur, he will chair this session. He is very much known on open quantum system. He is really an expert on that field, and he is doing very good research for a long time in quantum information and foundations. So I invite, he is also our good friend always. So I invite Professor Subhashish Banerjee to chair this session. Okay.
Thank you, Professor Shorkar. It gives me immense pleasure to be a part of this wonderful meeting that is going on. And today's speaker, Professor Anirban Pathak, of course, needs very little introduction. He is known to all of us. He's also a collaborator and friend of ours, but for formality purposes, let me introduce him. He's a very distinguished physicist who's been on the scene for a long time, more than around 2 decades now. And he's heavily involved into teaching and research in quantum optics and quantum information. He has nurtured quite a few layers of students belonging to different age groups. And he is a known authority in our country on quantum cryptography. He's also the recipient of the 2017 O.P. Bhasin Award in the field of electronics and information technology. And today he will be speaking to us on randomness, which is something which is very dear to my heart. So without any further ado, I will invite Professor Pathak to start.
Thank you, Subhashish. And so, just a moment. Okay, so this will be a random journey into the world of randomness, as the title suggests. So randomness appears to us from 2 different facets, and time to time I'll be informal about it. So one is quantum random number generator, and the other one is QKD, quantum key distribution, and other cryptographic applications. So there also the key needs to be random. If the key is not random, one can predict, and then the security is compromised. So one is generation of randomness, and one is capability to transfer randomness from one place to other place. So essentially we started with QKD, means for many years, we were doing QKD and related cryptographic protocol design. But when Quest project came, it appears that almost everybody wants to do QKD. So we shifted a bit and we thought that we'll do random number generators. And we started looking deeply into random number generator. And we somehow, Srikant and I are part of this Quest project. And there is another window in which Subhashish, me and Narayan is part of the Quest project. So these are the results are means more or less something is with Srikant, something is with Subhashish. And so we randomly present those results. And there is a disclaimer: don't try to correlate slide number n+1 to slide number n, as it's a random journey. So there should not be any relation between first slide to second and maybe second to third or third to fourth. So it can be random. So that's announced beforehand. So I'll start with something funny, means there now everything people get meme. And so there is some cartoon about Sole movie that Dharmendra and Amitabh is discussing, and that whether things will improve after election, and Dharmendra is suggesting let's have a toss. So they used to have a toss, and there was a coin, both sides of which had King George VI. And so the entropy of that was 0. If you consider the Shannon's entropy summation over minus px log 2px, and one of the probability is 1, then the other probability is 0. And if you put it, then entropy will be 0. So the whole point is randomness is measured with entropy, and not only Shannon's entropy. Shannon's entropy is shown in top as hx is equal to summation minus px log 2px, and Shannon's entropy of the coin used in Sole was 0. And of course, for the person who knew that both sides is head. And then there is something called Rennie's entropy, which is in the right. And Rennie's entropy is more general, and Shannon's entropy can be derived at alpha tends to 1. And for anyway, means without going in, alpha is the order of the entropy, but the whole point is that random number generators are actually source of entropy sources. So, and then we do post-processing and such thing. And whenever there was a winning probability was biased, there must be some kind of entropy reduction, be it Sole's coin or be it Shokuni's Pasha. And this kind of randomness, like Shokuni's Pasha, was in Epic. So use of random number generator and random number related things like lottery was there in all these epics and things. So the applications of random numbers may not be with this framework, this kind of mathematics which I use today was there from the early days of civilization. And now we can write protocols for quantum lottery and things like that. So anyway, so random number generators are essentially entropy sources, and this kind of basic structure exists. So entropy source is a physical system. So that's of course not for, there are two kinds of random number generators primarily. One is called pseudo random number generator and one is called true random number generator. So in pseudo random number generator, there is a deterministic algorithm to convert a small string of input bits to a larger string of bits that satisfies a certain set of random number test. So in case I know the seed and in case I know the algorithm, then PRNG will become predictable. So but the chance of that happening is very less, and the periodicity is very, I mean, after a very long string, it returns back. So for example, in the bottom, I have written about one particular case, which repeats after 2 to the power 19937 minus 1. So this is a very large number. I mean, the period is very large, and they are very fast. So most of the day-to-day applications, random number generators use that of this kind. But in TRNG, a physical process is involved, and physical process not essentially quantum mechanical. So quantum random number generator is a special type of true random number generator. And here is a physical systems, then there is a measurement system, detectors, and that leads to, so this, if it is quantum mechanical system, this measurement will lead to random collapse, and then there is a raw data, and post-processing leads to random numbers. So this is in general valid for any true random number generator, and I repeat that quantum random number generator is a particular case of this. So what makes QRNG special? Because there are so many true random number generators, but all true random number generators are slower than pseudo random number generator. And that's the reason that in day-to-day life, we use more often pseudo-random number generator. So the physical process used in classical true random number generator, so I add a C to make it classical, are difficult to predict due to the incomplete knowledge of the system. So given the complete description, it would be possible to predict the outcome of all classical TRNGs except QRNGs, because this is intrinsically random. But now the question that comes, do we need all the facets of the non-classical or all the non-classical features of quantum mechanics to obtain the benefit or uniqueness of QRNG? So via the use of QRNG, one can get certified source of randomness, which can be checked using the laws of quantum mechanics. There is no classical analog. So you cannot do that in the classical world. But do I need full picture of the quantum mechanics to get it? So if we construct non-classical toy theories, so with restricted number of non-classical features, will I still be able to get some features or uniqueness of QRNG as well as QKD? So then I will not call it a QKD, but rather I will call a key distribution with unconditional security or certain kind of security. So non-classical security. So that's the foundational aspect. So I don't work regularly on foundational issues, but since this meeting is focused on foundation, so I thought that I'll try to bring some foundation flavor in my otherwise cryptography talk. And this is a bit challenging, means because the something like a hard court player is playing in a grass court. So all keys are, so where the randomness is used. So as I mentioned that in quantum cryptography, the keys have to be random. All keys required to be random, but the random numbers are not essentially keys. So do we still need to take them hack proof? Because in cryptography, you need to make it hacking proof. But when you are just generating random number, do I need to make them hacking proof? The answer is yes. I still need the random number to be hacking proof for several applications. So casino owners require perfect randomness. So if somebody can hack the random numbers, then he will be able to bet accordingly and win a lot of money. State lotteries need it to remain fair. And then if you can break the randomness, you can predict that which number is coming to be the winning result of the lottery. So TRNGs take a seed and generate this, but here we'll use, and they are very fast. So in the casinos, there are slot machines. So slot machines use PRNGs or pseudo random number generators. And there is a nice, interesting thing happen. So in the right, we see some slot machine. So you give a coin, you bet, and the result comes. So how it works? So there is a random number generator. There is an online casino software. And then finally, this software decides that how the cards to be changed, what numbers to be rolled, numbers spun, symbols in view. So some random outcome. Now, suddenly in Russia, all kind of gambling on casino was banned. So then all the casinos had these machines and they sold it like waste material. And some people bought it. So they were the hackers. So it was really a company, and they understood the algorithm, they understood the process, deeply studied it, and it was mostly a machine sold by an Australian company. And then their agents were distributed all over the world, and many places they were making small bet, but they were always winning. And this was violation of the probability. By probability, I knew that, in every dollar, 7 cents will be profit of the casino owner, because there is with certain probability the winning card will come. But for a few days, they appeared that there are several machines where it's reporting loss. And then on inquiry, it was discovered that there are some Russians who are winning all the money, and they were operating all over the world, and it was targeting only a particular kind of machines manufactured in Australia. So even the random number generators can be hacked. So there are interesting aspects of random number generators. So it's not all about quantum random number generators. So we already mentioned that there are two types of random number generators: pseudo random number generator and true random number generator. And true random number generator can be classical and quantum. Then again, in the quantum, there are three kinds of things. One is trusted. So when it's trusted, it is generating certified randomness, and you need Bell non-locality kind of things. And when it is not trusted. So when it is trusted, you are trusting the device, so you are not checking anything. So if it is not trusted, then you are applying a self-testing. And there is something in between trusted, interim between trusted and self-testing QRNGs, which is semi-self-testing. So the cheaper versions, like what I bought in my lab, ID Quantix Quantis, this is a trusted device. There is no self-testing happening in that. And self-testing can be required for internal fault, as well as that the supplier may have given me faulty machines. He may have intentions to get my cryptographic key, which will be generated from this. And each of these has different issues. So this is a summary of different kind of implementations. There is optical and non-optical. So even in non-optical, there is radioactivity, which depends on uncertainty, electronic noise, atomic systems. And in optical, there are single photon detector-based things. And we'll show some of this. But semi-self-testing QRNGs are pretty interesting because this is in the middle. And many people have reported random number generators, and some of them are device independent. So we just propose a list. Of course, these references are not here, that from one of our paper. And every year we see some new device, and the analogy is somewhat similar. So just like we have measurement device independent QKD, so here we have measurement independent random number generator. Device independent QKD is analogous to device independent random number generators, and requirements are similar. So the kind of non-classical features required in random number generation, because ultimately QKD and random number generator are pretty close. So unless you can generate randomness, there is no point of distributing it. So QKD is a bit more demanding, or key distribution is more demanding. First, I have to not only I have to generate randomness, I have to distribute it between Alice and Bob. But if I can, so capability of performing key distribution always means capability of generation of randomness, but it's not other way around. So now we move to the foundation part, and that how or what quantum facets are required, which quantum features are required, and our ideas evolved over time. And any of us means at least Subhashish, and I know it very well, means whoever collaborates with Srikant means. So the papers normally never get finished because ideas keep on evolving. But these are the case. This is a particular case where ideas evolved over time, but each of them got somehow able to see the light, and public means it was published. So initially our idea to look at it was somewhat motivated from this kind of problem from Simon's papers on classical entanglement. So not only Simon's paper, we read a couple of other papers, some of them on classical entanglements were even predated Simon. And so we wanted to look at means what leads to entanglement first, and why is there classical entanglement? And we wanted to make a list of our postulates based on our motivated by quantum cryptography. And so we first list that any theory which is linear or governing equation is linear must have superposition. So be it Schrodinger equations or be it Maxwell's equation. So Maxwell's equations being linear, superposition is allowed there as well. So there is nothing special about superposition. It's nothing to do with quantum world. So that's the intrinsic manifestation of a linear theory. Then tensor product space is my second postulate in the classical. And tensor product space exists in the classical world. And that's why the polarization entangled states or non-separable states were reported by Simon's classical entanglement. So linearity and tensor product space is sufficient to find out classical entanglement. Then non-preserving evolution was added. That leads to unitarity, and no signaling is in any case the master of the things. And in addition, we know certain other things which are classical. So for example, in many of our papers, we use a technique called particle order permutations, or POP. So POP is essentially classical because in classically nobody stops me from changing the particle order. But of course, there is a challenge in the quantum world. Nobody knows means how to do particle order permutations without disturbing their optical state of polarization. So that's a technological challenge. Quantum mechanics does not stop me from doing that, but this is something classical. But anyway, so then we keep on adding the flavors of quantum mechanics, a measurement with probabilistic outcome according to Born rule. So as soon as I add this feature, so I have a toy theory which has C1 to C4, and in addition Q1, I can have quantities kind of random number generator. So this is the random number generator where there is a weak coherent WCP and or a single photon, and then you put it on a beam splitter. It splits in partly in reflected, partly in transmitted. So simultaneously it is present in both because of superposition, which is manifestation of linear theory, and linear is classical. It can be classical, and then it collapses on one of the detectors, either in the reflected side or in the transmitted side. So this kind of random number generator can exist in a theory, a toy theory, which is C1 to C4 and Q1 only. I don't need non-commutativity or other things, but the problem is that this will be only a trusted thing. So this, you cannot certify the randomness, you cannot make it device independent because your theory does not have those features. So apart from that, wave particle duality, Glasson's theorem, these are sufficient. All these things follow from this kind of theory, sufficient to protect orthogonal state-based crypto protocols like Goldenberg-Hedman. So how the Goldenberg-Hedman protocol works? So this is not like BB84. So in the right-hand side, I show a Mach-Zehnder interferometer. And if I send here to send 0, I send Kt plus Kb by root 2. So Kt is a wave packet. And to send 1, I send Kt minus Kb by root 2. So A plus B by root 2 and A minus B by root 2 are orthogonal to each other. But the point is that when I send this part, packet A goes from the upper path and packet B goes from the lower path. So packet A and packet B is never present simultaneously in the channel. So the whole that reduces that Eve can perform measurement only in Kt Kb basis. So just like 0-1 basis, whereas Alice and Bob can perform measurement in Kt plus Kb and Kt minus Kb basis. So this is very important. So in quantum mechanics is not really a completely stochastic probabilistic theory. So quantum mechanics has a spatial basis. So if the spatial basis is known or accessible, so like in this case, A plus B by root 2 and A minus B by root 2, then everything is deterministic. So that spatial basis must be unavailable to Eve. So how it is done? So I delay one packet at Alice's end and one packet at Bob's end. So as if Alice and Bob are doing in the superposition basis or wave-like basis, and Eve is compelled to perform a measurement in discrete basis, AB basis, which is giving the information about which path information. So that's like particle. So wave particle duality easily follows from Q1, and spatial basis leads to the unavailability of spatial basis to Eve leads to security. But now we add non-commutativity. So this will give me many things, and including BB84 kind of security and indistinguishability of particle we don't use much. So in this particular case, in Goldenberg-Hedman protocol, what is needed is that strict time checking has to be required, because otherwise Eve can delay the upper path and wait for the lower path to come and then do the measurement in superposition basis. So in order to avoid this strict time checking, we started with the idea that, well, one can start with a set of Bell states and just apply permutation operators, so permutation of the particles, and then Eve does not know which particle is entangled to which one, and we can do orthogonal state based. Because although Eve knows that it is Bell measurement has to be done, but he does not know that she does not know which particle to be entangled with which one. And that kind of techniques which we have used to convert almost everything into orthogonal state-based QKD or cryptographic task would require entanglement. So only collapse on measurement will not be fine. So this more or less I discussed. So in most of our works, we use either BB84 subroutine, which uses conjugate coding, and that requires at least Q1, Q2. And in other works, we use, and then we use entanglement to perform QSDC, DSDC, quantum dialog, etc. So origin of security comes from unavailability of spatial basis. And so our early view on the origin of security was somewhat like this. Quantum theory evinces a complex and cryptographically pertinent interplay of local and global properties, as has become evident from the study of general correlation theories. So in particular, non-signaling, non-local correlations imply intrinsic randomness and privacy of shared randomness. So this is well understood. Non-locality, so this is our more specific comment on randomness. Non-locality is known to be bound by uncertainty. Edge protocol like BB84 require only the incompatibility of conjugate observables. So something like lucidly speaking, security follows from our inability to perform measurement in 0, 1 and plus minus basis because M0 and M plus do not commute. So seemingly independent of the non-signaling and non-local features of quantum mechanics, but when no cloning play a very crucial role in BB84, and their proofs will be connected to no signaling. So uncertainty via disturbance in the local theory suffices to guarantee the security. And we'll show some particular example. So a little more about no cloning in post-quantum theory. So these are a set of early works where we tried to connect cryptography with the foundational issues. So the incompatibility of two observables using the fine-grained uncertainty relations. So the uncertainty relations are much discussed by Archanda and his students. So we just write the relations, and where the maximization is over all output vectors and pure states in the theory T. So that T is not really a quantum mechanics. And the summation is carried over measurements M sampled with uniform probability. So here P subscript xi can be considered as the uncertainty in the state. Now, our observation was that intrinsic randomness in the theory T be identified by this U, which is uncertainty, which is defined above. And if U shorter than 1, there exists irreducible randomness even in pure state. So under non-disturbing uncertainty, a state can be determined by repeated measurement even when U shorter than 1, and thus can be cloned. So we thus assume that measurement can disturb the system. So that's a requirement, and these features are there in quantum mechanics, but any other theory which we want that we should have randomness should also have this kind of property. So there is a simple example. This example was coined by Srikant, that let's consider a Poiller's urn with zero feedback. That is, an urn is filled with blue and red. So blue is written by B and R corresponds to red. Blue and red balls, and one samples means we just pick up randomly a ball and returns the ball. So the outcome is uncertain because it can be blue or red with certain probability, B by B plus R. So B plus R is the total number of ball and B is the number of blue balls. But the state of the urn does not change after measurement because I'm returning the ball. So this tells me that uncertainty does not logically imply disturbance because the state is not disturbed, but it was uncertain. So this initial tricky thing with simple examples help us to construct theorems like if U shorter than 1 and D shorter than 1. So D is a quantifying of the disturbance. Then a general state in T cannot be cloned. Subsequently, we thought of looking at a very simple toy theory where BB84 kind of QKD can exist. So consider a toy theory with only 4 pure states. There is nothing else. So there are 4 states and it's just defined in this way. So this is a non-classical theory. No cloning can be derived from this data without using no signaling. So here U is 7 by 8, which is shorter than 1, and U we have defined in the previous one. So there are possible measurements A and B, and there are 4 possible states, and on different measurement how they behave, that's written here. So these are my 4 states in the 4 corner, and toy theory tree is depicted in the table in left. So it's represented by this inner rectangle with where color rectangle. So then in this toy theory, one can design a protocol which is just analogous to BB84 protocol. So Alice randomly generates a bit X. If X is equal to 0, she randomly transmits the state 1 or 3. And otherwise, if X is equal to 1, she transmits 2 and 4. Bob randomly measures received state. So there is pretty analogous to BB84. After Bob has received all M transmitted states, Alice announces whether the state sent was of the A or B type. So just like this, we do in normal BB84, but then the Hilbert space is pretty big. We had many other states. So this is easy to show that even this kind of, so this is a hypothetical theory, hypothetical model, a toy theory. And in this toy theory also, BB84 security will follow. And so there's a quick calculations, but what we want to note that this T is a local theory and we cannot construct Eckhart 91, or yesterday Gurudev was talking about BBM protocol after Pankaj's talk. So all those things cannot be possible here. So this is a local theory. So evolve idea. So as I mentioned, the idea keep on evolving, and so now I am going to propose a kind of construction, pyramid-like construction, and giving a hierarchical structure to the postulate axioms of quantum mechanics. So quantum correlations are non-classical when non-local, in that they can be violate Bell-type inequalities that classical correlations cannot, and the converse is not true. Similarly, a classical theory is necessarily non-contextual and realist. A violation of a contextuality inequality would also imply non-classicality, but the converse is not true. So this will be in the background. And so here is the main part of the presentation. So this is Q1. So then initially we were trying to do some other Q1, Q2, Q3, and then lately around 2017, Srikant and Arbinda and I wrote a paper where we, this is Europhysics Journal 2019. And before that, we first started the single system. So single system is Q1 and Q2 is, apart from C1, C2, C4, Q1, Q2 is incompatibility and uncertainty, contextuality is sufficient. And this structure is such that means Q1 and Q2 does not imply Q3, and Q3 does not imply Q4, but there is a hierarchical structure because the theories are built on top of one. So if I say that Q3 is allowed, that means Q2 and Q1 also exist. When I say that Q4 is permissible in my theory, then Q3, Q2, Q1 is also possible, but some jumps are not based on the other one, because entanglement could have been produced if you have a two-party systems, means multiple particles, if you go just out of single systems, even without considering contextuality. So it's inspired by quantum information and generalized probability theories. And the hierarchy is ordered in such a way that the preceding axioms are necessary for the succeeding axiom, but which is not valid for Q2 to Q3 jump. And it is aimed to bring out the increasing structure. So there were many axiomatic structures, but no such hierarchy was there. And then we tried to look at what kind of QKD is possible if I have a toy theory with only Q1, what kind of random number generator is possible, etc. So at that time, we were not aware of non-locality without entanglement related discussion. So this, and in this particular meeting, there was so many talks on, Devashish Das, a student, spoke, means many people spoke about non-locality without entanglement. So we tried to fit this in our model, and we note that bilocally implementable operations are joint operations that can be implemented by two geographically separated observers, say Alice and Bob, using LOCC. And repeatedly applying LOCC, if I shared a state, but can I distinguish what state I'm sharing? Means, suppose there are 9 possible states which Alice and Bob are sharing, and they're allowed to do LOCC as many times as they want. Can they distinguish all the systems? So there can be states which is globally orthogonal, but locally non-orthogonal, and Bennett proposed such states. And our observation is that, so at least what non-local features should be present in a theory allowing the existence of these states. So Q1 will be sufficient. So in our hierarchical structures, which one is, so we specifically took this equation 3 from Bennett's paper. So where you can see that the first particle is with Alice and the second particle is Bob. So if both the particles were with Alice, then these states are orthogonal, but under LOCC, these are not distinguishable. So examining Bennett et al. Example, we find that neither entanglement nor the availability of more than 2 observable joint measurements, etc. are needed. Thus, so Q3 and Q2 is not needed. So Q1 and will be sufficient for having this kind of states. And of course, it should be top up with 3-level systems, because here is 0, 1, 2 and tensor product structure, but tensor product structure is already assumed in C2. Now, what is their cryptographic applications? So I'm not still clean about that. We will talk about that later. So RNG, random number generator, and QD can be designed in many local theories. So here we list that if I make a toy theory, which is local, which has only classical assumptions and added with Q1, then we can have ID quantic quantities kind of random number generator. So we have this one in the lab. QRNG based on electronic noise. Radioactivity requires only, so there are several things, and there is a BB84 like a local key distribution. So this one is, we are now making a lab, and this is a quantities random number generator in our lab. And these are some output, and we have done NIST test. So these random numbers are really produced in our lab. And so then I quickly mention another BB84 type local key distribution scheme, which requires only Q1 and nothing else. So in a toy theory, we can have, so I'll not go in detail because time will not permit that. So all of this will work in a toy classical theory with Q1. So these are different random number generator. So the first one is like what we use in quantities. The second one, that the B is, there is a photon, and neutral density filter reduces the intensity of the laser without changing its photon statistics. So it remains still Poissonian, average photon number is much lower. So it works like an approximate single photon source. And then at different point, it reaches the single photon detectors. And looking at the time gap, so you see that delta 3 is different from delta 2. So we decide whether we'll note it as 0 or 1. And here in the C, spatial distribution is looked for. So all these things will work in a theory which allow Q1 only. Then there is semi-quantum key distribution, where Alice prepares states in 0, 1 or plus minus basis. So the superposition is allowed, and Bob either measure or just reflect. So semi-classical theory, Bob randomly, but Bob can do a measurement in 0, 1 basis only. So this kind of protocols are called semi-quantum protocols of key distribution. And so wherever I'm capable of doing BB84 kind of stuff, so this requires reduced capability. Alice is same as BB84, but Bob is just a classical user. So this will also work in the theories which does not have full facets of quantum mechanics. So now we move from toy theory to toy model. So this is a toy experiment in our lab. So we have Alice, which has a source, and then Alice has a source, and there is a polarizer. So it's not randomly polarized. You have to do it by hand. And then there is a Bob, and Bob has an analyzer, which you can orient in 0 degree, 45 degree, 90 degree, etc. And then there are two, after beam splitter, there are 2 detectors, and this detector clicks, one makes 0, one makes 1, or plus minus as it is said. Now Eve has similar setup. So Eve can do measurement recent data, and Eve has a setup like Bob, and whatever she got, means she transform it to. So this is in a real lab. Priya is doing the experiment, and we get this kind of key, which are random. So then in Q1 plus Q2, if 2 are allowed, then we can have various experimental. So contextuality based randomness, random number generator will work, and KCBS inequality based local key distribution scheme will also work, which we have reported. Then we had Q3, so we have entanglement, and when we have entanglement, we can have beautiful things like controlled, deterministic, secure semi-quantum communication, so which can be used for quantum e-commerce, online business, and many things. But when I had Q4 as well, then I have more capability, and then I can add self-testing. But there are something demanding that in self-testing schemes of Bell test bed cell, there is an input random state. So you already need some kind of randomness to, and that's why these are just like key. In case of QKD, we say that QKD is essentially a quantum key amplification, because for authentication, we start with a small key. So here also we start with a small random number, and then we expand it. And this I'll not elaborate because my student Baishak has already presented this. So we recently published some. So this is acceptable article in Physical Review A, and semi-device independent randomness expansion. So this is another one. Okay. Yeah. So finally, we now have a setup in the lab on cow protocol. So this is showing how coherent one-way protocol works. But as I mentioned, that the keys are to be random. So this is a QKD setup in our lab, a new addition to our lab, and we are theoretician gradually transforming to experimentalist. And so these are some set of keys which has been tested. And finally, what do we expect? So if I have a full quantum theory and every devices are available, then someday we'll have photon number polarized preserving photon number resolving detectors, mutually unbiased basis means. So this kind of things we'll have. Quantum memory will be there, quantum repeater will be there, and we'll be able to do certain things, but still will not be able to do perfect quantum cloning, quantum broadcasting. So certain things are allowed in quantum mechanics and certain are not. Now, before I stop, so in the beginning, I gave a disclaimer that in the beginning, it will be a random journey into the random world of randomness. So now I ask the question, was it, or whether my n+1th slide was correlated to nth slide? So here is a joke that here is my random number generator and he is reading 99999. Then the other guy is asking, are you sure that's random? So that's the problem with randomness. You can never be sure. So that's a problem, and we enjoy that problem. So I'll stop here. Thank you.
Thank you, Anirban. We kind of ran out of time, but I think maybe we can have a one short quick question if there is one in the audience.
Can I ask a question?
Yes, please.
Yes.
Yeah, Anirbanda, nice talk. So you see how I see that in Bell scenario. So let's say you are at Delhi, I am at Trivandrum, and you have your local randomness. That is ensured by your choice. I have my local randomness. At the end of the test, we end up with a correlated randomness. That is the important point. And that correlated randomness we can use, and that correlation is it means private between you and me. No eavesdropper knows this, because it is certified from Bob Bell test. And that correlation means shared randomness we can use for our key generation. Yes. But in contextuality test, I have also seen this paper, but I haven't gone through it. How they can certify randomness, because they also initially have to start with some randomness. Because here also, even we start with randomness, we start with local and randomness, but we end with a correlated randomness. But in contextuality experiment, this is a single system experiment. We start with our randomness to choose our measurement, and we end up with some randomness. So what does it certify actually? If it amplifies, then I haven't gone through it whether they have amplified the randomness or not.
No, so there are specific cases and especially when you are in local means like you are not
Yes.
geographically separated, then it will certify.
Uh-huh.
So then that part is very convincing. Means if you are means that's like what I was telling, that even in local theory, composable contextuality will work nice. So in your example, these two users are separated, but if you are not separated,
Yes.
then it will certify. Means you are doing it locally and you want to know that it's really random, the device has no failure.
Yeah, that I understand, but for a practical purpose of view, why this randomness we require? We require mainly for distance.
If you have a slot, if you have this casino kind of slot machine, so in slot machine it will be fine. So where it is local means.
But again, you require initially your seed randomness. So from where you
yes, I mean that's the requirement. And amplification is everywhere. Means that you need everywhere. So that's the true for key also. Means initially I need a random number to authenticate. Means otherwise means how Alice will know that he is talking with Bob.
Okay. Sure. Thank you, Anirban.
Okay. Then let me thank Anirban once again. Thank you, Anirban, for the nice talk. And now I would like to invite the next speaker, Anu Kumari. She is from Delhi Technological University. And hello, welcome. She will be giving a talk on classification witness operator for the classification of different subclasses of 3-qubit GSZ class. So, Ms. Kumari, over to you. Hello.
Yes, I'm presenting. I'm sharing my screen.
Could you speak a bit louder, please?
I'm sharing my screen.
Okay.
Your screen was visible but disappeared again. And now it's fine.
Okay, so is my screen visible?
Yes.
Yes, but you need to speak louder.
Okay, so good morning to all of you. First of all, I would like to thank the organizers of this conference to give us an opportunity to present our work. The title of my name is Anu Kumari. I'm pursuing PhD from Department of Applied Mathematics, Delhi Technological University, Delhi. The title of my today's talk is Classification Witness Operator for the classification of different subclasses of 3-qubit GH8 class of states. So quantum entanglement is a useful resource in various quantum information processing tasks. Once the particle becomes entangled, they becomes related in a way that cannot be defined using classical laws of physics, and the particles remains connected in a way such that the actions performed on one particle affects the other, even when the particles are very far away. So I'm not going into the deep of quantum entanglement because we have limited time. So in this work, we have defined different subclasses of GH8 class of states, and we have constructed classification witness operator for the classification of different subclasses of GH8 class of states. So and we have done this work for pure 3-qubit states. So I'll be discussing only 3-qubit pure states. For 3-qubit pure states, all possible stochastic local operation and classical communication in equivalent classes have been characterized as 1 separable state, 3 biseparable states, and 2 genuinely entangled states, namely GH8 class of states and W class of states. So here we have taken a pure 3-qubit state of the form this, where lambda i's are non-negative real numbers. Normalization condition is followed, and here ket0 and ket1 denotes the computational basis. Now we have two inequivalent SLOCC inequivalent genuinely entangled vectors, namely GH8 type vectors and W type vectors. GH8 type vectors may be written in this form as in equation 1, whereas W type vectors may be written in this form. Also, there are various measures of entanglement for bipartite as well as tripartite systems. Concurrence is an entanglement measure for quantification of bipartite quantum correlations, and concurrence is defined in this way for pure states, where rho A is the reduced state, and for mixed states, it is defined in this way as in equation 4. And tangle is an entanglement measure used to characterize three-way entanglement of a state. For pure 3-qubit states, tangle may be defined as 4 lambda naught square lambda 4 square. Tangle is 0 for W class of states and non-zero for GH8 class of states. Also, tangle is 0 for other classes such as separable states and biseparable states. So since tangle is 0 for separable states, biseparable states and W class of states, so their classification is important. This classification has been done in this reference. Also, 3 tangle may also be defined in terms of Kaufman-Kondo-Wouters inequality. So for pure state, pure 3-qubit state, CKW inequality may be defined like this. Here C12 denotes the concurrence of the reduced system. And similarly, C13 and C123 are defined in this way. So in terms of CKW inequality, 3 tangle may be defined as a residual entanglement. And for any general distinct I, J, K in 1, 2, 3, tangle may be defined in this form. This tangle remains invariant under any qubit taken as the focus qubit. So tangle is basis independent. And also there are various criteria by which we can detect the given state is entangled or not. But for the most of the criteria, we need complete information of the state to detect entanglement. But if we have some partial information about the state, we can detect whether the state is entangled or not using entanglement witnesses. These entanglement witnesses are Hermitian operator and have at least one negative eigenvalue. An observable W is known as entanglement witness if trace of W rho is greater than equals to 0 for all separable states, and trace of W rho is less than 0 for at least one entangled state. In the same line, we have defined classification witness operator. Suppose we need to define a classification witness operator for this class gamma 1, where gamma 1 is the collection of all the states phi, where phi are of the type this, where lambda i's are non-negative real numbers and the normalization condition is followed. Then an observable W is known as classification witness operator if the expected value of W with respect to the states not belonging to the set gamma 1 is greater than equals to 0. So that is trace of W psi is greater than equals to 0 for all the states not belonging to gamma 1. And trace of W psi is less than 0 for at least one state belonging to gamma 1. So these are the subclasses that we have defined in our work. So subclass 1 consists of 3-parameter family of GH8 class of states. Subclass 2 consists of 4-parameter family of GH8 class of state. Subclass 3 consists of 5-parameter family of GH8 class of states. And these are the normalization conditions.
You are not audible.
Hello, you are not audible.
We cannot hear you. Is the chair is there?
Yeah, I also cannot hear.
Yeah, we can't hear, I think. Should inform. I don't know whether.
This chair is available?
Hello.
Hello, Anu.
Ms. Kumari, your voice is not. Please check your settings. Hello.
অনির্বাণ
মনে হচ্ছে ও নিজেই বকে যাচ্ছে, কথা শুনতে পাচ্ছে না।
আসছি না। Hello. You have to do something about your audio, please. We can't hear you.
Hello, am I audible now?
Yes. No, again, you are not audible. I don't know. Please check your settings. You were audible just when you asked, are you audible now? Or am I audible now? Now you are again not audible. We can see your screen, but you are not audible.
Hello, am I audible now?
Yes, now I can hear you, but then it goes blank.
Yes, you are audible now.
Hello, am I audible?
Yes.
Yes, you are audible now.
Hello.
Hello.
Hello, am I audible now?
See, when you ask, am I audible now? You are. But after that, there is a deep silence.
I'm so sorry.
I think you can now continue.
Okay. So to define the motivation of my work, why we have classified different subclasses of GHL class of state, let me just recall the definition of teleportation and fidelity. Quantum teleportation is the transfer of quantum information from a sender at one location to a receiver at some other distance away. And fidelity is the measure of closeness of two quantum states. It is defined as the measure of distance between two density operators. Maximal teleportation fidelity may be calculated in this way, where f of u is taken as the maximum of this inner product, where maximum is taken over all the maximally entangled states in 2 cross 2 qubit system. Now, since GHL class of states lying in different subclasses have different applications, for example, If we compare GH8 class of states lying in standard GH8 class have more tangle than the GH8 class of states lying in subclass 1. And here we have calculated that GH8 class of states lying in subclass 1 have higher maximal teleportation fidelity than standard GH8 class of states. Here by standard GH8 state, I mean this lambda naught 000 plus lambda 4 111. So for standard GH8 state, the maximal teleportation fidelity with respect to qubit 1, qubit 2 and qubit 3, maybe this is equals to this 2, 1 plus lambda naught lambda 4 divided by 3, which is given in equation 15. And the maximal teleportation fidelity for any GH8 class of states belonging to subclass 1 of this type is given in equation 17. So by comparing equation 15 and equation 17, we can see that maximal teleportation fidelity of GH8 class of states belonging to subclass 1 is greater than or equals to standard GH8 state. Because if we substitute lambda 1 equals to 0, then they are equal. Otherwise, maximal teleportation fidelity of GH8 state belonging to subclass 1 is greater than standard GH8 state. So it is important to classify because once we know classify in different subclasses, because once we know the subclass of the given GH8 state, then we can use them accordingly in various quantum information processing tasks. Suppose if we want a GH8 state to be of more tangle, then we can use standard GH8 state. And if we are using it for teleportation, then we can use a GH8 state belonging to subclass 1. So in our work, we have obtained different classification witness operator for different subclasses. And moreover, we have expressed those witness operator in terms of invariance, which gives us our witness operator an advantage to use them irrespective of basis. So these are the invariants that we have used. So our result one may be stated like this. The classification witness operator for the classification of different subclasses lying within subclass 1, the classification witness operator are H1, H2, H3 for the 3-parameter family of GH8 class of states for parameters lambda naught, lambda 1, lambda 4, lambda naught, lambda 2, lambda 4, lambda naught, lambda 3, lambda 4 respectively. Here O1, O2, O3, O4 may be written in terms of observables, and the expectation values of these operators O1, O2, O3, O4 can be written in terms of invariance. So our witness operators may be written in terms of invariance. So they are basis independent. And similarly for classification witness operator for the classification of GH8 class of states within subclass 2, the witness operators are H4, H5, H6 for the 4-parameter family of GH8 class of states. Here P1, P2, P3 are given in this form, and O5, O6 in the expressions of P1, P2 may be written in terms of observables. And the classification witness operator for GH8 class of states lying in subclass 3 may be detected using H7. Also, we have considered an example. Suppose we consider a 3-qubit state of this type 5, where G and K are the vectors. Then we can compare this state with the states that we have defined in our subclasses. It is a 4-parameter GH8 class of states. So this state belongs to subclass 2. So from there, we can choose our witness operator accordingly. And here we have found the range of parameter P for which the classification witness operator classifies the GH8 class, this GH8 class of state. So these are the references.
Okay.
Thank you.
Thank you, Anu, for even with that kind of impediment of this noise thing coming out, you finished in time. We still have some time, maybe for a quick question. Anybody in the audience, please feel free to ask. Okay, if there are no further questions, then let me thank Anu Kumari once again. Thank you, Anu, for your nice presentation and telling us about your interesting results. Thank you.
Thank you, sir.
Now I would like to invite Anandamoy Dash Bhaumik from ISI, Kolkata. He is scheduled to speak on from no causal loop to absoluteness of cause, discarding the quantum knot logic. So Anandamoy.
Yes, am I audible?
Yes, you are.
Okay. Okay, so I am Anandamoy Das Bhaumik. The title of my talk is from no causal loop to absoluteness of cause, discarding quantum knot logic. This is a recent work by us. My collaborators in this work are Professor Priti Parashar, Professor Manik Bonik, and Professor Guru Prasad Kaur. Okay, let's begin. Let's begin from the idea of a classical knot logic. As we know that a classical bit can have two distinguishable pure states, namely say 0 or 1, and a NOT operation, what it does, it just flips the state. That means if you in the input, if it is 0, then at the output it will be 1, and if the input is 1, it will be 0. Now a quantum, what will be the quantum version of this NOT operation? In the quantum case, the input can be infinitely many possibilities because a qubit has infinitely many possible states. So the quantum version of the NOT operation will be something like the following: that if you feed the machine, the flipper, we also call flipper a NOT machine. If you feed it with psi, where psi is any qubit pure state, it will flip it to its orthogonal state, that psi orthogonal, and that has to be achievable for all psi. All that means all qubit pure state. In the block sphere, this is just flipping the arrow. Okay. Now there are many results that establishes that quantum knot operation is impossible, and there are many further manifestations of this impossibility of quantum knot. Here I just mention one of them, where it has been stated why quantum knot operation is possible, that it would require an anti-unitary transformation. Now anti-unitary transformation is basically an antilinear transformation, and as we know that Schrodinger dynamics time evolution is linear, so from this it is automatically ruled out at the beginning that knot operation cannot be achievable with quantum systems. Universal knot operation, that means irrespective of the whatever input qubit pure state you give to the machine as input, it will flip it. It is not possible. Perfect knot operation is possible. It's not possible. So what's the point of my talk then? I have started with quantum knot operation and I have reached to the conclusion that it is not possible in quantum mechanics. Then why this talk? In this talk, we want to address this question, that is this impossibility of quantum knot operation just a mere artifact of the linearity of Schrodinger time evolution? So we know that from linearity argument, we can rule out this knot operation. But what about if we remove the linearity assumption from the time evolution of quantum states? Well, what will be the status of this quantum knot logic if we don't invoke the linearity of time evolution of quantum states? This question is important and worth analyzing because some fundamental considerations suggest nonlinear generalization of Schrodinger evolution. In particular, the unification of Schrodinger dynamics and the nonlinear projection dynamics requires the slight modification of the deterministic linear Schrodinger evolution rule. So this nonlinear, there are requirements of nonlinear generalizations of the quantum dynamics. In this direction, The first proposal came from Professor Steven Weinberg in 1989. That he made some model of quantum theory where the time evolution is not linear. But that particular model given by Weinberg drew several criticism. Notably, one of them were by Escher Perez, Nicolas Gisin, Joseph Polchinski. Escher Perez showed that that particular nonlinear model was incompatible with second law of thermodynamics. Nicolas Gisin showed that that model allows faster than light signaling. Joseph Polchinski even showed that that model allows communication between different branches of the wave function, which seemed to him more bizarre than faster than light signaling. However, though that model given by Weinberg was had serious conceptual issues, however, there are several other nonlinear generalizations of quantum theory that subsequently came in the literature, which were consistent with relativistic causality and all other physical principles. So it can be there can be possible of nonlinear quantum theory which are at peace with all the known physical laws. Some of them I have listed here by Professor Pearl, Gisin, Girardi, Dioschi. Weinberg even gave such a model in 2012. So these are some nonlinear quantum theory where time evolution is not linear. They have incorporated appropriate amount of stochasticity in the model so that it remains compatible with everything else. So now the question is, what will be the status of quantum knot operation in these nonlinear models? Is it possible to conclude anything about the quantum knot logic without invoking linearity of quantum dynamics? So this is the question that we will try to answer in this rest of the talk. And we will see that we will propose a causal principle which is hitherto not that much investigated in particular to address this question. So let's dive into that. Now, what is causal principle? Causality basically is about relationship between cause and effects. And we are already familiar with a very, very basic causal principle, which we name no causal loop, that prohibits some kind of disagreements about different observers regarding cause-effect relation. If we state it formally, the no causal loop statement is like something like that, that if A is the cause of B for some observer, then for any other observer, B cannot be a cause of A. This is the statement of no causal loop, and this framework of special theory of relativity is perfectly compatible with it, since we know that light cone ordering remains invariant under Lorentz boost, which in turn suffices to prevent causal loops and thereby rules out the possibility of grandfather kind of paradoxes. So no causal loop is a causal principle, and it prohibits grandfather kind of paradoxes. But in this quantum knot operation, whether it is possible or not, we will invoke some other causal principle, which we have named the absoluteness of cause. The principle of absoluteness of cause is different from the no causal loop because it prohibits a different kind of disagreement among different observers. So if we state the formally the statement of absoluteness of cause, it sounds like something like that if A is the cause of B for some observer, then A will remain as the cause of B for all observers. So for no observer, it will not be that B occurs, but A did not cause B to occur. So that is why we say that absoluteness of cause. Cause cannot be observer dependent. It has to be absolute. And every observer should agree regarding the cause of any event. So this is absoluteness of cause. So it forbids a different kind of paradox, as we have already told, that you can say that where a sculptor creates a sculpture in some reference frame, according to some reference frame, whereas to an observer in some other frame, the sculpture is created, but it has not been caused by its creator. So there in this paradox, no causal loop is formed. So no causal loop principle has no capacity to rule out this kind of disagreement. The absoluteness of cause principle has to say something here that these things cannot be possible. So we have pictorially, we have depicted the situation. Suppose there are two observers, observer 1 and observer 2. Observer 1 says it is Leonardo da Vinci who had made the painting of Mona Lisa, and observer 2 completely disagrees with this fact and says Leonardo da Vinci has no connection with the painting of Mona Lisa. So these kind of disagreements are not possible. At least the absoluteness of cause principle prohibits this kind of paradoxical disagreement between two observers. Now, we will now come to some specific implication of this absoluteness of cause principle. Suppose we have two processes, two operations. Suppose EA and EB. In this figure, if you see, EA is rotation along x-axis, about x-axis, and EB is rotation about y-axis. Now, there are two cubes. The two cubes in case 1 and case 2 start from the exactly same initial condition. Now, the difference comes from the time order of EA and EB. If EA precedes EB, then the final configuration is something, and EB precedes EA, then the final configuration becomes completely different. So, the time order of these two time-like separated processes, these processes are time-like separated because they belong to the world line of the same physical system. But this time order of two physical processes can lead to distinct future, and AC has no problem with this. Why? Because time order of two time-like separated processes is an observer-independent thing, the time order. Hence, AC cannot prohibit the time order of two such processes to be the cause for distinct observations in their common future. But suppose EA and EB are two space-like separated processes. Now their time order is completely observer dependent. There are observers who will say that EA occurs earlier than EB. There will be observers who says EB occurs earlier than EA. So this time order is not a frame independent concept no more. It becomes a frame dependent concept, observer dependent concept, and hence it is not absolute. And so AC principle says that time order of such two space-like separated processes cannot be cause for future events, that is, events lying in their common causal future. So this implication is what we require to address the question of quantum knot logic. Irrespective of the dynamical rule of the model, whether it is linear or non-linear, we don't need to bother about that. If we consider this AC principle to be a causal principle to be true, then the following theorem is we will reach that any formulation of quantum theory satisfying the principle of absoluteness of cause will not allow a universal flipping device. By any formulation, we means we do not need to bother about the dynamics of that, whatever dynamics is imposed on that theory. If it is the quantum state space, the dynamics can be linear like Schrodinger dynamics or non-linear like Weinberg or Gysin and other models. All those linear or non-linear models, if they satisfy the principle of AC, will not approve a quantum flipping device. Now we'll shortly, very briefly discuss the proof. So the proof begins like the seminal EPR paradox. There are two spatially separated parties who are far away, but they are sharing the singlet state, composite state, the singlet state, the well-known state. Now, in contrary to the statement of the theorem, we assume that there exists a universal flipping device, that is a universal knot operation device, which we call F, and Bob has this device. Now we will analyze three cases. Case 1. Suppose in some inertial frame, consider the time order, the specific time order in which Alice performs sigma z measurement on her part of the composite system, that means on the singlet. Alice performs sigma z, and then Bob applies the flipping device on his part. So this is a time order. Alice first performs sigma z, then Bob performs his flipping device on his system. So let's see this step by step. After Alice performs this measurement, due to wave function collapse, the singlet will collapse to either 0011 or either 1100. So it will be a equal, the post measurement state will be an equal mixture of these 0011 and 1100. So the post measurement state is written sigma AB is this. Now Bob applies his flipping device. So obviously, due to convex linearity, if the state collapses to 0011 and Bob applies his flipping device, it becomes 0000. And if collapses to 1100 and if Bob applies his flipping device, it will become 1111. So ultimately, after both of their operation, the joint system will reach this state eta AB, which is half 0000 plus half 1111. And here it is very important that we have not assumed any kind of linearity on the quantum superposition. We have this transformation from sigma AB to eta AB completely follow from the definition of the device. Okay. Now consider the reverse order of their operation. That means Bob first applies the F, that is the flipping device on his system on his part of the singlet, and then Alice performs sigma z measurement on her part. Now there is a catch. After the action of Bob, the updated state is we write it chi AB. Now what is chi AB? We do not know, because we have no prescription about how the flipping device will transform a singlet state if it acts on one part of it. We know how it acts on quantum pure states, that it makes psi orthogonal, but from that definition it does not follow how it will act on one part of singlet. So we keep open every possibility for chi AB. Since we do not put any constraint on the action of F other than its definition, the form of the state chi AB allows a vast possibilities. So we allow vast possibilities. But here, at this point, AC principle has something to say about this chi AB. According to this principle, after Alice's measurement on her part of chi AB, the composite system should be eta AB. So chi AB can be any 2-qubit state, but it has to be compatible with the AC principle. If we think AC principle has to hold in my theory, then chi AB should be such that if Alice measures sigma z on her part, it should lead to the eta AB. Otherwise, time ordering of these space-like separated events will lead to an observable distinction in the future, which is prohibited by AC principle. So, though chi AB can be any 2-qubit state, but when Alice measured sigma z on a part of the chi AB, it should give to the same final state eta AB. Otherwise, AC principle will be violated. So there is only this restriction on chi AB, that it has to be compatible with the AC principle in case 1. The time order should not lead to distinct future. The time order of two space-like separated processes should not lead to distinct future. So that restriction, if we then the solution set for chi AB becomes all those sets who are correlated along z sigma z direction. So this is this convex hull, CH denote convex hull of all those entangled states who are correlated along z basis. And these convex hull also includes mixed states which are correlated along 0-1 basis. Now we go to case 2. Case 2 is completely similar to case 1, but Alice's measurement sigma z is now replaced with sigma x measurement, and the similar analysis follows. Now also chi AB has to be compatible with AC principle in case 2 also. So case 2, says that chi-ab has to lie in the solution set denoted by 2. This is another convex hull. This is convex hull of all those maximally entangled states which are correlated along x direction. So this is the chi-ab solution set. The solution set for chi-ab in case 2 is this. Now, AC principle, if AC principle has to be satisfied in both case 1 and case 2, then obviously, if both has to satisfy, then we have to look for the common solution for case 1 and case 2. The set 1 and the set 2, the solution set 1 and the solution set 2 have only one common solution, which is phi plus state, the state phi plus, which corresponds to alpha k equals 0 in case 1. In case 1, if you put alpha k equals to 0, it becomes the phi plus state, and in case 2, if you put beta k equals to 0, it becomes the phi plus state, and this is the only intersection point between these two sets. So this is the only common solution. So if we apply the flipper on the one part of the chi-ab, it should become this phi plus state, because this is the common solution in both cases, compatible with AC principle. Now we go to another case, case 3. This case is also similar to previous two cases, but this time the measurement at Alice's side is sigma y. And in accordance with the AC principle, now new restriction comes for chi-ab, and this scenario, this case 3 says that the chi-ab's solution set should lie inside another convex hull, which we denote by 3. This is all the convex hull of all those maximally entangled states which are correlated in the y basis. Now, what is important here is that the set 3 does not contain the phi plus state. So the phi plus was the common solution for the earlier two cases, but this case 3 does not contain that phi plus. That means AC principle cannot be simultaneously satisfied in these three cases if we assume the existence of that hypothetical machine F at Bob's side.
You need to wind up. Time is almost over.
Okay. So this is the general solution set, and as you can see that this three solution set has no common intersection. So let us briefly remark what we have assumed in this proof. We have assumed the existence of the singlet state, like Bohm version of the seminal EPR paradox, and this state. Recent developments in quantum information theory allow self-testing of this state prepared from some uncharacterized device, and we also have used the wave function update due to projective measurement. But at this point, we note that the wave function update has also been assumed by Gissing while deriving no cloning theorem from no signaling condition, as well as while established superluminant communications in Weinberg's nonlinear quantum mechanics. In fact, Polchinski had pointed out the crucial role of projection postulate in the second case. So in summary, what we have analyzed is a novel primitive in the causal framework, namely the principle of absoluteness of cause, which is distinct from just prohibiting any causal loop. Using this causal primitive, we have derived a basic no-go result, which holds true in any generalized formulation of quantum theory, possibly allowing stochastic nonlinear evolution. Apart from the foundational interests, researchers have also explored computational power of such nonlinear models. Seth Lloyd and Abraham has shown that nonlinearities can be exploited in such a way that NP complete problems can be solved in polynomial times. However, our no-go theorem establishes that any such generalized nonlinear model cannot approve perfect universal NOT logic if it is meant to be compatible with the basic primitive of absoluteness of cause. Further questions that can be addressed are that quantum theory allows imperfect flipping device, so it must be obviously interesting to obtain bound on the degree of imperfection from the AC principle, or any kind of generic restriction whether this AC principle imposes on any generic quantum formulation, whether that is also interesting. And any connection with the second law of thermodynamics, though I have presently I don't have any idea how it can be connected with second law of thermodynamics. So this is the archive version of our result. Thank you.
Thank you, Anandamai. We have run out of time.
Okay.
But there's one quick question one could quickly have. Is there any question? Okay, in that case, let me thank Anandamai once again. Thank you very much for your presentation.
Thank you.
Thank you. Now I would like to welcome Sohail from HRI.
Hello, am I audible?
Yes, you are.
Okay, let me share my screen.
Yes.
Yeah. And first of all, actually, I would like to thank the organizer for giving me an opportunity to present my work. So let me share my screen. Okay, is this visible?
Yes.
Okay. So the title of my talk is actual convolution algebra of superoperators and non-separability witness for quantum operations. And this work is done in collaboration with Professor Ujjwal Sen. So the outline of my talk is this. I will first the introduction, and then Choi-Jamil-Koski isomorphism and channel state duality, and then we will define a new product, and then we will identify the new product as actual convolution, and then we will find the identity element of the convolution algebra, and then spectrum of the superoperators, and we'll then derive some nice property, a nice property of convolution product. Okay, and the non-separability of bipartite quantum operation, and then actually I will conclude my talk. So the Choi-Jamil-Koski isomorphism, I will discuss it now. So let H1 and H2 be two finite dimensional Hilbert space. Okay, and phi be a map from the set of bounded linear operators actually on H1 to H2. Okay, and we assume that actually dimension of H is n, and EIJs are basically a complete set of matrix unit for BH1. Then the Choi matrix for phi, okay, is defined like actually this equation 1. And it can be easily shown that the map actually phi goes to rho phi is linear and bijective, and it is called the Choi-Jamil-Koski isomorphism. Then the Choi theorem says that actually this matrix, Choi matrix, is positive if and only if the map phi is completely positive. Okay, so this Choi-Jamil-Koski isomorphism and this Choi's theorem, okay, these two things actually help us to give actually completely positive maps. Actually, as I state, in a higher dimensional Hilbert space. Okay, and now we'll define a new product. Okay, so let F represent the Choi-Jamil-Koski isomorphism, and phi 1 and phi 2 are two maps in this space. So L of BH1 comma BH2, this is the space of actually maps or superoperator from BH1 to BH2. So So for Choi-Jamil-Koski isomorphism, actually the product does not conserve. Okay. So the composition of two maps are not actually conserved. So here we ask the question: does there exist a product in actually in the space actually L of BH1, BH2, which is preserved under CJ case isomorphism? So so the answer is yes, and the product is given by equation 3. Okay, and we extend it by linearity to the whole space. So it can easily be verified that this product makes the space L of BH1, BH2 an associative unital algebra. Okay, and the CJ case isomorphism is an actually algebra isomorphism between this space. Okay, and the identity element is this phi e, and its action on a matrix element EIL that will give you to delta IL times identity. Okay, so now we'll identify this product as convolution. Okay, so if F1 and F2 are function actually from real line to real line, okay, then their convolution is defined like equation 4, and this convolution make the linear space of integrable function an associative algebra. So so the convolution actually can not only be defined for actually real lines, it can also be defined for actually groups. Okay, so let actually G be a finite group and F be a field, and let this L actually G comma F be the vector space of all maps from G to F. So the convolution of actually F1, F2 is defined like this equation 5. Okay, and the sum over is actually over all the pairs X and Y, actually whose product give us G. Okay, and this convolution can actually equivalently expressed actually by equation 6. So okay, so I will state a elementary theorem now. The theorem is that actually convolution algebra L G comma F is isomorphic to the group algebra of G. Okay, so the brief outline of actually proof of this theorem is that so let actually D is the cardinality of G. Okay, and a functional F from G to C complex number is completely specified actually by the D tuple F G on comma FG2 like this. So the set this L to G comma C is a function actually of functional is a vector space under the usual actual operations. Okay, and it is a vector space of dimension D. So and let A be the group algebra of G, okay, over the complex field. Then a generic element of A will of this form, this A equals to actually sum over I equals to 1 to D alpha I G I. Okay, so under the identification that A goes to actually this actually D tuple, the two space A and L of G comma C are isomorphic as vector spaces. Okay, sorry. Now there is a natural multiplication, okay, on A, which is induced by the group multiplication, and which is defined like this equation. Okay, so and And now using the fact that actually in group multiplication table, along a row or a column, each element of the group appears on and only once. So this sum can be rewritten like this. Okay, so this can be rewritten like this. Okay, and thus actually we proved that the convolution algebra is isomorphic to this L of G comma C. Now consider a group and an arbitrary algebra A tilde, okay, and let A denote the group algebra of G. Then okay, then this D tuple, okay, of element of algebra actually completely specifies the map phi. Okay, and using the same type of argument, the space A tensor A tilde and L of A comma A tilde are isomorphic as vector spaces, okay, under this identification equivalently by this. So okay, so the space this with multiplication rule induced by the group multiplication in G and multiplication in actually A tilde, and this space with convolution are basically algebras and they are isomorphic. Okay, and actually this fact follows from the fact that actually along group multiplication table, okay, so actually along any row and column, each element of the group appears on and only on. So yeah, so actually this fact help us to prove the theorem like this. So now so actually let us actually move back to the space this actually L of actually BH1 comma BH2 of linear maps. Okay, so it is clear that actually BH1 is not a group algebra because this actually matrix element does not form a group. Okay, under matrix multiplication. Okay, but these elements have a nice property that if you actually rearrange this element actually in a table similar to actually the group multiplication table, okay, then along any row or column, actually each element, actually not each element, some element appears on and only once actually. Okay, so this is the difference actually actually the previous case. Okay, so and this fact help us to prove that the convolution we defined on phi is basically preserved under Choi-Jamil-Koski isomorphism. So thus we give the theorem that the convolution algebra this is isomorphic to the algebra BH1 tensor BH2. Okay, where the isomorphism is the actually Choi-Jamil-Koski isomorphism. Now the identity element. So the lemma is that the identity element of the convolution algebra is basically the completely depolarizing channel. Okay, so you assume that rho is any arbitrary density matrix. Okay, so its action. Okay, so actually the action of the identity element on a row is like this. So it is from so actually it is clear that the identity element is basically like the depolarizing channel on BH1. And now we define the spectrum of a map phi. Okay, so And this spectrum is basically the collection of all those lambda belongs to C such that phi minus lambda and phi actually is not invertible. Okay. And from here it is clear that the spectrum of phi is basically the eigenvalues of the Choi matrix corresponding to phi. So here we give some lemma that quantum channel phi is actually unitary channel if and only if the convolution of phi with itself is n times phi, where n is the dimension of the Hilbert space H1. Okay. And the second lemma is the convolution of transposition operation on BH1 with itself is a completely depolarizing channel. Okay. And the convolution of Schur multiplier map SA and SB is equal to the Schur multiplier map associated with AB. And then we give a lemma related to the actual complementarity channel. And the lemma is that if phi tilde is basically complementary to phi, then the latter is unital if and only if the convolution of phi tilde with itself is phi tilde. Okay. Now we will define some known operation on the actually space of superoperator with the help of Choi-Jamel-Koski isomorphism. Okay. So any density matrix, okay, belong to this BH1 tensor BH2 can be written like this. So this induces a map phi, which is given by this equation 11. Okay. Now transposition with respect to system 1 or Hilbert space 1 actually on the density matrix induces a phi T1, which is defined like this, and we call this phi T1 as the transposition of phi. Okay, and we extend it by linearity to the whole space. So, and it is clear that the trace, okay, and we define the trace of phi to be actually sum of its actually spectrum. Okay. So it is easy to actually show that the trace of actually this actually phi 1 convolution phi 2 is basically trace of phi 2 convolution phi 1. So this behave like actually usual trace operation. Okay. So and we define a projection like operator on the space of superoperator. So if T is a linear operator and this lambda i's are basically the set of eigenvalues of T, then the projector onto the eigenspace corresponding to the eigenvalue lambda I is given by this equation 15. And with the help of the CJK isomorphism, we translate this formula to the space of phi. Okay. And this phi represent the convolution product here. Okay. So now we discuss how much time I have.
You have about 5 minutes time.
Okay. Okay. So a bipartite operation phi. Okay. Actually from actually BH on A tensor B H on B to BH to A tensor BH to B, it is called separable if the Krauss operator of actually are of this form, equation 17. Okay. So it can easily be shown that the set of separable operators is closed and convex, hence a witness of non-separability of bipartite quantum operation can be constructed. So these are the matrix unit of the spaces, this, okay, respectively, and the phi is bipartite quantum operation. Okay. So its action on this space can uniquely actually specified by equation 18. Okay. So now we take the partial transposition of actually rho phi, okay, with respect to the bipartition base, H1A tensor H2A and H1B tensor H2B, and this induces a map phi T A1 A2, okay, which is defined like this, equation 19. And then the projector, okay, so actually let the spectrum of this map is basically the lambda z, okay, and let lambda I be like a negative real number, then the projection like operator associated with this like lambda I is given by equation 20, okay. So we can then define a witness operator for non-separability of bipartite quantum operation phi like this, equation 21. And in particular, it is clear that the trace of this W, okay, and convolution phi, that will be less than 0. So actually this thing implies that phi is non-separable. So the conclusion is that we have defined a product in the space L of BH1, BH2, which is preserved under the Choi-Jamil-Koski isomorphism, and we have identified the defined product with convolution product on the same space. In particular, we have shown that the algebra L of actually BH1, BH2 is isomorphic to the algebra BH1 tensor BH2, which actually with the isomorphism being the actually Choi-Jamil-Koski isomorphism, and this statement can be seen as a generalization of the theorem stating that the convolution algebra L G, C is isomorphic to the group algebra G. The identity element of the convolution algebra is basically actually the convolution is actually basically the completely depolarizing channel. And as an application of convolution product, we have shown that it is possible to construct a witness operator for non-separability of bipartite quantum operation actually in the space of quantum operation itself. Yeah, so that's all. Thank you.
Okay, thank you very much for finishing in time, Sohail. We have time for a few questions. If there are any, please feel free to ask. Okay, even if the audience, anybody has questions, they can write to Sohail directly. Okay. Thank you, Sohail, once again for a very nice talk. Thank you very much.
Yes, sir. Thank you, sir. Thank you.
Now I would like to invite Hari Krishnan to join us.
Hi.
Hi. Welcome. So Hari is from IISER Trivandrum and he will speak on state-space structure of tripartite quantum system. So over to you, Hari. You have 20 minutes, you know that, right? So we are running 10 minutes short. So you can go up to, I will give you an alarm 2 or 3 minutes before time. Carry on.
Are you able to see my screen?
Yes, no, not at the moment. Yes, now it has come. Okay.
Okay, so hi everyone. I'm Hari Krishnan, and I'll be giving a talk on the state-space structure of tripartite quantum system, which is actually based on my paper of the same name, which I did in collaboration with my batchmate Ashish and my mentor Manik Badik, who is here right now. So let's get started. Coming into tripartite systems, if you look at the entanglement, it's not as simple as in the bipartite case. Like in bipartite case, the state is either entangled or severed. But in tripartite system, it gets more complicated. And second thing is that entanglement verification is easy, at least in some bipartite systems, which is the Saras-Sorodoki criterion. But this is not the case for even the simplest tripartite system of 3 qubits. So let's start by defining the fully separable states. So let's take a pure state chi ABC, and it is called fully separable or fully product if chi ABC can be written as some psi tensor phi b tensor eta c. And the control of fully product states is denoted using curly f of ABC, and the state belonging to curly f of ABC is generally called a fully separable state. Now, coming to the definition of biseparable states, we call a pure state chi ABC A versus BC biseparable if chi ABC can be written as some psi A tensor phi of BC. And it is important to note that this phi of BC can be entangled at B versus C cut. Now, the convex hull of all the states which are biseparable across A versus BC cut, we denoted use curly B of A versus BC. And similarly, we can define curly B of B versus CA, C versus AB. Now, having defined these three sets, we can proceed to define two more sets. First is the curly B convex hull, which is convex hull of BAB, A versus BC, B versus CA, and C versus AB, and also B intersection, which is the intersection of all these three sets. And a state which is in this convex hull is generally called as biseparable. Now, an interesting to note is that the set of fully separable states is a strict subset of the B intersection of ABC, which is actually counterintuitive. And this was first proved by Bennett in his paper. Now, going forward, we define what we call as PT states. So let's consider a density matrix rho ABC, and rho ABC belongs to the curly of A versus BC. If the partial transpose of rho ABC, which is denoted here, is semi-definite. And similarly, we can define rho B versus CA and rho C versus AB. And as in the previous case, we can define the convex hull of these three states and also the intersection of these three states. And we come to our main result, that is B intersection of ABC is a strict subset of P intersection of ABC for the Hilbert space CDA, CDB, CDC, where D is greater than or equal to 2. And this proof is carried out in construction, and also it is done in two parts. The first for the case where D is equal to 3. And for that, we consider this the orthogonal product basis, which was introduced in this paper by Agarwal, Halder, and Manik. So this is a set of states from B0 to B6, and B0 contains 3 for each k going from 0, 1, and 2. And each of B1 to B6 contains a total of 4 states, where I and j take values from 0 to 1. So total we have 3 in B0 plus 4 each from B1 to B6. So that's 24, 3, a total of 27 states. And we also introduce another state S, which is defined as follows. And using these states, we construct a new set, which is UPB, which is unextendable product basis. And how do we construct this? We consider the state S, take its union with all the states in B0 to B6, which are orthogonal to S. So if you look at the structure of S, we see S is not orthogonal to B0, any of the states in B0. And from B1 to B6, it is orthogonal for all the states except psi 0, 0. So that is what we do here. We take a union of BL where L is from 1 to 6, and we remove the state corresponding to psi 0, 0. So that gives us a total of 6 into 3, which is 18 states. And we append this S state to this. So the total of states in this set is 19. So the cardinality of this UPB is 19. And the 8-dimensional subspace orthogonal to this, like 8-dimensional because we are working in 27 dimensions. And since this is an unextendable product basis, the 8-dimensional subspace orthogonal to this will be fully entangled. So what we do, we take the normalized projector in this fully entangled subspace, which is defined as rho, and which is of rank 8. And then we put forward this proposition, that is the state rho is PPT in all three bipartitions, but it is not separable in any of these bipartite cuts. That is, 3 is contained in P intersection, but not in B intersection. Now, the proof is as follows. Like, we know that all the terms in rho are separable pure states with real coefficient. So when we take the partial transpose, it doesn't matter which system with respect to which the partial transpose is taken, but for any partial transpose, we get the same state rho. So from this we can conclude that it is contained in P intersection because rho is a density matrix and that is positive semi-definite. So the transpose will also be positive. Now coming to the other part, to show that it is not biseparable, we again says that rho is a rank 8 density operator, and if rho is A versus BC biseparable, then we must be able to write as a convex combination of 8 mutually orthogonal states because it is a rank 8 density operator. And these states should be separable in the A versus BC cut. And since it is in the orthogonal subspace, they must be orthogonal to the states in UP. These are the conditions if A versus BC is biseparable. But we see that we can only find 4 mutually orthogonal states which are separable and which are orthogonal to the states in UPB. This was actually shown in the previous paper I mentioned. And since there are only 4 such states and not 8 such states, we can conclude that rho is not A versus BC vice. So rho is not contained in this curly B of A versus BC, and consequently, rho is not contained in the integral. So this completes our proof. And this is for the D equal to 3 case. Now we can easily generalize this to higher dimensions for D greater than or equal to 3 in the same manner we did for D equal to 3. Now coming to the next part, for D equal to 2 case, we see that we cannot apply the same technique. If we do this, it doesn't work because in the previous case we wanted 8 states, but we had only 4 states. In D equal to 2 case, there is no such deficit of states. We are always able to complete this required states. Again, this was proven by Bennett in his same paper which I mentioned, and also in this paper by David P. Divenzo. Now, how did we prove this? We first looked into this particular PPT entangled states in C2 tensor C4, which was introduced by Haruki. And we thought of C4 as C2 tensor C2. And so we had these 4 states, Psi1, Psi2, Psi3, and also the state phi of ABC, where phi depends on a parameter B, which goes from 0 to 1. And using these, we construct the state chi ABC, and again we construct another state sigma ABC, and sigma C can be explicitly written in this form, as given in equation 7. Now, what we did was we took the symmetric permutations of sigma ABC, that is sigma ABC plus sigma BCA plus sigma CAB, and new state eta ABC. The rank of eta ABC and all its partial transposes with respect to A, B, and C, they are all 8. So what we did was we tried to reduce this rank. So we took eta ABC and we added and subtracted some matrices to get a new matrix H of ABC. And H of ABC matrix is positive semi-definite. So we normalized it to get a new density operator rho of ABC. And we make the following observations about rho of ABC. First is that rho of ABC is a valid density operator for B in 0, 1. Second is that rho of ABC is in the P of A versus BC, that is its partial transpose with respect to A is positive for all B contained in 0, 1. And it is in P of B versus CA and C versus AB for B in the subset 0, 1 from approximately 0.8 to 1. Let's call that some R, which is contained in 0. And we put this new position, that is for the parameters of B in curly R, the state rho ABC is in P intersection, but not in B intersection. So from observations 2 and 3, we can immediately prove the first part, that rho is contained P intersection for B in the subset of 0, 1. Now we need to show that the state rho ABC is not separable in the AB versus C cut, and for that we will use the range criterion. Now, what does the range criterion say? It's if a state rho ABC is separable in the AB versus C cut, then according to the range criterion, there should be a set of products psi A tensor phi k which span the range of this rho ABC and also the partial conjugate. So that is psi A tensor phi k star that should span the range of the partial transpose of rho ABC with respect to C. That is a condition of the range criterion. Now we write down rho ABC more explicitly and also the partial transpose of rho ABC with C more explicitly here. And we observe that a vector in omega in the range of rho ABC can be written as this form, as in equation 11, which is evident from the structure of ABC. Now, without any loss of generality, any element in the set of psi tensor phi k can be written in the form of one of these three vectors, v1, v2, or v3, where p is non-zero. And what we do is we compare equation 11 and equation 12 to get equation 13, where v2, v3 has been simplified. And we take the partial complex conjugation of v1, v2, v3 to get equation 14. And according to the range criterion, these vectors should span the range of partial source of rho with respect to C if it is separable. Now let's consider the vector u, which is in the range of rho BC, which is in the range of partial transpose of rho ABC. And we can observe that this particular vector cannot be spanned by v1 star, v2 star, v3 star. So this implies that rho ABC is not separable with respect to C versus AB, and so it does not belong to the intersection B intercept. So this completes our proof for B equal to 2 keys. Now I'll just sum up our using this diagram. So the green circle here is the FABC set, which is the convex hull of all the fully simple states. And the red leaf, this red leaf is the biseparable state with respect to A versus B. And similarly with respect to B versus CA and C versus AB. And if we take the intersection of the three red leaves, we can see that the green circle of fully separable states is contained within the intersection. So this is the result mentioned, which the black dot implies that the fully separable state is a strict subset of B in that. And this was proven by Bennett. Then we also define the PPT with respect to A versus BC set, which is this blue leaf here, and B versus CA and C versus AB. And the triangle here, this triangle is the convex hull of all the biseparable, and the blue triangle is the convex hull of all the PPT states. And the red, the triangle, this particular state implies that the convex hull of biseparable states is a strict subset of the convex hull of PPT states. This was a result proved by Ha and K. And our result, the result I presented, is denoted by this star here, which implies that the set of B intersection is strictly contained within the set of intersection. Now, we would actually like to point out one remark that Lig and Werner had actually proved that for a 3-qubit system, it turns out that these two sets, P intersection and B intersection sets, are the same if we limit ourselves to a particular class of that commute with unitaries of the form U tensor U tensor U. And we would actually like to thank Professor Werner for pointing this out to us. And for that particular case, these two sets are the same. But our results show that this is not the case for the generic case. When we do not restrict ourselves to this particular set of states, these sets are not equal. P intersection is not equal to B intersection. And I would like to conclude with some possible directions of future research. First is that we have shown that these two sets are not the same. So how does the extreme points of these sets look? So that is one direction. And the other part, to check if there are any channels that can take a tripartite to these these sets? Like, are there any channels, like take any state row ABC to the fully separable or the B intersection or the P intersection? Like, similar to entanglement breaking channels, how does it look in the tripartite case? So I would like to conclude my talk here. Thank you. Thank you for giving me this chance.
Thank you very much, Hari. Hari finished well within time. We have time for some questions. Anybody in the audience? Feel free to ask questions. Okay, if not, let me thank Hari once again. Thank you very much for the
thank you for giving me the chance.
Yeah, thank you very much.
Okay,
with this, we come to the end of the morning session. Let us thank once again all the speakers: Anirban Pathak, Anu Kumari, Anandmoy, Shohail, and Hari. Thank you for your nice talks. And we'll take a break here, lunch break here, and we reconvene for the afternoon session at 1400 hours. Thank you.
Thank you, Subhashish,
Thank
for
you.
hearing this session. Okay, thank you. Thank you, Anirban.
Okay. Bye.
Okay, we will meet at 2 p.m.
Okay.
To chair this session.
Am I audible?
Yes.
Thank you, Debashish, for the nice introduction. Welcome you all in this afternoon session of the 8th day of this conference. So we have 3 speakers in this session. Professor Valerius Karani from CQT Singapore, then Professor Runia Oduan from ICQ China, and Professor Indranil Chakraborty from IIIT Hyderabad, India. So our first speaker is Valerius Karani, who is this principal investigator and professor at the Center for Quantum Technologies, National University of Singapore. So he received his PhD degree from École Polytechnique Fédérale de Lausanne in 2000, and then he moved to the University of Geneva, where he worked on quantum information science and then basically quantum cryptography, Berlin non-locality, etc. In 2007, he joined the National University of Singapore as a member of the physics department as well as principal investigator at CQT. So today he is going to talk about irreversibility as irretrodictability.
Yes, well, thank you for the introduction. I presume you can hear me. And so I will start sharing the screen and I hope everything will go well. Okay, so yeah, this is a topic that is very new for me and started during the pandemic. And it's also something that is not a lot of quantum. In fact, I have only one quantum slide. So bear with me, and I hope maybe you've never heard about these things and you will learn something. And maybe you will teach me something because I'm, again, not a great expert yet of these things. And so I would hope that towards the end, at least you will understand the strange title. Irreversibility is something I'm going to explain, and irretrodictability is a word that some people made up at some point, and I hope this would be one of the things that you learned today. Right? I cannot advance my slides. I can like that. Okay. So, well, first of all, in everyday life, we know what irreversibility means. The process on the left is supposed to be reversible, because if I were to see a movie of the yellow ball hitting the red ball and the red ball getting into motion, and I play the movie backward and I see the red ball hitting the yellow ball, the two motions make perfect sense. Okay, if I don't see anything else, I would not be able to distinguish in which sense the movie is being played. So this is something we call reversible. On the other hand, if I see an egg that is entire and gets broken, and I see now the reverse of this movie, and I see the broken egg being reformed, this looks very implausible, and therefore this would be called irreversible. Okay. So this is somehow what we're dealing with in this topic, and you know that this is related to the second law of thermodynamics. Sometimes it's related to the arrow of time. So what I'm going to tell you today is mostly phrased in terms of thermodynamics, but exactly the same formalism, the same approach is applied to any form of time reversal in physics. Okay. So let me just go briefly through the science of irreversibility, some milestones that you might have heard of. First of all, of course, is Boltzmann, who tried to address these questions at the end of the 19th century, beginning of the 20th, and he came up with this H theorem that is controversial. It's controversial because still it's very hard to accept that irreversibility can come from reversible dynamics. So how does that happen? And of course, there have been many developments since, right? And in between, while people were developing the philosophy somehow, there have been some tools that have been widely used in the first half of the 20th century and still are used today, that are called fluctuation dissipation relations. And you might have learned of them in your undergraduate classes, which means something like this. If something experiences friction when driven, it will experience fluctuations at rest. And well, the Brownian motion is the canonical example of that, right? If you were to try to drag a particle through water, of course, it experiences friction because, well, there is water there. But this water, this liquid that creates friction, is also something that is made of molecules. And therefore, if you leave your particle there, you will see this particle moving around because it's being hit right and left and by these molecules. Other examples are the thermal noise, 1928, the reciprocity relation of Onsager they used in chemistry. And then in the 1950s, Cullen and Kubo and many others came up with a general approach, including to quantum theory. For this is the fluctuation dissipation relations are usually fluctuations near equilibrium. And then a few years later, and let's say for the sake of the argument, at the end of the 20th century, although there were some Russians who anticipated it by a couple of decades, people found fluctuation relations that are even valid far from equilibrium. And I'm going to present to you the two most famous ones that are the ones of Dzerzhinsky and of Crookes. So what is the idea? The idea is that there is the work that is being done on a system, so there is some work being performed on a system in contact with a thermal reservoir, and this work brings the system from an initial state to a final state. In this context, the second law of thermodynamics can be rephrased by saying that the average work that is being that you have to provide to the system to go from that initial state to the final state must be larger than the difference of free energy between these two initial and final states, the supposed equilibrium states. Well, this is just you write the second law of thermodynamics, and then you know that in case of constant temperature, that's what you get. And now Dzerzhinsky equality is something for me amazing. Okay, so what it says is that the inequality on the right for that type of processes come from an equality, and the equality is if you look at work as a statistical process, that sometimes work can have some value, sometimes other values, and you say the average value of work must be larger than the free energy, the difference of free energy. However, the exponential of minus beta times work is equal to the exponential of minus beta times the difference in free energy. And this is a kind of amazing result if you think about it, right? So it means that in such a process, again, this is work done on a system that is dissipating into a thermal reservoir. The exponential of the average of work is the exponential of the difference of free energy between the initial and the final state, whatever the process is in between. A way of proving that, of arguing for this, was found the following year by Crookes. And Crookes decided, had the idea that's very natural in studies of irreversibility, to compare the process that is happening with a reverse process. It kind of makes sense, right? If the reverse process is different from the forward process, then somehow you can say that the thing is irreversible, right? So what Crookes proved is the relations that is there, that I will prove at the end of the lecture for you, but with my notation and my approach that is probably simpler than theirs. So what Crookes proved is that if you have a value of work that is larger, the equation that's written there, but let me just read it in some examples. If you have a value of work that is larger than the difference of free energy, and then you compare these to a reverse process in which you would extract an amount of work that is larger than in absolute value than difference of free energy, then this ratio is exponential in that number, W minus delta F. It means that the probability on top is much larger than the probability at the bottom. It means, if you want to put it in this way, it means that if the work that you observed is larger than the difference of free energy, most likely you're observing the forward process rather than the reverse process. The forward process is much more likely to produce that amount of work than the reverse process. And in graphics, this looks something like that. So if I have work and my possibly free energies, the forward process, a distribution of work that looks like this. You see that most of my work is above the difference of free energy, although occasionally, you know, the second law is statistics. So occasionally you can have an amount of work that is less than the difference of free energies. The reverse process looks like that, usually plotted by symmetry around the same axis. So you just take the minus of the horizontal axis, and the two curves intersect at exactly the value work equal difference of free energy. Now you may say, okay, that's very nice. How is it used? Well, it's actually used. So here is an experiment done in 2005, where the idea was to pull a molecule of RNA that is usually in a folded configuration and pull it until it stretches. And I mean, the graph on the left represents the experimental value. So when the molecule gets stretched, somehow there is a kind of hysteresis there, there is a change in energy. And then on the right, you have the curves, the similar curves that I showed you before. So indeed, the reverse and the forward process for some types of cases. And you see that indeed, the work that is observed has this distribution that as expected, and because of this, they could measure the difference in free energies that is not easy to compute in theory. Okay, well, that's the context for my talk. Okay, now let's speak about time reversal. So you see, in Crookes fluctuation relations, you need the reverse process. If you're not interested by this kind of fluctuation theorems, just think of time reversal in general, in the universe. I would like to reverse the time and go back to the time of the Big Bang and these kind of things, right? So if you think about doing physics of such a reversal, what is physics? I mean, usually physics is the initial state is free for you to choose. The laws of physics determine the dynamics. And when you put the initial state into the dynamics, you propagate them and you get the final state. So now if I want to do the physics of the reverse process, I have to do the same. It's not just enough to watch the movie backward, because that would be simply like just looking at that final state and looking back. What I need is, what is the reverse dynamics? It must be a valid dynamics. It must be something that I can put any state in. The initial state from the future should be any state, not just the state that I observe now. I should be able to do that reverse dynamics for every process, for every initial state. That's what it means to define a reverse process. And so what is this reverse dynamics? In particular, a question that has been posed many years ago is, is this reverse dynamics determined only by the laws, so only by the forward dynamics? And the answer was given in the 1950s by Watanabe, and the answer is most usually no. Okay, now I'm going to argue why this is usually not the case. So remember, now our goal is to define what is the reverse dynamics. And let's start with something simple. Let's start with a case where the reverse dynamics is defined by the laws. So this is the bilateral deterministic dynamics, or for quantum practitioners, Hamiltonian dynamics. So this is a dynamics such that is deterministic, and not only is deterministic forward, but it's also deterministic backward, if you want. So there are trajectories. Every state evolves into a given unique state. So here my states are represented by these black dots. It's classical in this case, the example. And you have that this state evolves into that state, these states evolve into that state, these states evolve into that state. Well, of course, if you have such a channel, then it's absolutely obvious that the reverse is just you take the arrows and you change the direction of the arrow. So here, indeed, if I give you the forward channel of this type of Hamiltonian dynamics, then the reverse is the obvious reverse. If I mean, if you want in quantum information terms, if your channel is unitary, the reverse channel is U dagger. That's no much discussion here, so that's fine. Now, something that is pretty interesting, I don't know if you ever thought about that, is that these, this is definition of inverse, you know it, and this would be a classical case when you drive your Hamiltonian. But what I wanted to stress is that this is if and only if, also in quantum mechanics. So let me say it again. The reverse channel is uniquely determined by the physical channel and is the inverse channel of the physical one, if and only if the forward channel is an Hamiltonian channel or unitary channel or bilateral deterministic dynamics or whichever theory you want to have. So it means in every other case, as soon as your channel forward is not Hamiltonian, is not unitary, to determine the reverse channel, you'll need to do something else. You need to add some pieces of information. And the question is, which ones? Okay, let's try. Just to give you an example, like appetizer, right? This is a type of erasure channel where every initial state gets sent to the final state that I chose to be probability P on this one, probability 1 minus P on the second, probability 0 on the third. The fact that probability 0 on the third is not important, could be any example, just for the sake of the drawing. So this is a channel that destroys all possible information on the input, right? Every information in the input is thrown into the garbage, and what is produced is this unique state P1 or minus P0. So what is the reverse of this thing? It's clearly not the inverse, because the channel is not invertible in the first place. So you can't just invert it. The matrix is not invertible at singular eigenvalues, sorry, at 0 eigenvalues. And so what would be the reverse state here, reverse channel here? And what is missing? Okay, physicists usually have an answer, which is, let's reduce the dynamics to an Hamiltonian dynamics. So let's close the open system. What do physicists say? They say, well, if I have a channel like this one, or any channel that is not Hamiltonian, the truth, right, the underlying truth is that there is a larger space in which everything is unitary, and I'm just seeing part of it, right? So you can dilate any channel to a unitary channel with an unschiller and entanglement later. So what you do, again, I do it classically, I could do it quantum, is you say, I have my state is, my system has 3 possible states, but I have a path that has many states. And of course, now this object is a tensor product, or the Cartesian product in the classical sense, of the systems times the path. And now, if my path is the correct one, then here I will have a unitary dynamics. So now this state will be to this, will go to that state, this state will go to that state, this state will go to this state will go to that state, and so on and so forth. And this is reversible as before. So now finding the reverse process would be just, okay, I change the direction of the arrows, and then I trace out the path, and we get something. Now, I want to propose to you a different approach. Let me first this use statistical physics, and the arbitrariness in this construction is that, I mean, you don't know what are the path and the total dynamic, right? If the only thing I give you is the channel small phi, the rest is your fantasy, right? You may say, oh, I model my bath by bath of harmonic oscillators, and sure, you can do that. And then the interaction will be optomechanical coupling between my bath and the harmonic oscillators of the harmonic oscillator of the bath and the system. Sure, you can do that, but you don't know, right? In reality. And honestly, I don't think any thermal bath is actually a collection of harmonic oscillators. It's just a very convenient way of representing things. So you see, if phi, the channel, is given, you are adding an element of arbitrariness in order to purify the system and the dynamics, and now you can trace. Now I will tell you another way to derive the reverse process. And this is logical inference. So how does logical inference work? Well, the logical inference is the kind of thing that nowadays we have to use it, unfortunately, very often. The logical inference is the following process, right? It is the process when you see the cause, when you see the effect and you want to infer the cause. Example, I test positive for COVID-19. Thanks God I didn't. But anyway, what is the likelihood that I actually have the sickness? Oh, and of course, the alternative is that the test gave a false positive, right? So here I see so what is the causal process? The causal process is I have COVID or not, and as a result, my test gets positive. But what I see, of course, is the opposite. I see the end of the process. I see the fact that my test is positive. And you ask, what is the probability that I actually have the sickness? Now, why is this important? Because imagine that the sickness is not COVID, but is a very, 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 very rare sickness. Something that happened last times 200 years ago and has not been seen since. And now I test positive for that thing. I mean, how likely it is that I have that strange sickness compared to the likelihood that there was a false positive. You see, the fact that nowadays many people have COVID makes it probable that if I test positive, I have COVID. If I test positive for a very strange sickness, then it's probably most likely that I don't have it. That's the idea of the prior. I mean, most of you might have recognized the idea of the prior that is in all logical reasoning, right? In order to make an inference from the future back to the past, I need to have a prior on the past. I need to know, in this case, how likely it is for a general human being to have that sickness. And then I add the piece of information that I tested positive, and I infer back the likelihood that I actually have the sickness. So how does that go? Well, if I have my forward channel from the sickness, from the virus to the test, I add my reference prior, how likely it is that I have the sickness, and then I just construct my reverse channel by equating these. So by saying that, I mean, this is just a posterior. This gamma hat is nothing else than the sum over x of the left-hand side. So is the probability of y given this input. So there's nothing new here. And I just declare that my reverse channel is defined in this way. Now, you may say, well, this is a bit of a strange recipe, but that's the recipe that is used in inference. So I would get this formula, by the way, that my reverse channel is the forward channel multiplied by this beautiful term that depends on my reference prior. If you go into the literature on inference, this reasoning goes under the name of Jeffrey's update, or Jeffrey rule of probability kinematics, is related also to the virtual evidence by Perm, and is widely believed nowadays to be the way of performing Bayesian retrodiction in the case where your posterior is not sharp. When your posterior is sharp, so if this gamma y were to be a delta function, then everybody knows how to do Bayesian retrodiction because you just take the conditional probabilities. Anyway, this is just for your information. I mean, I cannot explain everything in 45 minutes. So if someone has questions, you can ask me later, or you can study these matters. Just please trust me at this point that this is the way where that backward inference are done in logic and actually machine learning, for instance, right? You see the image and you want to infer the cause of the image and whatever. This is exactly the type of formula that is used for that kind of inference in a simple channel. Of course, in machine learning, you have a Bayesian network, it's a much more complicated object. Here you have just an input-output channel. Just a new piece of information from 2 weeks ago. That's actually exactly the same path as the one using the bath. So we managed to prove that there is absolutely no difference between purifying, so the arbitrariness that is involved in purifying the system with a bath, inventing the dynamics and tracing the bath is exactly the same arbitrariness involved in choosing a reference prior. There's no difference whatsoever. That's a new result that I just announced. It's not in any of the papers, but well, it's not difficult to prove either. Okay, so now I have my reverse channel. That's what I set out to get. And well, let's apply this recipe to the erasure channel, this disastrous thing that destroys all information. Well, what you get is that the reverse channel is also an erasure channel, and it erases back to your reference prior. You may be a bit disappointed by saying, well, so that then what, right? Well, honestly, what else did you want, right? From the output of the forward channel, all the information on the input is lost. Now I ask you to retrodict back. What would you do? Well, you would say essentially, whatever you give me, I will stay with my reference prior because I have nothing better to do. I've got no information that allows me to update my reference prior. So, okay, you may say this is disappointing. Maybe you were hoping for more, but it's actually probably the only thing you can do, and it works. You know, it's logically consistent. Again, it may not be very exciting, but you know, an erasure channel is not very exciting either. But it is the logical way of constructing a reverse. And now you see, I'm able to construct a reverse for the most irreversible channel. It's not the inverse, because the channel is not invertible. The first time you hear these words are a bit confusing. So, well, maybe you have to listen back to my talk or to read the papers. But now take away the message that retrodiction is something you can do on every logical reasoning. If the logical reasoning is, I destroy all the information and I don't tell you anything, well, then your logical answer of retrodiction is, in this case, I stick with my opinion, because you didn't tell me anything that would help me change my opinion. Great. So at least everything is consistent. Quantum inside. Finally, I have some quantum formulas here. So what happens if this channel, inside these boxes, there is actually a quantum process? What is a quantum process? It's prepare a state, evolve through a completely positive map, and measure a P of M. And then, of course, that this means that the transition probabilities are given by this object. Then the reverse channel can also be done quantum. That's a kind of triviality. But there is a way to infer the reverse channel from the quantum formalism only. So without having to go through this calculation, there is an immediate translation of the objects Q, E hat, and sigma in terms of rho, E, and P. And what are these things? Well, you need a reference prior, as usual, and in particular, you need a reference state. And then you get these beautiful formulas here. Now, they may be a little bit scary for some of you, maybe not. I mean, for those who are accustomed to channels, these are normal things. For those who have never seen these things, like there are few too many square roots, maybe. But let me tell you what they do. I mean, essentially, this one is transforming a P of M into a state. So, you know, P of M's are normalized so that the sum of the elements is the identity. States are normalized such that the trace of the state is 1. And unless the P of M is projective measurement on a one-dimensional, I mean, with one-dimensional projectors, this is not going to be a state. So you need to transform it into a state somehow, and that's the way to do it. The same for the bottom line. The bottom line, you have a state that must be transformed into a P of M, the opposite. In between, there is this object that some of you might have recognized as the PETS recovery map with reference state gamma 0. Actually, the fact that the PETS recovery map is related to retrodiction was already noticed before this work by many people like Chris Fuchs, like Matthew Leifer, I presume Masaito Hayashi has found this. Everybody working in channels would have told you at some point that the PETS map is the quantum retrodiction. Here you see it appearing in a kind of very natural way as a inferred by the classical retrodiction of the channel. And still remember, you need a reference prior. And the reference prior plays a role in your PETS map. One thing I want to highlight is that this structure is valid for every state, every channel, every POVM. So what I'm going to tell you now about fluctuation theorems applies to every state, every channel, every POVM. If you find a paper that says that it's difficult to derive fluctuation theorems for non-unital channels or for states that have coherences or for POVMs that are not projective, well, this was because this paper was written before our work. With our work, we can define fluctuation theorems for every state, every channel, every POVM. The formulas are there. Okay, now I need to tell you something more about the reference prior, because as you see, this is a very crucial object. I hope you understood with the metaphor of sicknesses why we need it, but what is that thing? And I like to describe this in terms of a game. So imagine that prediction and retrodiction are a game. There is a predictor Alice and a retrodictor Bob. The referee, what they are given, right, as the rules of the game is the channel phi. That's the rule of the game that the referee gives to both. However, the game is not fair. To Alice, the referee gives the input X and asks Alice kindly to produce an output Y that is compatible with the channel. So Alice has a very easy task. She takes the input X, throws into the channel, gets an output Y. To Bob, the referee will give an output Y and ask him to retrodict the X. And now Bob is in trouble because what he knows, phi, is not enough to perform the retrodiction. He has to invent, before the game starts, he has to invent a reference prior in order to be able to write down his retrodiction channel. Okay? So you see that the game is unfair. Bob has something more to invent, whereas Alice can just play the game without anything else. Now, what are the real priors? We don't know. The referee may be sampling X with a prior P of X and Y with a prior Q of Y that have nothing to do with any other formula written on the board. Right? So I hope here, at least I try to convey to you, I know it's again one of these notions that you have to think a little bit more carefully, and maybe a talk is not the best environment for that. But I try to convey to you the fact that the reference prior is something that you need in advance in order to even retrodict, and may have nothing to do with what is actually happening. In this context of games, is rather clear. Maybe in a natural context, we can then make some assumptions that the reference prior should be a kind of reasonable prior and whatever not. But in the context of game, it's very clear that the reference prior is something that, well, you just need to invent. Okay, so then the forward process would be the prior of the referee times the forward channel, and the reverse process will be the prior of the referee times the reverse channel. And now with these two guys, I'm going to reconstruct for you the fluctuation relations, and with this I will finish my talk. Well, which reference prior to choose? Let me skip these because I'm maybe a bit late. Anyway, in statistical thermodynamics, people choose a steady state as a reference prior. We have found some game theoretical thing where it's better to use a uniform state. But okay, well, that is a technicality. Okay, so how do the fluctuation theorems look like? And in order to rewrite fluctuation theorems, I would need to tell you first that people are interested in statistical mechanics, statistical thermodynamics, sorry. People are interested in this quantity that is called entropy production, and is the ratio between the probability of going from X to Y in the forward process divided by the probability of going from Y to X in the reverse process. And then you take the logarithm of this ratio. Now, why is this entropy production? How can I prove that? there is something in the chat. I don't know if is why astrologers begin to pass points before they begin to predict. Well, I'm not an astrologer, but you know, well, whatever. We can discuss these things later. Okay, so why is this called entropy production? I see that I've left I left something from a previous presentation. There is no what I would call apodictic justification, or for those who don't understand that word, there's no general proof that this is entropy production. My example here, okay, I had an example with gender and smoking, but I can give the example of COVID-19 and the test, right? What is entropy production in the test of COVID-19, right? So these, I mean, I can define these to be entropy production, but it wouldn't follow from any physical principle. However, in statistical physics, it has been proved in many models with Langevin equations and on some specific thermal bath and other things, that this object very often behaves like entropy production. So, I mean, again, I'm not very good at justifying that because I don't think there is, again, a very general justification, but you can take it as a definition. Let's define this guy as entropy production. It has a very interesting advantage that if you take the average of the entropy production over the forward process, what is it? Is the, well, you take the variable and you multiply by the probability of the forward process. And what you get here is what is called the Kullback-Leibler distance, or the relative entropy between the forward and the reverse process. Why do I like that? Well, first of all, I like it because it's a measure of statistical comparison, right? So it seems that this is a kind of random variable whose average captures the statistical comparison between the forward and the reverse process. And besides, or between prediction and retrodiction of the same process, depending on the language. And of course, one very interesting property of this object is that it is strictly positive, or I mean, sorry, strictly non-negative. So if you interpret the average of entropy production as the macroscopic change of entropy, you've got the second law for free, right? By the mathematical expression of this guy, you get the second law for free. There is another funny property of this thing that I may not mention here. Anyway, so, okay. So keep in mind, just this kind of introduction, keep in mind that this kind of structure is of interest because it gives entropy, it's something related to entropy. And now, finally, I can prove to you Dzerzhinsky and Crookes equality. So consider a random variable that is written like that. The random variable of Z is the logarithm of two probability distributions. Here, I'm just purely formal. I don't think anymore of entropies, of processes, of inputs and outputs. It's just the two probability distributions, P1 of Z, P2 of Z. I take the ratio Z element-wise in Z. If one of the probabilities were to be 0, I kindly ask you to replace it by 10 to the minus 2000 and find the difference. So this definition has no singularity unless the strict singularity at P equals 0. As soon as you move epsilon away from it, this definition is perfectly valid. So as a physicist, I will just ignore that singular point and replace it by a very small number. So take this random variable. What is its distribution according to the distribution P1? Well, it's this, right? So I sample Z with probability P1, and I give the value omega of Z with that probability. And similarly, the probability according to distribution according to the probability P2 is this. This is the probability density of the value omega. And now, very simple. I multiply and divide by P1Z. I told you this is never 0, so I can do that. And what do I get here? Well, okay, these are, so far is a triviality. And here, because I define my omega like that, this ratio is nothing but exponential of minus omega. And because of the delta function, I can bring it out of the sum, and I get that this mu2 is exponential minus omega times mu1. And this is Dzerzhinsky equality. And if you want to get, Crookes, if you want to get Dzerzhinsky, You integrate over omega. On the left-hand side, you have a probability density, so the integral is 1. On the right-hand side, you have the average value of e to the minus omega with density mu1, so these. And these are really, I mean, these are the structures of Crookes and Dzerzhinsky. Mathematically, there's nothing else in those relations. And now, last slide, I will go very quickly there. So how do we get Dzerzhinsky and Crookes the physics? Well, you plug the physics into it. So what is the physics? The physics of these people are prepare a thermostate for a Hamiltonian at time 0. There's an evolution that is the Hamiltonian generates the evolution. By the way, the Hamiltonian can be time dependent. And also there are some exchanges with the bath with some assumption called microreversibility. I will tell you later what it is. And at the end, you post-select on a state that is thermal. The last equilibrium state you reach is thermal for the Hamiltonian at time t that might be different for the Hamiltonian at time 0. So let's see what it gives in my formula. So that's what I have to compute, right? The logarithm of that guy. Well, prepare a thermostate for H0 is very simple. You prepare a thermostate for H0. Prepare a thermostate for HT, yes, is also very simple. That's thermostate for HT. That's no discussion there. I think that is very easy. So I took care of the first term here. Now, microreversibility means that essentially you take what is called the detailed balance, or in other words, you take the steady state as the reference prior. And you can check that then this ratio, because of my Bayesian retrodiction, becomes this ratio. And now, the fact that is a change with the bath, what is the steady state? Well, the steady state is a state such that all the energy that I gain by the change of the Hamiltonian with time, I lose it in the bath. Or all the energy that I lose by changing the Hamiltonian in time, I gain it from the bath. So the steady state is related to the exchange of heat with the bath. Okay, plug everything in there, and you get that this ratio is the exponential of this. Remember, we have to take the logarithm in order to take the to find the entropy production. So look at the exponent here. What we have in the exponent, we have difference of energy, difference of heat, and difference of free energy. But difference of energy minus heat is work. So I've got my Dzerzhinsky equality, that these my Crookes relation, that this ratio is exponential of beta times work minus difference in free energy. Okay, so that's my way of deriving these things. You see that we have a very, very simple general mathematical structure, and then you throw the physics into it. And now, if you have a different physics, you want to prepare a different state, you want to use a different prior, you want to change the physics here, well, feel free. You just plug in your own formulas and you get a new fluctuation relation. Okay, finished. So let me pay tribute to Watanabe, who is the person who inspired this kind of research. In 1955, he wrote these beautiful reviews of modern physics where prediction and retrodiction, it says something like, he's considering the time reversal of quantum theory. He's not considered fluctuation relation in thermodynamics. And he says, in spite of this formal symmetry, it can be shown that the actual success of a retrodiction depends on the satisfaction of an additional condition, which is not required in prediction. This is my reference prior. In a later paper, he even says it better. It says, this is 1965. This paper, you can find it online. It is contended that the phenomenological one-wayness, okay, the fact that of temporal developments in physics is due to irretrodictability and not due to irreversibility. So this irretrodictability, the fact that retrodiction is harder than prediction, originates from a simple property of the very notion of conditional probability, independent of the structural dynamical theory. So it's the fact that to retrodict, you need a reference prior. Quantum physics is retrodict, whatever, irretrodictable, microscopic as well, macroscopic, whether it is invariant for T, TC, TCP, or whatever, or not invariant at all in any such sense. So in a sense, Watanabe is saying that the reason why we see irreversibility is not because there is some fundamental irreversibility in the dynamical laws, but because we need to postulate a reference prior in order to revert to invert the sense of time. Summary. The philosophy is something like we formulate physics based on our perceptions, and our perceptions, whatever they are, they tell us that there was a process going from X to Y. So in a sense, in our approach, the arrow of time is accepted without trying to derive it from further principles. We accept it as a bias of our knowledge. Then, if your knowledge is biased as to see an arrow of time from X to Y, if you try to describe the reverse process from Y to X, you face an element of arbitrariness, which is this reference prior that you need to postulate. And entropy captures exactly the statistical asymmetry due to this logical asymmetry. Well, of course, I mean, still philosophical problems, right? Why, if this is only knowledge and reference priors, why I cannot play soccer anymore? That's a big problem. But anyway, that's probably the right way to stop it. I just want to say that we may soon need a postdoc to work on these topics. So please let me know if someone is interested. And with this, I thank you for your attention.
Thank you, Valerio, for this wonderful talk. Now it's open for questions. Let me see if in chat box, okay.
Yeah, there is a question. Someone has raised the hand. Aravinda, maybe you can unmute yourself and just ask.
Yeah, Aravinda, you can
unmute. Yeah. Hi, it is a very fantastic talk. So I have one question. Does it mean the second law of thermodynamics or irreversibility means our failure to deterministically retrodict?
I think that, I mean, you see, the approach I have taken. Okay, first of all, I cannot pretend to have solved all the mystery of the second law of thermodynamics in any possible mean, right? But the approach I've taken is that, I'm taking an approach that physics is a human endeavor. So we describe physics. I mean, all our life is about irreversibility. We can influence the input. You cannot influence the output, right? You can choose the initial condition. You cannot choose the final condition. What does initial and final mean? Well, we have this perception of time, right? That is this perception fundamental or not? Is God seeing the things in that way or not? That's not my concern here, right? The question is, when we do physics, we have this thing. Now, in a lot of physics, maybe this relates to a question that was asked before, we actually retrodicting, right? If you try to, for instance, to speak about the Big Bang, well, we didn't see it, right? We see the effect of it. We see galaxies going apart from each other and so on. And we're trying to, okay, what happened before, right? We're trying to retrodict. So in archaeology, we are trying to retrodict, right? We find a skeleton of a dinosaur and we need to find out what happened to the dinosaur and what was that thing, right? So there's a lot of retrodiction going on in science. And my claim is that, well, even if you know the laws of physics forward, because you have been able to formulate them, to do this retrodiction is harder because you need to postulate something about the state at that time in general. Of course, if your channel is deterministic, then that's not the case. That's the only case where you don't need to do that. If your channel is deterministic, then you just follow the trajectory backward and you get back where you were, and that's fantastically okay. I don't know if I answered. I mean, to be honest, I also cannot claim again to have a fully, to go around and claim the full understanding of the second law, right? So
no, it is fantastic. It somehow brings an epistemic view about the thermodynamics.
Yes, definitely. So, yes.
So that was what I was guessing whether my understanding is correct or not. Your work, in some sense, bring temporal direction or the second law as an epistemic
absolutely yes.
Feature. So that's what I. Thank you.
You're welcome.
Any other question? Okay, so maybe can I ask one question?
Yes, please. I mean, as far as I'm concerned, yes.
Yeah, sure. Okay, so this is well, this is maybe not a question, maybe comment. So in the standard way of this going about the quantum Jarzynski equality or Crookes fluctuation theorem in the open system dynamics. So whatever people have done so far, mostly for the Markovian dynamics, like Lindblad like equation, and there are some bottlenecks for non-Markovian dynamics. So do you think that with this approach of retrodiction, one can also tackle the fluctuation theorem for?
Okay, so first of all, when you speak of Markovian dynamics, it already assumes that you are applying your channel a few times, right?
Yes,
Because
yes.
so the approach I presented is you enter a channel and you get out of the channel and nothing happened in between, right?
Yes.
So of course, Markovian makes sense only if you have multiple applications of the channel and then there is or there is not a memory in the bath, right?
Yes.
As it turns out, yeah, we are working on that. I mean, first of all, retrodiction must be possible in any physical process and any process whatsoever, right? So in particular for non-Markovian things. The question that would, so yes, the answer is yes, and actually we have the formulas. This will be in our future paper. Actually, you can find some formulas in the work of Crutchfield, and for classical works, you can do work of Crutchfield and Ellison and others on epsilon machines. You find retrodiction on these machines. And these are hidden Markov models, so you find some. So many of these things are actually known. Now, what is not entirely obvious is if you give me a non-Markovian channel, in the retrodiction channel, what do I see as remainders of the structure, right? So the general formula will be the same as I gave you. But now in this reverse channel, what features of the forward channel will I still see, right? Or will it be such a mess that I cannot recognize anything anymore? That's the interesting question, right? So otherwise, clearly retrodiction can be you just go through the motions and you try to retrodict. It can be complicated, but it's not so complicated. And yeah, you can do it for any form of reasoning. So if your bath has a memory, you need to take that into account, yes.
Yeah, so this problem of this reference state might be an issue, right? In the case of non-Markovian dynamics?
Yeah, so your reference state at the very beginning is not an issue. In between, yes, indeed, to update, that's exactly the problem, you're right. So to update the steps in between, you need now a reference state for both the system and the bath. You cannot have a reference state only for the system, otherwise you lose the memory, right?
Right.
So yes, I mean that's exactly the problem of structure that I was mentioning. So that when you try to do the retrodiction, yeah, there is a reverse channel. Certainly there is, but is it easily writable in terms of the forward channel or not? And our current understanding is in most cases not. I mean, if you look at this literature on the epsilon machines, you even have very strange things like you have that let's say an epsilon machine that in the forward direction has 2 or 3 causal states, in the backward direction has infinitely many causal states. So it's a much more complicated object, right? So it's really, yeah, again, so these rules can be applied consistently. You get something, whether that something is nice or not, that depends on the dynamics.
Okay. Thank you. Any other question?
Yeah, Shivashish, can I ask something very quickly?
Yeah, sure. Make it
clear. Very nice talk. So I would like to understand the definition of entropy that you just, in one of your slides, you put it in. And you said the physical origin, perhaps you had not much time to clarify what is the physical origin of this entropy. And this is sort of related to something else which I would like to ask. So in your approach, there is no fundamental, in the sense that the way I understand it, fundamental concept or microscopic origin of entropy. It is the problem, as you said, it is not irreversibility, but irretractability.
Yes.
Now, if you come back to your analogy for the universe that you have used several times in the talk,
yes.
Now it is known that if in a closed universe, we make the condition that it goes forward towards the Big Bang, then there is something called while entropy, which is different from what it was in the initial state. So it depends on how you define entropy. So do you have any comments on that?
Well, apart from the fact I'm not very familiar with cosmology in its details, right? But yeah, so first of all, one of the things I still have to study, so I have to admit my ignorance there, is whether the definition of entropy that I gave at some point is, let's call it general, at least for thermodynamics, or not. I have the impression it's not. I have the impression that there are processes in which that definition will not go through, in which case, whatever the construction is, will have to be revisited, right? So that definition of entropy is the one that is used in the literature on statistic fluctuation theorems, and we have somehow taken it up. I know it can be justified for many rather simple physical processes, but as I said, I don't have a proof that you just write down that thing and it's entropy correct for every physical process. Now, I have a slide that I didn't show that slide in this presentation, but if you work back the formula for entropy, if you work back from my Bayesian formulas, you find that the reference prior appears in the entropy. So I just throw it as a suggestion, but again, I'm not, maybe I'm completely off with respect to your question, but it is perfectly possible that two different notions of formulas for entropy come from the fact that people are choosing two different reference priors. And, I wouldn't be surprised if, at least again, abstractly, not being an expert of these, the initial condition around the Big Bang or around those times may not be something we are absolutely confident about. And if someone has maybe a different view of what that thing could be, well, it's not unthinkable that they get a different number for the entropy that was generated from then to now. That's all I can say, but I really want to also claim my ignorance in the field. So if anybody has more competent answers, please send me an email and inform me about these things.
Okay, thanks a lot. So it gives a lot of food for thought, a lot of things to think about for me after listening.
Thank you very much.
Thank you.
Okay, so maybe for the paucity of time, let us stop the discussion here. Let me thank the speaker once again.
Okay, thank you very much. I mute myself.
Yeah. So, Valerio, okay, fine. So our next speaker is Professor Runiao Duan, who is basically he's from this. He's the director of Baidu Quantum Computing Institute in China. So Runiao did his PhD in computer science from Tsinghua University, Beijing, in the year 2006. He was thereafter a professor and the founding director of Center for Quantum Software and Information at University of Technology, Sydney. And since 2018, he is the director of Baidu Quantum Computing Institute in China. So he has been in the steering committee for many QIPs and AQISs. His main research interests are quantum information, communication, and cryptography. So today he is going to talk about quantum adiabatic theorem revisited. Runia.
Oh, thank you very much. Just one moment. I need to share the screen. Oh, sorry. I need to log out first and then come in because the system asked me to do that. But it will be very soon.
Okay. No problem. No problem. Yeah.
Mm-hmm.
Runia, can you make it full screen?
Runia, your voice is not audible.
Hello?
How about now? Anyone can hear? If so, just maybe answer.
We can hear you, but we can't see your screen. Now you can see.
Now you can see my screen now because I already shared it.
Yeah, we can see the screen. Can you make it full screen?
Yeah. So how about now?
Yeah, it's okay. Okay.
Oh, thanks. Thanks for the nice introduction, and thanks a lot for inviting me to join this wonderful online conference. It's a great pleasure to join you. And today I want to talk about a work recently I have finished. It's I think it's maybe fit the topic of the conference better. It's about the quantum adiabatic theorem, and I want to introduce a new proof of it. Okay, and the paper already posted on Icqif 2 years ago. So I think if you're interested in detail, you can always go there for it. So here is the outline of my talk. First, I will introduce a little bit about the motivation and the related works. And then I will outline the new proof, but only first for a special case, and then I generalize it to the general case. As an application, I will also discuss adiabatic preparation of a qubit, use the new theorem. And of course, I also need to compare it with some previous work because this quantum adiabatic theorem is a well-known classical result, and there are already many results about it. So it will be very helpful to clarify the connections and the difference with previous works. Finally, I will outline an open problem and I hope. Okay, so that's the outline. And to introduce this maybe very technical part, I have to say that today's work will be very technical because this is exactly why I want to talk about it, because this quantum adiabatic theorem is I see many different versions. Most of them are very technical and the proof is very difficult. But I'm sure the one I provided here will be hopefully more accessible. But still, I think in some sense still a little bit technical. So before that, let's think about a very very simple scenario, and it's in some sense it's an imaginary scenario. So Of course, we always want to, climb up a mountain and very, enjoyably and at a normal heart rate. So without sweating or breath hard, and also we can spend a lot of time and energy and work slow enough. So this is something we are always dreaming of, because that's very enjoy the mountain view, but also at the same time not very tired. But of course, here the most cool thing is that we can actually keep at our normal heart rate, will achieve something highly not trivial. We can climb up a mountain, but without, still not heart beating, not. So, of course, in reality, such a scenario seems impossible, even for little hill. It's always a very difficult thing to do it. But interestingly, this imagination actually leads us to the quantum adiabatic theorem. This is my personal viewpoint, because we can understand this theorem as a mathematical formalism of the above imaginary scenario. Okay, so let's start from the Schrödinger equation, because quantum adiabatic theorem is some corollary of this Schrödinger equation. So solving Schrödinger equation is a key challenge since the establishment of this quantum mechanics. So here is the equation. We take the partial derivative of this the wave vector psi t, and it's always equal to this the Hamiltonian times the vector. And here we have this Planck constant h bar normalized h bar, and but in the rest of this paper, I think we always assume it's just a unit. Okay, so just a unit, just one. Okay, and I is the unit, the imaginary unit, square root of -1. Okay, so this equation is actually only solvable for some special Hamiltonians. For example, very low dimensional and or maybe time independent. So in that case, it's just take an exponential of a matrix h hat, and also for a special case like quantum harmonic oscillators. Okay. However, it's actually it's very important. Even in some sense, even we cannot solve the equation, we still want to understand the behavior of the solution. We want to understand the behavior of the state of the quantum system. Okay, this is actually more practical problem in some sense. So the observation here, of course, this is also very almost very simple, but of course not trivial observation. For time-independent Hamiltonian H, if the initial state is an eigenstate of H, then even with this unitary evolution, the final state is always keep at the same state, because it's an eigenstate. So every time you apply this Hamiltonian, it's just it's just keep the same eigenvector. Okay, so this is a very simple observation. But the interesting thing is that this quantum adiabatic theorem, in some sense, is just a far-reach generalization of this observation, but for the case of time-dependent Hamiltonian. So even for time dependent Hamiltonian, we can see similar thing. If we can keep if the initial state is at the eigenstate of H0, the final state will be very close to the eigenstate of Ht under some the
Hello.
হ্যাঁ শিবাশিস, তুমি ওনাকে
yes.
ওনার ভিডিওটা অফ করতে বলো, তাহলে মনে হয় একটু বেটার কিছু হবে।
Okay. Runia, maybe you can switch off your video because maybe there is some issue with the internet connection. Can you hear me?
শিবাশিস,
হ্যাঁ।
তুমি ওনাকে ওনার ভিডিওটা অফ করতে বলো, তাহলে মনে হয় একটু বেটার কিছু হবে।
Switch off your video because there is some issue with the
আর চ্যাট বক্সে লিখে দাও, চ্যাট বক্সে লিখে দাও যে প্লিজ সুইচ অফ ইউর ভিডিও।
Hello.
Yeah.
Can you hear me?
Yes. Yes.
I think you should switch off your video because there is some issue with the internet connection. Perhaps.
Oh yes, I already switched off. So how about
okay.
now?
Now we can hear you, but we can't see your screen.
Oh, so I need to share again. But so where I should start, because I think just now you people maybe missed some part, right?
So there is this, your thing is Schrodinger equation and quantum adiabatic theorem.
So have you already heard about the quantum adiabatic connection with quantum computing? No, not yet, right?
Not yet, not yet. So what basically you were talking about this, Schrodinger equation and quantum adiabatic theorem. In the end, you were talking about the point number 3.
Okay, so maybe I just start from the ball and the fork. Okay. Okay.
Okay.
So the ball and the fork, they introduced this adiabatic theorem in 1928. Okay, and then people already have new proofs of this adiabatic theorem, like Cato and also other people. They have discussed the adiabatic theorem and its application to quantum Hall effect. Okay, so for people from the quantum computing community, the most interesting is that we find that the quantum adiabatic theorem also have the application in this exciting field. So by Adi Fahy and Goldstone, Gutman and Simpson in 2000, they introduced a new computing mode called by quantum computing computation by adiabatic evolution. And then later, Aharonov and other people that proved that in 2004, this adiabatic quantum computing is actually equivalent to the standard quantum computation. So that actually that triggers a lot of research interest for people from quantum computing because this adiabatic quantum computing seems a very natural physical model for computation. All you need to do is you prepare some initial state, and then you set up the final state as the solution, And all you need to do is you just evolve the Hamiltonian from the initial to the to the final, and then the ground state maybe of the final Hamiltonian will be your answer. Okay, so it seems very very promising model for quantum computing. Okay, and this field is very have they grow exponentially, and actually 2018 there's Orbash and NIDA, they already have a review paper about this adiabatic quantum computing. And later, Fahey, Goldstone, and Gottman, they introduced a model called quantum approximate optimization algorithm, or widely known as QAOA, for based on this quantum adiabatic computing. But it's more, it's like more trackable way for this near-term quantum computers. Okay, and maybe Fahey and Harrow, they also discuss how we can achieve the quantum supremacy through the quantum approximate optimization algorithm. And Prask also, discussed about the quantum computing in the Icqif area and beyond. And clearly, this quantum, this QAOA and maybe adiabatic quantum computing is a very good candidate for this Icqif computing area. Okay, but this quantum adiabatic theorem is because it's a very very intuitive physical how to say it's very intuitive physically because if you stay at the ground state and then if you evolve very slowly, and then you can always keep at this near this ground state of the Hamiltonian at that time. So there are many descriptions of this theorem, but people argue there may be some inconsistency. Because why? Because, for example, there are at least several papers, they have the proof for this adiabatic theorem, but also they talk about the inconsistency because so it's only I think the Ambenius and Regev, they in 2004 they actually have a very nice paper. They give an elementary proof of this quantum adiabatic theorem, and this proof is of course it's not an optimal one because there are many different forms of this theorem. But the one they give is very elementary. Only use some basic matrix inequalities and some norm properties. And from this proof, we can actually see why this, how this adiabatic condition could be formulated into a very, rigorous mathematical form. Okay, so to be honest, I completely understand this theorem until I read, the Ambenius and Regev's paper. So this is a very interesting paper. Of course, there are also many other research on this theorem even after the in very recent years. Okay, so because this work, this paper is actually highly motivated by the work of this Ambenius and Regev. So I want to quote cited from their paper. Indeed, the elementary proof given by Ambenius and Regev is not just cleared several confusing issues regarding the validity of this quantum adiabatic evolution, but also yielded a new insight why this adiabatic theorem works. So for example, they say essentially the proof shows that the error means the actual state
শিবা আবার গন্ডগোল হয়েছে, কথা শোনা যাচ্ছে না। শিবা,
বুঝতে পারছি, কি করবো বলো তো?
কিছু করার নেই, ও কোনো ইন্টারনেট প্রবলেম তো আর তোর আমার হাতের নেই তো। হ্যাঁ,
একবার চ্যাট বক্সে লিখে দিতে পারো।
আমি লিখে দিয়েছি, চেক করছো।
বলছি শিবাশিস, ওকে ফোনে রিকোয়েস্ট করা যায় না? বলতে ফোনে
ফোনে
হোয়াটসঅ্যাপটা কি নিয়ে রেখেছিলে? যদি হোয়াটসঅ্যাপ নিয়ে রেখেছিলে তাহলে ফোনে দিতে পারো।
হ্যাঁ, তাহলে বলতে হতো এটা পড়ে কিন্তু ওটাকে তো করতে হবে, চেঞ্জ করতে হবে, নাহলে তো হবে না।
এসে গেছে আবার এসে গেছে।
Hello.
Hello.
Hello. Can you hear me now? It's very
Yeah, we
strange.
can hear you now. Yeah.
Okay, so I talk about the work by Ambenius and Regal. Is that the part that people hear?
Yes,
okay.
yes. Actually, you are in the end of this slide. Yes, almost end.
Okay, good. So yeah, do let me know if I'm not audible, because I don't have any feedback otherwise. Okay, thank you. Okay, so now we can have, we can actually come to the description of this theorem. Okay, so we associate Hermitian operators like HT over capital T, and T is from this 0 to capital T with a quantum system as its Hamiltonian. So, and then we drive the system from H0 to H1. Actually, it's means from time 0 to 1, okay, 0 to T. So the initial state of the system is prepared at the ground state of the initial Hamiltonian H0. And if we drive the system according to Hamiltonian HT, and eventually after time T, we will reach a system state. So the theorem is say that the system state at time T will be kept close to the ground state of H capital T if we drive the system sufficiently slow and if T is low enough. Okay, so the challenge task is to formulate such an intuition into a mathematical statement. So in order to do that, I need a little bit notations. It's a very ordinary notation, but just to make sure everyone with me, so I listed it here. So first we need an operator norm of a linear operator. So this is actually the largest singular value, okay? And for a family of linear operator, we can do the same. So all we do is we just take the maximum of the norm of the operators in this family. So we can take the norm for H and the norm for the first derivative of H and the second derivative. Okay, all this do it. And another concept I need is we know that because this HS is a Hamiltonian, okay, Hermitian operator. So we assume that we can have the case eigenvalue because we can sort all the eigenvalues, from the gamma 1, gamma 2, and to maybe gamma D into dimension. So and then we have this eigenvalue equation. We assume this phi ks is the case non-degenerate eigenvalues. So here we assume this the case eigenvalue is not degenerate. Okay, so that means there is only a essentially there is just one single eigenvector have this eigenvalue. Okay, so once we have this, we can define this spectral gap between around this case eigenvalue. So essentially, we assume these eigenvalues are sorted in this non-decreasing order, and then we can have this lambda s is just the minimum between this gamma k minus gamma and gamma s minus gamma k minus 1. So here gamma is just the gamma k, okay, because we assume we are focused on this the case eigenvalue. So all we need to do is we just omit this subscript. Okay. Okay. Oh, let me. Okay. Oh. Okay, so with this notation, we know that if the system is initially prepared at this okay. Oh. Okay, so if the system is initially prepared at the eigenstate of H0, the final state will be close to the eigenstate of H1, providing that the evolution is sufficiently smooth in terms of the norms of the first and the second derivative of the Hamiltonian, and the energy gap is strictly positive, and the evolution time t is low enough. So indeed, what we do is we will do this. We will show that t is actually polynomial of this the inverse of epsilon. This is the error threshold, and the inverse of this this spectral gap, and also the norm of this first derivative, and also the norm of the second derivative. Okay, they are related polynomial. Okay, so eventually let's we come to this description of this this quantum mathematical theorem. So, but there is a very important trick. I just follow from Ambanius and Regave's work. We consider the special case that's the eigenvalue is 0. Okay, we assume this eigenvalue is 0, and then what we do is we prove the theorem for this special case, and then we reduce the general case to this special case. Okay. So the idea is assume this phi s is a unit eigenvector of Hs with eigenvalue 0, and here we have an additional assumption. We assume the derivative of this phi s is orthogonal to itself. This is just also by a very simple choose of the phase factor before phi s, because we have the freedom to choose the phase factor before the eigenstate. Okay, so we can make this condition happen. Okay, so suppose the initial state psi 0 of the system is just phi 0, then we drive the system through the Hamiltonian h t over capital T from t0 to t. Then for any epsilon, the final state of system psi 1, okay, is at most. So I have to say, psi 1 just means the solution of this Schrödinger equation at time t is almost epsilon, far from phi t in the order vector norm. So that means that the norm is less than epsilon if we choose the t is in this way. Okay, so that means t should be the inverse of this the inverse error threshold epsilon 1, epsilon, and the spectral gap, and the norm of the derivatives, they are in a polynomial way. Okay, this is a qualitative characterization of the tuition of this adiabatic evolution. Okay, so here, I mean, because this is the condition of this gamma s actually can be reneged to gamma s equal to constant for this case, for this special case, because we don't need this 0 condition directly. We can just use the constant condition. We can also do the same. We will have an example. So any question here about this part about the description of this special case? Because now we will go to the details of the proof. Because the proof, you can see it looks technical, but essentially it have just 3 techniques, very very interesting 3 techniques, and then we can finish the proof. Okay, so let's just go straight forward to the proof. Okay, any question can I ask maybe after that? So the first trick we use is we use this Dyson operator. So it's U S2 S1. So it means the unitary evolution from time S1t to time S2t. Okay. So because here we always assume the total evolution time is capital T. So we use this fractional number S1 S2 to represent the time, at different moment. So this operator is very interesting, have not a very interesting property. For example, if this S are same, then it's just additive because they are the evolution like just do a trivial one. And also the U1S is the evolution from the ST to T. So because 1 means the actually final state, final time T, and the ST is just use the S to represent. And the US1 S2 is just equal to US1 S2 S times US S1. So for any S between S1 and S2, okay? So that means it has this multiplicative property. This is also very reasonable, right? Because the unitary evolution from S1 to S, and then S to S2 is the same as the total evolution from S1 to S2, okay? So the interesting property we need is the derivative of this U1S. Okay, so this is in some sense is another way to reformulate this Schrödinger equation in terms of Dyson operator. I'm sure that people in this maybe theoretical physics or maybe some other very physics-based field, this is maybe something well known, right? But here I find it interesting, so I listed it here. So this du1s is just equal to it times u1s times hs and ds. Okay, so it's a very nice way to express this the derivative of this u1s use u itself and also the Hamiltonian hs. But the additional effect factor it is very important because it's actually connect the total evolution time t and also the unitary and the Hamiltonian. So this is why it's very useful later. And the second is I think this is the key result or a key finding of this of my paper. So we have a very nice integral representation of the difference between the eigenstate phi1 and the actual state psi1. So you see because the phi1 is the eigenstate and the psi1 is the actual system state after the evolution. So what we find is the difference between them can be described by this very nice integral representation. So all you need to do is you apply u to this the first derivative of this phi s, okay, and then you take the integration, okay. So it's in some sense it means the error between this the error during this adiabatic evolution is simply just accumulated at a different moment like s, and at each moment in a short time ds we have this u1s phi prime s times ds error, and then we need to accumulate all of them, and then by taking the integration, this gives us the total error, okay, during this adiabatic evolution. So this is in some sense I think this is a very key representation we need later. Okay, so once we have this a and b, what we do is we carefully manipulate this integral representation, and then we create a factor of 1 over t, because we need to connect the error with the evolution time t, right? So if we could create a factor of this 1 over t, then in some sense there is a hope to get some quantitative connection between the time and the error. Okay, so this is some key proof techniques we will need. So the first one I think is very just by some basic algebra. So by the definition, this the derivative is simply just you take a very small time period and then you take the difference, and this time difference can can be, we can insert some, some another interval s plus ds, and then we can take the common factor out, right? And then you now apply this Schrödinger equation to the period of this small period. Then we have this the u, the Dyson operator in this small period is simply by take an exponential of this small Hamiltonian, and then we sorry, at the evolution is given by the Hamiltonian at that time evolve a small time TDS. Okay, so this is simply by Schrödinger equation. Okay, so we have this take the first order approximation. We have this I minus ITDS HS and a high order term. So all we need to do is we just substitute this formula into the above one, and we omit the high order term. This gives us this formula. The du is equal to this, as we claimed before. Okay, so easy. So I think it's a little bit challenge to prove this B. It's not very difficult, but it's just like, actually the difficult part to find this is we need to know the formula. Proving is not that difficult. So what we do is we consider the vector u1s applied to phi s. So what does that mean? That means if we assume the system at time st, okay, is phi s, then we apply the the evolution generated by the original Hamiltonian. That is u1s. So what we will have? So it's very interesting. Okay, we can have this because you can see that if we choose the s equal to 1, it's equal to 1. So that means nothing, right? Because u11 is just the trivial operator I. So this phi 1, both sides of phi 1, they are equal. But the interesting thing is if you choose it as 0, as equal to 0, then what we do is we apply the u10 to this psi 0. But psi 0 is the initial state, right? So we assume the system initially is prepared at phi 0. So psi 0 is equal to phi 0. So we know that it's equal to u10 applied to phi 0. So you can see here, the formula is like s equal to 1. And here the formula is x equal to 0. So this reminds us we can apply the fundamental theorem of calculus. So we can have phi 1 minus psi 1 equal to the u1s phi s just at the 2 points 1, 0. And then we can rewrite this, take this inside, okay, inside this integral psi. And all we do is we use the production rule, okay, production rule that for this derivative, and then we can have this 2 term. Okay, so the interesting thing here is the first term, only the first term is what we need, right? You see, you compare with the original form. So expected form, we know the first term is the same, but the second term we have this u1s times d phi s. D phi s, we know that this oh, sorry. Only here is a typo. Okay, only the second form is now vanishing. The first term is actually vanishing because we use the formula of this duys, and then we can have this. It's just use the hs times d phi s. But we assume that this because phi s is the eigenvector of this hs, so this term is essentially gamma s times phi s, which is 0. Okay, so we have this formula. The first one is by the Dyson operator property A. The second one is just the assumption of this 0 eigenvalue. Okay, so the proofs, the part C is the most technical part, but it's also we need to introduce a little bit notation for this. So we do is we have this the eigen.
Hello?
of SHS over this subspace. Okay, so we have this RS is equal to R dagger, and HS times RS is QS because they are in this the inverse in this subspace. So they, of course, if we multiply them together, what we have is we should have the identity of this space. So that means the projection QS, and RS is equal to QS times RS as well, because it's just lying in this subspace. Okay, subspace of Q. So here, of course, we also need to remind this we have this the orthogonal collection. So the first derivative is orthogonal to the vector itself, and the QS because phi s is in the orthogonal complement of phi s, and then if we apply the projection of this subspace, of course, they apply to this phi prime. It's invariant, okay, because phi 1 is lying in this subspace. So we can okay.
Sorry.
Okay, so can you hear me now?
Yeah, we can hear you. We can hear you.
Okay, that's good. So thank you very much. Yeah.
Runia, how much time will you take?
Oh, it's fine. It's because I wasted some time, So
Sure,
maybe
yeah.
Yeah, if possible, maybe I can take. So how much I have if original
Well,
plan?
actually, you don't have almost. You have almost 1 or 2 minutes, So.
Maybe can I have maybe another 10 minutes?
Another 10 minutes. Yeah. Okay, you can try to finish.
Okay, I try to finish this part. Okay, and the other part I just maybe escape. Okay.
Sure. Okay.
Okay, thank you very much. Okay, so once we have all this ready, so what we do is we just insert this HSQ in the formula we have between phi 1 and psi 1. So what we do is we insert HR in before phi 1 and phi prime, and then what we have, we combine the first few terms together, and we take out the factor IT. Then we can have this formula like DUSRS, and what we do is we apply this integration by part. Okay, so from the previous proof we already have this formula. So now what we do is we apply the integration by part. We can have this two term, and for each term we do the evaluation. Okay, we do an evaluation and use the invariant of this norm for unitary, and then we can have the phi 1 minus psi 1 is actually less than this formula. Okay, T over some constant. So that means that the error is actually of order inverse T. So the rest part is just to estimate the constant CH. So for upper bound, I mean, it's what we do is we need 3 important norm equation. So it's listed here is R times phi prime, and is less than this the H prime norm over R nominal square. Similar, we have another 2. But this part I think it's quite technical, but routine. So I don't spend all the time here to do it. So all we need to do is once we have these 3 inequalities, the details maybe you can find in paper. Okay, and then what we do is we have eventually we have this nice formula, and then we have the T. Okay. So my original plan is to spend some time to prove this 3 equalities, but now I decided because I don't have much time. So what we do, I just quickly go through it. Okay. So all we need to do is to give the estimation on. We use the formula by Ambanis and Regal, and with some additional techniques, we can actually show this formula. but because it's too technical and we don't have time, so we omit this part. Okay. So let me quickly mention a little bit about the reduction of the general case. So all we need to do is we create a new family of Hermitian operators, H hat. And the H hat is just use HS minus gamma S times the identity. So then this new H hat satisfies the condition of the theorem one, and then we can use this to obtain the estimation. Okay. So, but we still need to find the connection between the norms between this H hat and H. But this is not very difficult and very routine, so I omit it. Okay. So the general case is similar. We can eventually for any gamma and not zero, we can still have the result. Okay. So the here is also a connection between the adiabatic computation and the QAOA. But I think that this part I omit. Okay. I want to quickly go to adiabatic preparation of a qubit. So qubit preparation means we want to use the adiabatic preparation, adiabatic evolution to prepare a qubit. So from cat 0, okay, maybe from cat 0 to psi. And all we need to do is we can design some road path from the this block sphere. We can rotate cat 0 to psi. So we have two ways to do it, right? We first have this. The first way is we have the Hamiltonian just by the combination of this sigma z and also an error times sigma. Then we can calculate the eigenvalue and get the the evolution time t. But another way.
Hello. Hello. Runio, can you hear me?
শিবা, তোর কথা শুনতে পাচ্ছি, তুই ওকে বলে এবার স্টপ করে দে, মনে হয় সেটাই বেটার।
আচ্ছা আচ্ছা, আমি তো ওর কথা, তোমরা কি শুনতে পাচ্ছ ওর কথা?
না তোর কথা শুনতে পাচ্ছি, ওর কথা কেউই শুনতে পাচ্ছে না, তুই ওকে বলে দে ইংরাজিতে।
I can hear you all. Yeah.
Runia, can you hear me?
Yes. Yes.
Yeah. So we can't. So we are not able to hear you.
Okay. Okay.
So maybe may I request you to go to the conclusion? Because we have to start the next session also at for 16:20. Sorry for this. Really.
Okay.
Sorry.
Okay. So maybe my conclusion. Okay.
Yeah,
Our conclusion. Yeah. Okay. So yes. Okay. So yeah, I'm okay now.
Yeah. Okay. Yeah. You are audible.
You can hear now.
Yeah, we can hear you. Yes.
Yeah. So this this the last page. Okay. So I'm not sure how much you missed, but in any case, you can find the paper on internet. Okay.
Oh, I see.
Yeah.
Are you done?
Yeah. I'm okay. I can stop
Okay,
now.
so,
Yeah. Thank you. Thank you very much.
Yeah, thank you, Runia. I mean, we are extremely sorry for for this for not being able to hear you properly.
Okay.
So in next near future, we'll have you here. So definitely, this paper is available in the archive. So people who are interested can look into it. So because we are running short of time, so maybe if people have question, can put in the chat box addressing to Runia, or can write to Runia. Okay. Thank you again.
Okay. Thank you. Bye.
Bye. So
Thank you.
yeah, you can unshare your screen.
Yeah, I will. Yeah. Okay. Good.
Sorry for this.
Oh, no problem. Bye.
Bye. Okay, so our next speaker is Professor Indranil Chakraborty from IIIT Hyderabad. So Indranil will talk about quantum conditional entropy, a resource. So Indranil did his PhD from Bengal Engineering and Science University, Shibpur, Howrah. He is currently an associate professor in the IIIT Hyderabad in India. His area of research interest is to study quantum information, relativistic as well as non-relativistic, Fisher information, and so on. So Indranil, you can start.
Thank you, Shivashish. Am I audible?
Yeah, you are audible.
Yeah, so let me share the screen. If the screen is audible, visible or not, please let me know.
Yes, it is visible. Yes, it is visible.
Okay. So thank you once again to the chair Shivashish for giving this kind introduction, and also thanks to the organizers for inviting me. It has been a wonderful conference, and I had been witnessing this conference for the last couple of days, and there are several interesting talks. As Shivashish mentioned, the title of my talk is quantum conditional entropy, a resource. So this is based on two papers that we had done. With one was published in Physical Review in 2017, another is in Physical Review in 2021. So based on these two papers, today's talk, I will talk about the work that we had done in these two papers. So this work is mostly done with my students and my collaborators. Professor Arun Pati was one of the collaborator, and Dr. Nirman Ganguly from BITS Hyderabad is also another collaborator. And there are students who are involved in this project. I will mention them at the end of the talk. So, the outline of the talk is like this. So I have one or two slides which are pedagogical slides, like information, telling what is information. I can skip through them quickly, and what is conditional von Neumann entropy. Then I will try to give 2 or 3 applications of conditional von Neumann entropy in quantum information theory, and based on these applications, we will come to the motivation of our work, and we will try to characterize the states with negative conditional von Neumann entropy. And what is the purpose of characterizing the states experimentally and creating the witness operator for these states which are having negative conditional entropy, that we will discuss. We will also talk about how to construct a witness operator for those states which are having negative conditional entropy. And in the second part of my talk, I will also talk about a class of states which is called absolute conditional von Neumann entropy non-negative class. Means this class of states are those class of states which will remain non-negative, whose conditional von Neumann entropy will remain non-negative even after the application of the global unitary operator. So I will try to characterize this class and try to see what are the necessary and sufficient conditions for a bipartite state to belong to this particular class. And now, along with the characterization, I will also try to motivate why we should study this class and why should we study the states which are lying in the fringes, and how to witness the states which are there in the fringes. So we will talk about that. And finally, I will also talk about the absolute separability and absolute conditional von Neumann entropy, non-negative ACVNN class and absolute local class. So all and the relation between these classes of states. So so there are different ways to understand information. One simplistic example to understand information is that consider 2 systems, A and B, and if A starts maybe the system A is me and the system B who are listening to this talk, and and there is a lot of uncertainty in within the system A and the system B how the talk is going to happen, and this uncertainty.
Sorry to disturb. Can you just close that hide so that we cannot see the bottom? Yeah, thanks.
Okay, now is it fine?
Yes.
Oh, thank you for mentioning. So system A, maybe the system A is like me and system B is like who are hearing this talk. So once there is a lot of, as I am telling you, there is a lot of uncertainty in both these systems about how the talk is going to happen. So once we start interacting, there is a flow of information that happens from the system A to B or from B to A. As a result of this interaction, there is a reduction of uncertainty. This is one way of understanding information, and we know how to characterize information in the classical scenario. Given a random variable x with possible outcomes x1, x2, xn, and each of these outcomes occurring with probabilities pi. Then we write down the entropy of the system as given by the Shannon entropy, which is minus pi log p. These are very much well known to all of us. So I'm not giving much time to this. So when we move on to the density matrix scenario in the quantum scenario, this entropy gets replaced by the von Neumann entropy. So and von Neumann entropy is given by S rho of minus trace of rho log rho, where rho is the set of all density matrices, mixed states. We bring in the concept of mixed states and the pure states in quantum information theory and quantum mechanics. So in a sense, von Neumann entropy measures the minimum classical uncertainty that is there in the mixed states. And operationally, if we think, it denotes the minimum number of qubits that part symbol required to transmit information from a quantum source, which is described by this density matrix. Now, coming to the conditional entropy, I tried to motivate, give an example how we can understand conditional entropy, and then we'll move on to the quantum scenario. So, for example, if you take a very one example where there is Alice and Bob. Bob invites Alice for the dinner, and Alice was not sure whether she will be able to go or not. So this event of coming to Bob's house for dinner, if you call it as X, so there is a lot of uncertainty of h of x, that whether Alice will come or not. So Bob is uncertain. So Bob is not sure whether Alice will come or not. Now, what happens when Alice on the way, Alice car got, there is a tire puncture in Alice's car. So, and this event was observed by C, and C was going to Bob's house, and C reports this event to Bob, and and if you call this event as Y. this event is reported by C as Y. So now Bob is unhappy that whether Alice will come, that Alice is more likely not to come, right? So there is more uncertainty. However, the uncertainty in Bob's mind got reduced because of this event reported by the this third party C, and there is a reduction of uncertainty. So if we call that event as Y, h of x/y is given by h of xy minus h of xy minus h of y. So, and we can easily see that in the classical, this is the total information of this total event, two variables x and y, and h of this is h of y. So the classical conditional entropy is always a positive quantity. However, this is not the scenario when we go to the quantum case. So these are basic things, like if you have a density matrix rho AB, so the quantum conditional entropy will be given by S of rho AB minus S of rho B, where if we denote here S of H as the set of all density matrices, and we take a particular example to show that quantum conditional entropy can be negative. So one example may be the very simple example of a maximally entangled state 1 by root 2 0 0 plus 1 1. So since it is a pure state, S of rho AB will be 0 here, and S of and if you trace out one qubit from here, you will get an identity matrix. So an S of rho B in this case will be 1. So, and you will find that the conditional entropy S of S/B in this case for rho AB is -1. So in fact, there are a set of states which possess negative conditional entropies, and there are set of states which have zero conditional entropies, and there are set of states which have positive conditional entropies, right? So so this particular set of state, we are calling it as FVH. Now, as I am telling you, that three possible cases can arise. And the interesting part is that though the negativity of conditional entropy indicates the signature of entanglement, but the converse is not true. As if the state is a negative conditional entropy, we can say that it is an entangled state, but there are entangled states with non-negative conditional entropies. So it is not so if you want to see something as a resource, it is and if in that resource the negative conditional entropy plays a crucial role, it is not equivalent of saying that if I can identify the entangled state, that we are done. No. So we need to know states with negative conditional entropies. Simply merely becoming an entanglement cannot be told as a resource for that particular task. See, based on task. So for example, one of the tasks that we can, I will talk about two tasks because there is lack of time. So one is the state merging. So in the state merging is considered a scenario when there are two parties, Alice and Bob, where Bob has some prior information B, and Alice is having some missing information A. Now, if Bob wants to learn about this missing information, wants to know how much additional learn about A, so now the question is how much additional information Alice needs to send to Bob. So, and it turns out that this S of S/B, the conditional entropy will suffice. Now, what is now that, as you know, if Alice and Bob share a 2-qubit entangled state, and if we find out of S of S/B of this 2-qubit entangled state, that or 2 qubits, not necessarily has to be an entangled state, 2-qubit state between Alice and Bob, the conditional entropy can be either positive, 0, or negative. So if it's positive, it simply tells you that whatever it tells you that Alice needs to send this amount of information to the receiver Bob. If it is 0, there is no need of sending this information. Bob knows everything about it. No need of further communication. But if there is a very famous paper by Winter which tells about negative information and state merging. So if S of A/B is less than 0, then the sender, so it is what does it signify? It signifies not only there is no need of sending information, but there is this state can be used as some potential resource for future communication. Similarly, you can take another task. You can take another task like super dense coding. Most of you know how it is super dense coding and how with the help of a quantum resource we can send classical information. The capacity of the super dense coding is given by this quantity log2d, maximum of log2d plus s of rho b minus s of rho a b. Now the what we can achieve classically maximum is log2d for if this quantity s of rho b minus s of rho slash rho ab is positive, then only this expression becomes more than log2d, and then only what we can gain, we can say we can have a quantum advantage, and we can achieve more than what we can achieve classically. So it is important for a state rho ab which can be used for a super dense coding purpose or not. It is important to check whether this quantity is coming out to be positive or not, right? So what is so what does it mean this quantity to be positive? What does it mean to be this quantity to be positive? This quantity to be positive, it means that this expression, the conditional, this expression is nothing but the negative of the conditional entropy. So in other words, we require states with negative conditional entropies to act as a resource for the tasks like super dense coding. Similarly, we can see also in case of coherent information, if you see that a lower bound of the quantum capacity of sending quantum information is given by this negative of the conditional entropy. So if this is positive, then this quantity is positive. So we will be also, there are many other tasks where we require like this, we require the states with negative conditional entropy. So I just mentioned 3 tasks over here, and now we take this opportunity to motivate why we should look out for those states and what we have done in this particular work. So the motivation of our work. So suppose we are thinking about a situation where we are looking out resources which will help in actually realizing a task like super dense coding. Now the answer to this question, is the entangled state will be sufficient? The answer to this question is no. As there is twist here, and we need states with negative conditional entropy. Now given a state in a lab, how will you determine that the state is a negative conditional entropy? So what we will try to do, we try to develop methods to construct operators which can witness negative conditional entropy states in RB belonging to arbitrary dimension. For example, if we can create a witness operator, when we take the trace of this witness operator with these particular states, it will come out to be negative, and we will be able to tell the states whether the states which is having negative conditional entropy or not. But before the construction of the witness operator, it is very much important for us. It is very much important for us to at first to see whether there exists a witness for this kind of states or not. Means I want to witness a state with negative conditional entropy, but is there a first we need to know whether there is some existence of this particular witness or not. So to know this particular existence of this particular witness, we need to check that if you take all the state conditional von Neumann entropy states, non-negative conditional von Neumann entropy state, and we try to see whether it is convex or compact. If we can prove that whether it is convex and compact, then we, by Hahn-Banach theorem, we can say there will be an hyperplane which will separate out this particular set from a state which is having a negative conditional entropy. Right. So our first motivation will be to see whether the set is convex or compact or not. Right. So this FBH is the set with non-negative conditional entropies. So let us take two to show the convexity. It is very easy to see whether this set is convex. Let us take 2 states, sigma 1, sigma 2 from this set, and check whether since these are belonging to this class, they are all having non-negative conditional entropy. So S of A slash B sigma 1, S of A slash B sigma 2 is greater than or equal to 0. Now if you take a convex combination of this state, sigma lambda sigma 1 plus 1 minus lambda sigma 2, then if you take S of A slash b sigma, from the concavity of the conditional entropy, you can tell lambda of this will be greater than lambda of s of ab sigma 1 plus 1 minus of lambda s of ab sigma 2. So now each of these quantities is greater than equal to 0. So the s of a slash b sigma is greater than equal to 0. This indirectly this tells you that sigma is actually belonging to this FBH. So we take a convex combination of any two states and we see that that is also lying in the any two states belonging to the CVNN states, and that is also lying in the AVH or the CVNN class. Right. Now, to prove that it is compact, we need to show that this is closed as well as bounded. The bounded thing will come very automatically, but to show that it is a closed, we will see how we can show that this is a closed. So suppose we take this sigma AB belonging to FBH. And we know that sigma s of a plus sigma AB is always greater than 0. The value 0 will be attained by which type of states? Which are pure states. For example, pure separable state, this value is going to be pure separable state, this value is going to be 0. S of a slash b 0. So for now you use again the subadditivity of the conditional entropy. So for example, and you can see that s of sigma AB can always be is less than equal to s of sigma A plus s of sigma B. So now if you take s of sigma B on the left hand side, we will see that this quantity becomes the conditional entropy of sigma AB, s of a slash b sigma AB, which is bounded by sigma A, and which is always less than equal to log 2d. And this particular value log 2d is attained by which particular states? I by d square state. So we can see if we take this s of a slash b as a function from the set of non-negative conditional entropies, the image set that is we are getting 0 to log 2d, this image state is a closed set. And it was proved that the s of a slash b is a continuous function under trace norm. This was referenced by the Winter's paper that s of a slash b is a continuous function. And since it is a continuous function, and if its image set is a closed set, then its domain set is also a closed set, right? So from the we can say that FBH, the set from which the mapping is done, from the mapping is done to the to 0 log 2d, this particular set is also closed set. Now this particular set is closed set. Now FBH is also bounded under trace norm, as every density matrix has a bounded spectrum. So every trace norm can be written as a function of the eigenvalues, and it will be bounded. So in a sense, we can say that for a finite dimensional Hilbert space being closed and bounded, FBH is a compact set. Now, since it is a convex and compact set, we can say that there will exist witness for every negative condition of von Neumann entropy states. What is the definition of witness? There will be an Hermitian operator for the states for witness for states possessing negative conditional entropy, such that if there is a state rho with a negative conditional von Neumann entropy, which is not belonging to this particular class FBH, that means it is not belonging to non-negative conditional von Neumann entropy. It is belonging to the negative conditional von Neumann entropy. And if it comes out the trace of rho W rho is less than 0 for such state, and this is not only sufficient to show this is a witness. Now to show W2 witness, we have to show that for all state sigma belonging to this class of FBH, which is having non-negative conditional entropy, for all such states in this class, trace of W sigma has to be greater than equal to 0. Now as a witness, to act as a witness, it is not only it has to be negative for the state lying outside this set of non-negative conditional von Neumann entropy states, but also it has to be positive for all the states lying inside this convex and compact set. All right. One example of this witness you can think about this W rho minus log rho AB I cross log rho B. So this is an expression that we obtained. We obtained from the conditional amplitude operator, which is a paper by Nicholas. So there are many use of this conditional amplitude operator in Nicholas Phillips paper. This most probably Nicholas Phillips paper. So this is not exactly equal to conditional amplitude operator, but we can derive this witness from this. Now you see, we have to show that this witness can identify is satisfying this condition or not, right? So how you are going to show this? We are going to show this that if you take trace of W rho and rho AB, trace of W rho and rho AB, this expression is coming out to be S of AB rho AB, and which is always less than 0. So the first part is shown. Now if you take any sigma AB from the set of all non-negative conditional entropies, for that sigma AB, we have to show that trace of W rho sigma AB has to be positive, always positive for any sigma AB from that class. Now how will you do this? This proof is very simple. If you take the monotonicity, use the monotonicity of the relative entropy, S of sigma B and rho B is always less than equal to S of sigma AB rho AB. Now if you substitute these values of S of sigma B, this relative entropy on this quantum relative entropy of this side and the quantum relative entropy on this side, what you will get trace of sigma AB log sigma B minus trace of sigma B log rho B, and here on the right hand side you will get trace of sigma AB log sigma AB and minus trace of sigma AB log rho AB. If you can rearrange this term, you will see the right hand side you can get S of A slash B sigma AB. Now sigma AB is a state in the non-negative conditional entropy. So this particular sigma S of A slash B sigma AB will be always greater than 0. And what is the left hand side? Left hand side is the trace of W rho sigma AB, which we are looking at, trace of W sigma. W rho sigma AB. So this right hand side, this is always greater than the right hand side, and the right hand side is always greater than the 0. So trace of W rho sigma AB is always greater than the 0. So we show that this is true for all such sigma AB belonging to this class. So we can safely announce that W rho is a witness operator. One such example in this context, if you take this particular state gamma, one state like this, gamma 0.995 plus 5 plus and 0.01 I by 4. A witness corresponding to this W gamma will be this, which can be broken up in this way, where the values of A, B, C are in this form. Now, if you detect if you say trace of W gamma, this will not only detect this particular state, but it will also act as a witness for other states like delta, right? So this is an example of a witness operator which can detect states with negative conditional entropies. So this is one example that we have given here in the form of an algebraic construction of witness. But we have in our paper, I have not included this in this presentation. We have also constructed the geometric witness for the states having negative conditional entropy. So this witness can
so you have 5 minutes.
Sure, I am just I will complete quickly. So this witness can be broken up into this basis, and can also we can do this decomposition of witness in the poly basis and the other basis. So in the last part of my talk, we will try to give a little bit motivation to the detection and characterization of the states which are absolutely conditional von Neumann entropy. So now if we ask this question, suppose once we find out the states with non-negative conditional, we are having states with non-negative conditional entropy, and that cannot be used as a resource or a task like this dense coding. Then is that the end of the story? Is something more that we can achieve if we can apply global unitary operators? We have seen that it is some states are there which are now non-negative conditional entropies, but after the application of the global unitary operators, they can be turned out into states with negative conditional entropies. And there will be some states which are very much resilient to this attack of the global unitary operators, and they will not be they will not be they will not become the states with negative conditional entropies. And these class of states are generally known as absolute class of states. For example, in case of separability, we call it as an absolute separable states, those which remain separable even after the application of the global unitary operators, right? Similarly, here we are trying to characterize the absolute conditional von Neumann entropy non-negative class states. So this class definition can be given as sigma AC S of u sigma AC u dagger minus S of u sigma AC u dagger A after the tracing out the density the one subsystem. This has to remain positive for all such u. If this is this class which remains whose conditional entropy remains positive and non-negative even after the application of the global unitary operator, this particular class will be called as a absolute conditional von Neumann entropy non-negative class. Now I'm not going to the proof since there is a lack of time. I'm just tell you the result. For example, if sigma AC is greater than equal to 1, this is a necessary sufficient condition for a state sigma AC bipartite state 2-qubit state to belong to this class, right? I will say that this sigma AC will belong to this class if and only if this sigma AC S of sigma AC is greater than equal to 1. You can look into the paper for the proof, but since there is I have 2-3 minutes left, I'm not going into the proof. I am just telling what is the utility of detecting these states. Now the utility of detecting this is that once we are able to characterize the states which will remain non-negative, whose conditional von Neumann entropy will remain non-negative even after the application of the global unitary operator, we can in the same time we are able to characterize the states which are now having a non-negative conditional entropy, but after global unitary operator they become a negative conditional entropy state. Means these kind of states are lying in the fringe, right? These kind of states are lying in the fringe. So detecting such states becomes very important. Here also we prove that this ACVNN class is also a ACVN class is also a closed and bounded, and is a convex is also convex and convex and compact. And I'm not going into the proof, but this particular class is also convex and compact, and there exists a witness operator for such for states which are lying in the fringe to detect such states. One such examples with couple of examples I stop. One such example is take this particular state which is having right now the conditional entropy of this particular state is 0, and but after the application of the unitary operator like this, the state changes to this, and we will see the conditional entropy is negative. So this is a state which is lying in the CVNN but not in ACVNN. Means these are the states which are not useful, but it can be made useful after the application of the global unitary operator. So this is an example, and this witness operator will able to detect the states which are useful for which can be made useful after the application of the global unitary operator. And this is an example of an Warner state where for these values of P, the state will be absolutely conditional von Neumann entropy non-negative class, and so whenever P lies in this range. So this is the range whenever P lies. So last part. So what is the relation? So relation between the absolutely local and absolutely separable and absolutely conditional von Neumann entropy, the whole exact geometrical relation of the relation is not known, but we can straight away say that we showed that absolutely separable can be a part of is a subset of absolutely conditional von Neumann entropy ACVNN class of states, right? So absolutely separable state preserves separability under global unitary operation. The non-negativity of the conditional entropies is a necessary condition for separability. And all separable sets have non-negative conditional von Neumann entropy. And we can show that this is a proper subset because with the help of this example. So there are states which is not absolutely separable, but in the absolutely conditional von Neumann entropy states. Similarly, in case of absolutely local, we also see that this will be a subset. In case of Warner state, absolute local will be subset of ACVNN. But in general, we cannot tell about this relation. So what is the conclusion? So we are actually moving towards the resource theory of conditional entropy. In the process of moving towards the resource theory of conditional entropies, and we have seen that how to detect the states with a negative conditional entropies, and how to identify the states which are not negative yet, but can be made negative after the application of the global unitary operator. What is the necessary sufficient condition? How to characterize, how to detect with the help of a witness operator this particular class of states? Not only CVN conditional von Neumann entropy negative class, but this particular class of states also. So these are few references that are useful in this context. And also, as I was telling you, there is an how we move towards the resource theory. We are able to characterize the free operations, which will actually keep the conditional von Neumann entropy non-negative states to non-negative states, right? So this is another work that we have done recently, and probably one of the invited speakers that Niman will tell about this work. So there are many other important bounds and witness, different construction of witness are there in the paper, but I didn't mention here. But if you can look into those papers for this. So so these are my collaborators who had been who had worked with whom I had worked. So and thank you. So Professor Arun Kumar Pati, Nirman Ganguly, and Shubhasri Patra, and Mahati Venpati. Thank you.
Thank you, Indranil, for a nice talk. So if just one or two questions are there, one can have that. Any question is there? Okay, if not, then...
Hello, Sivasis.
Yes.
So I would like to ask one question. I would like to know from Indranil that the witness operator he has constructed, whether this witness operator is defined for all the density matrix rho AB.
No, this is
because
not an optimal.
No, I am not talking about the optimality of the witness operator, but the witness operator, the way you have constructed the witness operator, that is log of rho AB minus something, something is there. So so I doubt that whether it is defined for all density matrices.
No, it is not defined for all the density matrices, because it depends on the rho AB. Because if I choose a particular state, on basis of that, this witness operator is defined.
Okay.
And the geometrical witness is defined for all density. In the paper we have the geometrical witness, which will define for all density matrices.
And
okay,
second
we'll have to,
thing is that,
sorry, Satyabrata, I think
yes,
we are
yes.
running
Okay.
out of time, short of time. Maybe you can discuss privately or in the chat box or email. So maybe we'll have to stop this session because we are running short of time. Sorry for this. So let me thank the speaker again and all the three speakers of this session. Thank you.
Thank you. Thank you.
Thank you, Sivasis. Okay. Okay. So since we are out of time, so we now start our next session, last session of this today. Professor Ujjwal Sen will chair this session. He is from HRI Allahabad, and he is doing quantum information and foundation for a long time. From after passing his master degree, he is engaged in this field of research, and he has done many works in the field of quantum information and foundation. So I invite Professor Ujjwal Sen to chair this session.
Thank you, Devasis. It's a nice opportunity to chair a session in this conference. So the first speaker is Miao Horodecki, right? Is he online? I don't see Miha.
Yes.
So
He has not joined yet.
So should we start with the second talk and wait for him, or wait for him for, because the actual schedule was at 4:20, right?
Yes, yes.
So it's already 7 minutes late. So did he send you an email that he will not join or something?
I am checking. Okay.
I think we should move. If the next speaker
so,
is available, I think it's better to.
I think we can.
Okay, there is no message. So Ujjal start with next speaker.
The next speaker is Jan is there, right?
Yeah.
Yes. So is Jan there?
Yes, he is there, but you have to. Okay.
Yeah, but I don't see him. Do you see? Is he online?
Yes, he is online.
So Jan, maybe yes. Jan, maybe you can share your screen. Hello, maybe he is not at the desk. He is probably prepared for in something like an hour's time or something. So maybe he has gone off the desk. Should we try the third person then? The third person, Lorenzo. Is Lorenzo there? Lorenzo, I think, is not online, no? Lorenzo, I don't see. So we are in a fix. So what should we do?
Wait for a couple of minutes. Okay.
Yeah, maybe we wait for a couple of minutes.
We are contacting with Meow.
With Miha. Okay, you have his number?
No, Sapon, someone has done. Sapon is contacting with him.
Okay. So we just wait for 5 minutes. Yeah. Or if Jan comes online, maybe we can start with Jan. I mean, he is online, but if he comes...
I have given him a chat. Could you join now?
Okay.
I have messaged him.
Okay.
Ujjwal, we are also contacting with Ian also. Okay.
Okay. Let us see. Whoever comes first, we can start with him.
আর মিয়াওয়ের সাথে মানে মিয়াওয়ের স্টুডেন্টের সাথে ওখানে কন্ট্যাক্ট হয়েছে, দেখা যাক, ও এক্ষুনি বলছে। আর ইয়ানকেও কন্ট্যাক্ট করা হচ্ছে, যে আগে আসবে তাকে শুরু করে দিতে হবে।
ওকে।
উজ্জ্বল, ইয়ানকে দেখতে পেয়েছিস? উজ্জ্বল?
Hello, yes.
হ্যাঁ, ইয়ান রেখে ও জয়েন করছে।
Yes, he has joined, yeah. So Jan, you may share your screen, please. Hello, Jan. Could you please share your screen? We can't hear you or see your screen.
ডেস্কটপের আওয়াজ শোনা যাচ্ছে।
Jan, if there is a problem with your system, maybe it's sometimes useful to log off and log in again. That is provided you can hear us. So maybe we can chat with him and tell him to log off and log in again. Should I do that?
হ্যাঁ, চ্যাট করতে পারিস।
Yeah, so maybe I can.
Hello, everyone.
Yeah, I can see you. We can see you.
Sorry, I just got the call that you would like to talk to me earlier. I apologize for not being there when you pointed me. I can do my talk now if that's what you prefer.
Yeah. Good, great. Yeah. So the first speaker, we can't contact him. So
sure.
The usual online
Hopefully
trouble.
he's joined. Okay.
So
So shall I share my screen?
Yes, certainly. Yes.
Maybe I'll do like this because I have two screens. Can you see my presentation?
Yes. And we have to make it full screen. Yes.
Yep.
Yes. Good. So we have the first talk of this session by Janek Kolodinsky, and he's from the Center of New Technologies in Warsaw in Poland. Jan.
Thank you. So first of all, thank you very much for inviting me. I wish we could all guess meet all in India, but unfortunately the times are as they are. So indeed, I work at the University of Warsaw. So given that I'm not physically there, maybe I just decipher all these affiliations. Basically, we are a kind of special department at the University of Warsaw, and in particular work in the Center of Quantum Optical Technologies. But I run a small group since 3 years, the Quantum Information and Inference Group. And maybe if some of the audience know me from my works, I've been working a lot on problems in quantum metrology and sensing. And this is what I would like to tell you about today, about our recent results of metrology with imperfect measurements. However, just to maybe emphasize, and I'll try to be explicit in the talk about this, these days we are trying to, okay, I don't like this expression because it's more for the grant writing, but to bridge the gap between the abstract quantum metrology and the experiments. So although I thought of giving a talk that is more on our fundamental results, I would like to give an insight that what maybe is the frontier now is some kind of to connect to what is actually done in the lab. So as said, my talk will be on quantum metrology with imperfect measurements, and this is really a collaboration with Professor Alex Retzker. So he's an expert on envy centers as well as other things, and this is what will be the main motivation on my talk. But just to say more, Alex Retzker is a professor at the University of Jerusalem, the Hebrew University of Jerusalem, but he's now with Amazon in California. As you probably know, lots of researchers are now being dragged by the quantum computing community. And actually the driving the tour de force on these projects were postdocs, in particular my postdoc Ying-Long Len, who is now on vacation after the long 2 years working with me, now in Singapore. But the other person was Tuvia Geffen. He's a postdoc, used to be a PhD of Alex, but now he's with John Preskill in California. So this is it. And if I'll try to be as explicit as possible, but if you would like, please refer to the Icqif for these results. And actually, as we are just doing the resubmission, I can promise that there'll be another version within coming weeks with more details, but I will hopefully tell you within this talk and will not keep any secrets. Okay, so what is the main aim about this work that I would like to present? It's really something quite obvious, and we were kind of surprised that no one looked at it before, that we all know that measurements are never perfect. I mean, what you do in the lab, when you try to implement a POVM, it's not going to be the way you'd like it to be. And somehow we asked the kind of question in a systematic manner. I hope I'll convince you that we give kind of general answers, is how does this fact impact quantum metrology, which I will define in a second. And actually, when I say quantum metrology, I mean the most optimistic scenario of local estimation. Again, I'll be more precise on the next slide, but this is really about, if you're familiar with the topic, it's about doing this so-called asymptotic statistics, asking questions about unbiased estimators and using tools such as Fisher information. But the main point here is like, okay, in an experiment, my measurements aren't perfect, but maybe I can compensate for this, right? So the compensation is really the control. And here came the idea of Alex Retzker, this is what really happens in envy center-based sensing. So for those of you not working maybe every day with solid state systems, note in this type of system, it's really easy to apply some kind of control pulses, such as microwave fields to some kind of rotate your spins. And this is, for example, what happens in dynamical decoupling. And if you remember, these are techniques to some kind of fight the noise. However, what limits you is the measurement. The measurement is imperfect by definition, because you are shining light in a solid state system and you are measuring it. So you are doing photon counting in the end, and this you cannot really go around. Okay, but before I give you that motivation, I really need to summarize some results on quantum metrology. And maybe I'll try to follow chat, which is always hard when you give a talk. But if you are puzzled by any of the definitions, please stop me. I'm more than happy to answer during talking. But what is quantum metrology? If you don't come from this background, it's really the problem of parameter estimation, which is not new. It's known in the statistics and parameter inference community. So here I've put a book that is really, say, a Bible on different techniques. But the problem is like this. I've drawn it in the quantum setting, but you can think of that the idea comes from classical schemes. So I prepare some system, a quantum state of a system. Let's say for generality, the system consists of n particles. This can be photons, this can be atoms, photons in an interferometer, say, that are in two modes. Atoms have, say, two levels, then you can describe them effectively as qubits. And I prepare some state that in particular can be entangled. Now in metrology, the idea is that this system evolves. So the evolution I represented here by this curly E, map E. And basically this evolution encodes some parameter of interest on the state, right? So here I call it curly phi. And basically, I would like to measure the system now. In the quantum world, I would do the quantum measurement. And then from the outcomes of this measurement, I would like to infer what was the parameter. So for instance, if you think of interferometry, and these are photons, then I would like to infer the relative phase between two modes of an interferometer. In terms of atoms, maybe a magnetic field that is responsible for the Zeeman splitting, and so on. But notice that, okay, I've drawn it in a quantum way, but the last step here is really this classical statistical inference. In every round of measurement, I'm obtaining an outcome X, and now based on many repetitions, so say X1, X2, and so on, I'm trying infer, okay, formally this is called build an estimator. So these are random variables, so this object is also a random variable. And I would like this estimator to be as close as possible to the true value that was encoded, right? So this is really, this part is classical and has been studied by the statisticians for many years. So, but I maybe refer to this book if you want to have the basics. But you should already be asking yourself a very fundamental problem is, okay, but in this setting, can I do as many repetitions as I want? In particular, if you work with, say, capacities of quantum channels, is this an IID scenario in which this parameter mu, which is the number of repetitions, can be freely taken to infinity? And indeed, if you say yes, you follow the so-called frequentist approach in inference. So this is the approach in which basically the outcomes, because you will register frequencies of obtaining particular outcomes, they will converge to probabilities, right? So if you follow this approach, then you have this is really the kind of tour de force, is that in this approach, you know that any estimator that you will build, which is formally unbiased, okay? What I mean by unbiased, it means that on average, it reproduces the true value. It is bounded by the so-called Cramer-Rao bound. So this is a statistical property that you can always bound an unbiased estimator, but please bear in mind, this is really this limit of infinite repetitions by 1 over the Fisher information, where Fisher information is the property of a single round of your experiment of the probability that dictates the outcome, okay? And now the thing that you should ask yourself already, okay, something is dodgy with this approach, because this object in particular can depend on the value of the parameter you are trying to estimate. So is it the temperature of the system I'm trying to infer? Is it this relative phase? Is it the magnetic field? And indeed, my answers here can depend whether I'm trying to sense, I don't know, phase fluctuations around pi over 2 or 3 pi over 7, right? And this is indeed the catch of the frequentist approach, but you should not be put off by it if you are thinking of quantum sensing experiments like gravitational wave detection, for example. You are building a device that is optimized, calibrated for some particular value of the parameter, and you are really trying to estimate small fluctuations for this known value. However, if you would like to do a typical sensor in the way, I don't know, you'd like to build a device that measures the temperature, this is indeed not what you should do, because then you actually don't know the parameter in advance. And this is where the Bayesian approach comes into play. And if some of you are statisticians, you probably know that there's the two communities that maybe don't agree on many things. And then in the Bayesian approach, this maybe refers to the talk of Valerio Scarani from today, is you should really infer. So he was talking about retrodiction, going back. In the Bayesian, in this setting of metrology, we just need to go forward. In particular, from the outcomes of the experiments, we should most actually infer the parameter, assuming some prior that represents our knowledge. And this is what I will not talk about, but I would like to just mention to you that this is what we do in our group nowadays a lot, because we are really thinking about the realistic devices that are operatable, and these are more this kind of real-time estimation problems. So if you're interested in this, please feel free to approach me. But what is interested there, just to give you some kind of intuition. So for example, with atomic spin ensembles, you have atoms which are being held in a magnetic, so these are actually in a vacuum chamber, but they're affected by a magnetic field, and you are trying to measure them with light. And in particular, you are measuring them over time. So you cannot assume now that these are independent repetitions. Actually, you're dealing with a quantum system that continuously gives you a signal, in particular, a very noisy signal, which is what you are registering on the photocurrent here. And now, this is where actually extra quantum effects come into play. If you are familiar with the continuous measurement theory, now because I'm measuring the system at time t, I will affect its subsequent evolution. So for example, in this kind of setups, you can get effects such as spin squeezing. You are entangling the atoms by measuring them. And this is reflected then in your inference, right? That you are actually improving the properties of the system at later times, thanks to what you've done before. So I refer you to our work with Julia Moros-Binefa, who's my PhD student, but Bayesian inference techniques such as Kalman filtering come into play. On the other hand, another devices that we were studying are optomechanical devices. This you can think of as optical cavity with one of the mirrors being an oscillator. But this applies equivalently of the photonic resonators or levitated nano spheres or nano objects. They actually share the same Hamiltonian. But then here you are driving such a cavity that is with a mirror, and you are actually registering photons that come out. And these photons give you various click patterns. And now again, you are not allowed to repeat your experiment. You just have your cavity, there's some external force that perturbs your mirror, and now you are just getting these click patterns, and based on them, you need to infer what was the perturbation, right? So this is again, a sensor that needs to work in real time. And what is interesting here, for instance, this is a nonlinear interaction, so you can have some quantum effects such as bunching of anti-bunching of photons, which I hope you remember from your quantum optics standard courses. And based on that, we are able, for example, here to infer parameter much more precisely, because the photons that come out in this what we call cascade regime, that they try to bunch when they come out, they provide more information about the parameter, right? So I close with this. So just this is when I would talk about quantum sensors, I more think of this type of devices, but my talk will be fundamental. I will actually go back to this frequencies approach. So from now on, I will assume that any experiment you do in quantum metrology, you can repeat as many times as you want, and you would like to obtain best precision in such a limit. So having said that, I hope I convinced you that this is this classical fish information that comes out. Then by the Kramer-Rao bounds from below the ultimate precision, the mean squared error of your estimator. However, now you can some kind of put it in the quantum setting by saying, by constructing the so-called quantum Kramer-Rao bound. And this is quite intuitive. Basically, in this kind of structure, you should maximize over all POVMs you are able to do. And this is by definition the quantum Fisher information, which stands here. It's basically given this setup. If I optimize over all POVMs, I recover what is called the quantum Fisher information, which is now independent of the POVM. It's a property of the state. And from the kind of seminal work of Brownstein and Caves, this quantity is often written like this, where L now is this called symmetric logarithmic derivative. Okay, so so that's it. We are dealing with quantum systems. We are doing many repetitions, and hence, if I'm allowed to do any arbitrary POVM, I'm limited by the quantum Fisher information that limits my precision. But one more slide, because I will need some properties of this object. It's actually nice to think of it as a metric on the manifold of quantum states. So maybe I refer you to some review that we did with my colleague Marcin Jarzyna, but there you have it nicely summarized. But think of it that we are actually trying to resolve probability distributions. So these probability distributions live in a manifold, and now the parameter is really specifying a single curve, right? So the question about parameter estimation is really, or statisticians would call it point estimation, is where along this curve of p theta or p phi, I apologize, you are, no? And apparently you want to resolve the point at which you are currently standing. And the same idea can go onto quantum set. In the quantum set, similarly here, you can define distances between probability distribution, Kullback-Leibler distance, Bhattacharya distance, which will appear here, or total variation distance. Here, similarly, you have the structure of quantum states. So you have distances such as trace distance, Burras distance, and so on. So you can define the kind of tangent space and the metric associated with a given distance. And this is, I'm not going to go more into mathematics, but just to really give you intuitions about quantum Fisher information, this is really the metric that comes out if I choose the Burras distance as a measure of distances between two quantum states. So if I take two quantum states that are perturbed by a, say, along this curve by a small perturbation of the parameter theta, then the metric that naturally appears is the quantum Fisher information. And actually, the Burras distance is defined by the quantum fidelity. I haven't wrote the formula for the quantum fidelity, but I hope you are familiar with it. So important observation that I hope that comes to your mind is now that we have defined the quantum Fisher information as the maximization over all POVMs. So maximizing the classical Fisher information, which is the right-hand side here, becomes equivalent to minimizing fidelity, right? So for instance, I referred previously to this work of Brownstein and Caves, but actually, even if you remember like Nielsen Chuang's book, you know that to saturate quantum fidelity, it's enough to, there's an explicit proof of which POVM to choose, such that from the Bhattacharya, I'm giving the talk in India, so I should probably use this name. So if I take the Bhattacharya distance and I maximize it over POVMs, I will recover the quantum fidelity of Yosha et al., right? So in the same sense, this quantity is recovered, and this is some kind of independent proof what Brownstein and Caves did. So please bear that in mind if you haven't worked on quantum Fisher information before. But another issue that you might strike your mind is that maybe actually you have a system that you cannot describe in this framework. I have included some quantum map and so on. So there's then actually I advertised the talk of Javid, Javid Naiko at 6:40 of the Indian time, who's my postdoc there. You need to somehow change the rules of the games if you deal with, for example, a quantum system that obeys non-Hermitian dynamics. And this is an interesting topic now that various groups are working on, because then there's this phenomenon of exceptional points. I hope Javid will explain you there, but there you don't have quantum maps describing the evolution, you have this non-Hermitian dynamics, and you need to be a bit more careful. Okay, so the last concept that that is important, and I hope it will be clear, is this notion of standard quantum limit versus the Heisenberg limit. So let's go back. So I have a quantum system that is encoded by the parameters encoded on it, and then I measure it with a POVM to construct the estimator. But the crucial kind of canonical setting is that the encoding happens independently on each particle. And this is interesting because now we can in particular look at properties such as entanglement of this input, because now thanks to quantum entanglement, maybe I can do something better than in the classically correlated or here separable states. And indeed, this is the canonical setting when the unitary is encoded with some local Hamiltonian. Then it's not hard to prove that actually the Fisher information of the quantum Fisher information of the output is just the variance of the Hamiltonian. So for example, of the global Hamiltonian describing the all n particles. So in particular, it's a sum. So if it's a qubit, you can think of it being say proportional sigma z. Okay, and then I think that by the connection to fidelity, you should already agree with me on these first two properties that I wrote here, because if I take a tensor product of quantum states, you know from quantum fidelity that you don't need to do collective measurements to saturate the quantum fidelity. In particular, then it should be intuitive that the quantum Fisher information must also be additive. Moreover, you can prove it's convex in the sense that if I take quantum states, it's always best to provide someone pure states with some probabilities and tell him which pure state I give to him. So in that sense, it should be clear that the optimal input should be a pure state. And moreover, you know, I hope you know that the variance of a Hamiltonian is generally upper bounded by its spread. This is what I mean by S, which is the difference between maximal and the minimal eigenvalue. And then depending whether the state is separable, the variance will scale either linearly with the number of probes or particles or quadratically when it's entangled. And this is really these notions of standard quantum limit and Heisenberg limit. So in the standard quantum limit, it's a quick observation that if I start with separable states, my quantum Fisher information must be limited by n. So at best, my error will scale as 1 over n. And now if I allow for quantum entangled states such as GZ states or Nun states, then my error will scale as 1 over n squared, and this will refer to as the Heisenberg limit. Note that I sneaked here this number of repetitions on the left-hand side, because again, let me emphasize, we talk about scalings with number of particles. In the limit, I can do as many repetitions as I want. Okay, and the last observation is very important for the purpose of this talk, because okay, I've been talking a lot and it's hard when I don't see your faces, but we will want here to deal with imperfect measurements. And now the crucial observation is that okay, from fidelity, you probably should have the intuition that if I have tensor products of states, so if I take independent repetitions, you can ask why could I not make a collective measurements of all different copies? But from fidelity, you know that this is not necessary to saturate the quantum fidelity. So follows that you don't need collective measurements on tensor products of states if you do quantum Fisher information. But the second observation was made by the seminal paper by Giovannetti, Lloyd, and Marcona, is that moreover, in this setup, it's also enough to consider local projective measurements on each particle. So here it's not that clear because this guy is entangled. Particularly, it can be a GZ state or a Nun state or some entangled state, but it's enough to do local measurements, right? So in the perfect case, ideal case, if I want to do quantum metrology in the Heisenberg limit, it's enough to do local measurements. And now it kind of comes our work. And let me start by the motivation of the envy centers. But the point is that in the real experiments, this guy here. So each of these local measurements will be noise. And so maybe what will be the consequence? Are we still able to attain the Heisenberg limit? Is this the same as doing noise here? It's not, as I hope to convince you. And let me tell you. So what is the motivation? Okay, let me watch the time because I started first. So the motivation is really when Alex Retzker came to us, it comes from the envy centers. And if you're not familiar with the solid state systems, envy center is basically a diamond with one of the carbons being absent, and next to it, there's a carbon replaced by a nitrogen. And thanks to this, because nitrogen has more electrons, this is a stable system, but there's one free electron that kind of, bumps around in this empty spot. And it's particularly this electron that will act as a qubit, right? But what is so cool about the system is that this extra electron that comes from nitrogen can be coupled to the surrounding carbons, in particular the nuclei, or the nitrogen. And this is what type of gates people are able to implement in this type of systems. Moreover, in the current experiments, this is the group of Misha Lukin, people are already starting experiments with multiple vacancy centers. And in particular, I chose this plot just to show to you that this is what they call spin control. It's easy for them to do some kind of microwave light beams to say rotate the spins or make the spins interact, say the nucleus of nitrogen with the electron and so on. But then they have a separate beam that allows them to measure them. So this is exactly where we come from. We'll be able to control the system, but then when we measure it, we are kind of restricted. This is all what we can do. And this is what I tried to show to you here. This envy center is a spin. In particular, the parameter that I will be concerned with within my talk will be some magnetic field that you apply from outside. And now basically, so this is this external signal that is kind of drawn here. But then you are able to apply some pulses to control the spin. And then in the end, you will measure it by fluorescence. And let me just first tell you a bit more about what is the problem with this measurement. It's basically you shine light at a spin half particle, and basically you collect photons. And based on which state of this system, in particular here, I will just call it 1 and 2, you'll get a different distribution. In particular here, you will get a Poissonian distribution. And if I drawn it to exaggerate it, if the state was 0, you'll get a Poissonian slightly to the left. And if the state of the spin was 1, this vacancy, you'll get it to the right. No? But you see some trouble, right? Because if you measure something in the middle, you might not really know, did I actually project it onto 0 or did I project it onto 1, right? And this is the noise that you need to fight. But basically, experimentalists are very smart people, and they have invented very cool idea how to improve this measurement. So basically, they rely on this notion of quantum non-demolition measurement. This paper comes from David Wineland, from papers on ions, but I don't know if you are familiar with this, but the idea of quantum non-demolition measurements is you're gonna use some system on the side that you will actually measure. So you would like to measure one spin, but you use some kind of auxiliary ancilla, and now you have some interaction between these two systems, and in particular, you would like that your total Hamiltonian, which means the system, your ancilla, and their interaction, commutes with the operator you would like to implement, this measurement operator you would like to implement on your system. And this means that by measuring, you are not affecting your statistics. Okay, you will affect the off-diagonal coherence terms, but at least the eigenvalues stay the same. And this means that I can repeat these measurements as many times as I want. And in particular, I will keep measuring the same system, right? Okay, same system in this particular basis. And this is what they do. And particularly, they want to measure the electron, and by implementing a C-node gate, they transform its state onto the nearby nitrogen. And then basically they measure the electron, because it's easier to measure the electron because light always couples to the electron. They do this measurement, but then afterwards they transfer back the state of the nitrogen back onto the electron, and they measure it again. And this they can do up to thousands, right? So basically these Poissonians get more and more stretched out, and in principle you should be able to resolve better and better whether the state of the electron was in the ground state or the excited state. And sure, just to make the story full, I mean, this is very advanced. So they can even do the same by using the electron as the ancilla and measure the nitrogen, or measure actually the carbon, the state of carbon, which is somewhere nearby, again, using the electron as an ancilla. But my point is they always get this kind of Poissonian distributions. And in particular, if the state was 0, it's a Poissonian to the left. Okay, if the statistics are high, Poissonian is even more like a Gaussian. And then if it's excited state, you have the Poissonian to the right. Okay, so this is the model. May I just kindly ask Ujwal to tell me how much time I have, just because we started at.
Yeah, it's about 20 minutes more.
Okay, thank you very much. Yeah, I'll manage. No problem. So basically this is the setting, but we want to write it in this abstract form, right? So I have a system which is rho. Now I have some parameter coding. It's a unitary. It's this magnetic field, and now the point is that these pulses that I can apply, these are this control, which I will label as V. And afterwards, there's this P of M that happens, but importantly, it's imperfect. There's some noise, which formally it's a stochastic map in this case. It's basically, rather than getting two outcomes I, 1 and 2, I get the output is a number of photons. No? So in particular, this, let's call it this Poissonian mixing. No? So if it's 0, I get the Poissonian to the left. If it's 1, I get the Poissonian to the right. This is what I try to write here, but okay. You can really sum up over the POVM elements, and this is really, you can also think of it that this is just particular implementation on an imperfect POVM. So now you would like to, for this given imperfect POVM, you'd like to find the optimal rotation such that you maximize the precision, in particular maximize the quantum Fisher information. So okay, this will be a very simple example, but bear with me, but I hope it'll give you some intuitions. It's a qubit. So we are dealing with a Bloch ball. It's not rocket science, just quantum physics. So basically here we just have a qubit that rotates around the Z. So we are really trying to estimate the angle from, say, the x-axis, which I label as theta. And okay, for simplicity, say that this theta is really proportional to the magnetic field. Say our experiment lasts time t, and this time t is constant. This is the standard. I didn't invent this. This is standard what's called DC magnetometry model in NV centers from this paper. And basically, okay, let's apply these tools. I told you, okay, if I do a perfect projective measurements, I have no noise, everything is clear. My error is bounded by the classical Fisher information. Now it's bounded by the quantum Fisher information. Note, just to be consistent with our paper, I call it now curly F rather than FQ. So if you go to our paper, this will be the notation. But and again, the classical Fisher information is as I wrote it before, and the quantum Fisher information is the formula from Baumstein and Caves. But okay, let me give you some facts, because I hope this doesn't require any of this machinery. First of all, we are estimating rotations around Z-axis, and we have a Bloch ball. So it's clear that you should be somewhere on the equator, as far as possible from the axis. So you should get any pure state on the equator will do it, because it's most sensitive to the angle. Moreover, actually, this is kind of maybe non-trivial, but you should think about it, that any angle, any measurement that you will do in the equator plane will also give you the best information, because one outcome oscillates as cosine, other oscillates as sine. If you calculate the Fisher information or think about it, you'll get this ultimate resolution. No, so this seems very simple, exactly. But now I have this imperfect measurement. So let me just give you a motivation, and things get, even for such a simple system, things get quite nasty. So now I say, okay, but I'm not allowed to do perfect measurement in the equator plane. Unfortunately, I'm doing this NV center experiment and I have Poissonian mixing. So I'll get some effective POVM that's no longer projective. And then, sure, and this is the definition, okay? We would like to define the imperfect QFI as, given this measurement model, what is the best precision you can achieve when you maximize over this control here. And in our simple model, this will be the rotation around the z-axis. It's actually in which direction you should now measure, given that your measurement is noisy, such that you get the best precision. Okay, and it gives you some more facts. These are proofs in our paper, but okay, still the optimal state is the pure state on the equator. Sure, we are trying to resolve angles, so let's stick to being somewhere here. But the second proof that is not that trivial is actually, again, it's optimal to consider measurements, so this unperturbed measurement, to be in the equator. But now the problem is that actually the answer will strongly depend on the angle where your measurement, so this is the angle I marked here by this green curly phi. So let's just focus on this this imperfect, this dashed line. It's basically, or this solid black line. And basically now, depending on the angle you are from your state, you will get different precision. And this is what actually experimentalists originally asked us. They didn't know what path to, so by what angle to rotate the spin to get best precision. No? And basically this question is already non-trivial here. And they just wanted this angle, and this angle depends on this Poissonian distributions that I had on the different slide. And okay, so this is it. We have a noisy measurement given by these Poissonian distributions, and thanks to that, now even for such a simple problem like estimating a qubit rotation, we really need to tailor at what angle to place our projective measurements that gets disturbed. And actually, how to find this angle? Okay, so so first of all, sure, you can do numerics. Numerics always works, but this is not nice. Basically, what you can do is, we are having these distributions of photon counts, no, that have these Poissonian distributions. We can just decide on a cutoff far enough to the right, and then do the sum, no, and solve it analytically to find the optimal phi that maximizes this quantity. Okay, but as I said, experimentalists are very smart, so they actually invented something that they like, because they like also simple solutions. So what they do in experiments, they do what's called threshold methods. So by threshold method, they say, okay, let me not count the photons, let me just put a line in between the two Poissonians, and if I say I got a photon number to the left, the state was 0. If it was to the right, it was 1. Okay, in this particular experiment, they had 3 states. So, but in our simplified model, is basically these represent these two Poissonians. And this, just to give you intuition, this is just a bit flip channel, right? You should, if you did a projective measurement, you should get outcomes 1 or 2. Now again, you get outcomes 1 or 2, but with some probability 1 minus p and 1 minus q. When the state was in say excited state, you actually will think it's in the ground state, and these correspond to the overlaps here of the Poissonians with the nominal distributions, right? So in the sense, this is just the effective stochastic noise that that affects your measurement outcomes, which is completely classical, no? And then for that problem, we can solve it. So this is what we actually plotted for you here. It's if I solve the system, I can solve the system with this particular binning, and as you see, you can get an angle very close to the optimal. But we did something else. Okay, you can generalize it to the more binning. Say you can put these thresholds. Say you can say that there's a region in the middle when you don't really know, so you can really include it here. But then the problem is how to optimize where to put this X star, no, which is the where to place these boundaries when you make decisions, okay? But what we are also proud of, and I just wanted to show it to you, we also devised a hierarchy, a convergent hierarchy on the classical fish information. So basically, the problem is here is that in this experiment, you have infinite outcomes, no? You have x goes to infinity. But then what we did, we realized that you can do lower bounds on classical fish information by studying the moments of a given distribution. And note that here we have two Poissonians, okay? So it's an effective convolution of two Poissonians. So for such distribution, it's relatively easy to get formula for the first moment, second moment, and so on and so on. And basically, what we've shown, there's like a convergent hierarchy of how many moments you will include, the tighter you'll get to the true value. So for example, okay, you construct a matrix that describes your outcome distribution up to 2k moments. So F1 requires you to know the variance of the outcomes. And actually, if you know about this, F1 in this hierarchy is simply the error propagation formula. So this is the simplest, probably you've learned it at some experimental courses, that if you want to infer from some random variable of observable, this is the formula how errors propagate, right? You take the derivative of what you are measuring, square it, and divide it by the variance. Then this is exactly the connection to the Fisher information. So we were proud of this, and this is what I plot for you, because this then gives you a way to go up and up in the hierarchy to get closer and closer to the true values. However, I should say that we discovered that mathematicians had this concept in the 80s, maybe not in such a nice form, but we are very close what was known in the mathematical community of building lower bounds on classical Fisher information. Okay, so last and maybe not least. So, okay, I've told you about the very simple problem of a qubit, and it already got quite nasty, but I wanted to give you these intuitions, because now I would like you to present the main proofs of our work. So these are kind of general proofs. And now the first theorem that I'll throw at you, but try to give you some intuitions. So what we are able to prove, that actually in this setting, any setting of qubits, if you give me a pure state and it's encoded somehow, and if you are allowed to do a noisy measurement, which is this POVM M, that actually this imperfect QFI has this very interesting form. It's actually the QFI as if the measurement was perfect times a factor that depends explicitly only on the POVM. So this was what surprised us. This means that some kind of noisy POVM just rescales your quantum Fisher information by a constant, right? And this constant you can calculate independently. So what is the intuition? Note that this is a maximization of orthogonal states, so any two states. So basically, you are trying to seek two orthogonal states that you are able to resolve the best with your particular POVM. And these two states that you may resolve, that give you this constant factor that stands in front. And okay, you might say, okay, but your theorem applies, or lemma, sorry, applies only to pure states. Indeed, we can prove it only for pure states, but the encoding is not relevant. And if you are familiar, people are also working with some kind of problems of critical metrology when the pure state describes, for example, a ground state of some Hamiltonian. So although it's only for pure state, let me emphasize that encoding doesn't need to be unitary. Okay, so what I showed you before, for example, these plots, it was actually plots of computing this gamma. So all the techniques I told you about, okay, I gave this motivation by this simple example of a qubit, but it's really about computing this gamma, which is this factor, this POVM-based factor that lowers your quantum Fisher information. Okay, but this seems surprising, and it was surprising to us, because if I tell you now that if I give you a quantum metrology problem and you're allowed only to do a noisy POVM, you'll tell me that you can still get a result for your quantum Fisher information as if the measurement was perfect. You just get a rescaling factor, right? Which is this gamma. But this should then mean that if I have a problem that of n particles and it scales like this Heisenberg limit, this n squared, then you should also get just a constant factor. So you should preserve this Heisenberg limit. And is this true? And this is where our results come into play, because the answer will strongly depend on what control operations you are allowed to do in your experiment. So I told you that in the perfect case, it's always enough to do local measurements, right? And this is important. And now, okay, if I get a global control, so if this experiment is could act a control that controls many qubits or many NV centers, then, okay, the intuition is that this is global, so this becomes like a global POVM, right? And then things seem promising. And this strongly contrasts if you are able to only control locally the qubits. And this is indeed the case. So what we prove then is we prove a Go theorem. So we show that with global operations, indeed, if you allow for a global control, but your local measurements are noisy, you are always able, in the limit of n going to infinity, attain the quantum Fisher information. So if you had Heisenberg scaling, you will preserve the Heisenberg scaling. Okay, and let me tell you why. So I hope you remember that the first lemma told us that there's this constant factor, which is dependent only on the POVM, and it was about finding two orthogonal states that are at best distinguishable by a POVM. And now is the idea. So somehow you have your measurements. These measurements are noisy but are local. So basically, you can always think of it that whatever comes out of the circuit, or this is what you're trying to estimate, you can, because you have a global unitary, you can always rotate it into an orthogonal state that has this tensor product structure as well, right? So because remember the measurements are local, so they have the tensor product structure. So I can always rotate out the state that comes out onto a subspace, which is a tensor product structure of psi, and then orthogonal to it. And but this means that, okay, if you stare at this formula, you can easily construct a Cauchy-Schwarz lower inequality, which is then gives you this lower bound. But basically this means that this is the overlap that will determine the lower bound on this gamma. And now it's an overlap between product things, so this will scale exponentially, right? So this C is just this overlap on depending on which states I rotated it on. But importantly, thanks to the tensor product structure, scales exponentially. So if I go with n to infinity, this bound converges to equality. No? So okay, so just last intuition is that quantum Fisher information, maybe for the experts, depends on the state and its derivative, right? So this forms like a two-dimensional subspace, and all the magic that comes out here is that with a global unitary, I can just move, despite that measurement that will happen later will be noisy, I will move all to this two-dimensional subspace onto the subspace that my measurements still can distinguish. And that's why this works. Okay, you should say beautiful, but this is for pure states. So maybe it's like it's a zero measure result. Maybe if you add a bit of noise, this is completely lost. So we did that. So we proved the robustness. We showed that if you add a bit of white noise, you still the proof is preserved. Just you get the constant factor of R, which is the strength of your white noise. So some kind of this preservation of scaling is not it is preserved not at a single point, but around, say, a ball around the state you are trying to use. And so, okay, just to give you a concrete example, remember this asymmetric bit flip channel. indeed you can show that despite you are doing local measurements that experience this asymmetric bit flip noise, so your outcomes are randomly flipped, you can saturate. This is if you have no white noise, this is what the GZ states will do. The GZ states have quantum Fisher information n squared, so dividing by n squared, they just give you 1. And now importantly, despite the noise, okay, we have our lower bound and we have the true. Then numerically, you can see they converge to the true values. So basically, you can do global control in your experiments. You can even preserve Heisenberg scaling. But this is not the end of the story, as you may imagine. If you have just local control, then unfortunately, you are doomed to go back to standard quantum limit. And why is it so? So basically, we use this framework of quantum classical channels of whole level. So basically, note that if the control is local, I can just focus on this building block, which is my encoding, my control, and then the noisy POVM. And then I can just treat it as a quantum classical channel, right? It's the channel that gets quantum input and outputs a probability distribution. So it's just a diagonal distribution, but it's still a quantum channel. And then basically we apply the tools of noisy metrology, which were known in the field previously, to show that you can build an upper bound that on this imperfect quantum Fisher information that now importantly scales linearly with n. And this relies on the fact that you can always build some Krauss representation, and basically you should optimize this quantity over Krauss representations. I will not go into detail, but the kind of framework behind this is this framework of quantum classical channels that I think was in the book of Holevo, right? So for example, in this, again, this asymmetric bit flip case, note here I plot the error versus the number of probes. This is a log-log scale, so 1 over n is this line, some kind of, no? And now the crucial point is that your optimal, our upper bound scales like this. So basically this is if you didn't have entanglement, so you are able to improve by a constant. And then what we also do in our work, we also show how to saturate this upper bound asymptotically. In particular, we show that you can do it with spin squeeze states. And okay, this requires some modifications of error propagation formula to include the idea of noisy POVMs. But the conclusion is, if you have only local control, you can only improve by a constant factor above the standard quantum limit. And but luckily, okay, you can saturate it, but by doing some smart preparation of the entangled states. Note that in the previous case, global control, it's best to use GZ state. Here, for instance, best to use a spin squeeze state. So some kind of less entangled states are then robust to this type of noise. Okay, so let me summarize. I hope you followed me, although it's always hard to talk to a screen. So basically, at first, I hope that I convinced you that in my group, we work on quantum sensor implementations, in particular, these ideas of how to do them in real time with single shot. However, we also work, and this is the project I presented, on fundamental problems in quantum metrology, in particular in this frequentist approach when you use tools such as Fisher information, and this is what our work was on. And in particular, the motivation is that in sensing applications such as the envy centers, that imperfect measurements naturally arise. I mean, you are not allowed to do the projective measurements that you would like to. However, you can then control your spin, right? And basically in that setting, we have developed various techniques to estimate, okay, forming lower bound. I showed you these techniques of binning that experiments like to do, or we do this convergent hierarchy of moments. But basically we can lower bound this Fisher information and the imperfect Fisher information that includes this fact of imperfect measurements. And Okay, and basically this is a special case. This was this lemma 1 that I showed to you, that this evaluation of imperfect quantum Fisher information is a general problem when you have some kind of constant factor that now depends on the P of VM, the structure of PM that you have in your lab. And this has in particular very strong consequences on the setting in which you have n probes, right? Because there you have the notions of standard quantum limit and Heisenberg limit. And then if you stick to local measurements, but they are now imperfect, it's really whether you can still do global or local control on your system. If you can do global control, which is a bit idealistic, you can in principle preserve the Heisenberg limit, or this n-squared scaling of quantum Fisher information. If you unfortunately have only local control, you are doomed to linear scaling, but you can improve by a constant factor. And with this, I would like once more to thank you all for inviting me to speak here. I wish I could come to India, and I hope we can meet soon. Although let's say that 2022 is a bit turbulent, but fingers crossed that pandemic will slowly allow us to meet in conferences soon. So thank you once more for the attention.
Thank you, Jan. Thank you for the very nice talk. Questions? Anybody in the audience?
Hello, can I ask you?
Yes.
So,
Yes.
you consider SLD Fisher information. Why you did not consider RLD Fisher information?
Sorry, I didn't get the last.
You consider SLD Fisher information. Usually, you can consider maximization of the SLD Fisher information. So this one gives us somehow Heisenberg scaling limit. So why you did not consider RLD Fisher information? RLD.
The right logarithmic derivative.
Yes, right logarithmic.
Yeah, so I mean, as you know, okay, so basically, as you know, that only, okay, this is a kind of technical question, but I'll try to put it in 3 sentences. In this work, we would like to find achievable quantities. In particular, we know that only the SLD Fisher information is achievable.
Yes,
so this was the
but
okay.
Optimization of SLD is not so easy. Usually quite difficult. But optimizing the RLD satisfies the additivity. If
yes, but okay, but our motivation was different.
There is no Heisenberg scaling limit.
So, okay, RLD will be, or maybe like this, RLD will give you an upper bound, right?
Yes.
And so it could be, which probably you also have the intuition that this is not true, that it could be in this no-go theorem, the RLD scales quadratically, but the true limit scales.
No. RLD never has a quadratic. I already know this part.
Yeah, but
very important result. RLD satisfy only linear scaling.
Sure.
Exists.
So okay, so
Heisenberg scaling, in that case, maximum RLD bound becomes infinity. So using the RLD, you can easily distinguish the scaling, Heisenberg scaling or a standard quantum limit scaling.
Okay, so basically, so I'll be very, very precise. Basically, your question is to the rest of the audience, could we get this bound in a different way? And I agree. Probably you could obtain this upper bound, which is written here, by using different techniques of upper bounding quantum Fisher information, which is defined based on SLD. In particular, you could use the techniques of RLD, for instance.
Yes,
however, as I know this, unfortunately, RLD will not give you the tightest bounds. So, as you may kind of expect, we just try to use the tightest bounds on the form, on the market. And here we use this, I think this stems from Fujiwara works of upper bounding with the Krauss representations. And I'm pretty sure that maybe the derivations that we give this constant factors, probably they can be done in different ways, like using RLD. And and surely there are many different ways of upper bounding quantum fish information, but okay, we use the best thing on the market. So okay, I mean, so I agree with you that RLB fish informations are interesting, but in this particular work that would be useful in this part, and this maybe will give you some different ways of deriving these constant factors that appear here. And well, it's an open problem. Maybe in some cases, depending on the noise of the measurement, they'll maybe more tangible to the reader. So thank you for this comment. This I do not know.
Maybe I can show you my paper. So this paper proves the additivity of the RLD, maximum of RLD.
Yes, I think I know it, but
yes,
but,
maybe yeah. So maybe yeah, we can do this discussion in a different way,
sure.
maybe email or something.
Yes.
We go to the next question if there is one. Any other question? Anybody? Yeah, so can I ask one question? So you when you showed this experimental part in this Winelands experiment, you showed these Poissonian overlapping Poissonians,
yes.
and you told us about this the somewhat intuitive experimental strategy of putting the sort of the imaginary barrier in the cusp between the Poissonians.
Yes, this is this threshold method. Yes.
Yeah. So but is there a way to sort of understand why that is not the real optimum?
Yes, it's just from the overlap because. Okay, maybe I'll just go forward. Basically, your question is exactly to the point. It's basically this. First of all, if these Poissonians were not overlapping, then this would be an ideal measurement, right? So it is not optimal because in the real experiments you'll measure some number of photons, say 30 photons, no, and then according to this model, because it's above the threshold, you will say it must have come from the blue distribution or the state I measured was 1. But there's still slight probability that the state was actually 0, and you actually measure it in this tail of this Poissonian distribution, right? So this is why you get this bit flip error. Basically, you have two coins and you think it was tails, but it actually was heads. And there was some bit flip error that depended on this overlap of the Poissonians, right? But from the perspective of experimentalists, I mean, they don't want complicated inference techniques, so they are mostly happy with doing this and accepting these errors. This is what I understand from these papers.
Okay, thank you. Are there other questions? Yeah, so otherwise we thank Jan. Thank you, Jan. And we go to the next speaker. I see Miha already. Hi, Miha. So we have. So Jan, could you? Yeah,
I've just done it.
Okay.
Thank you once
So
more.
Miha, maybe you can share the screen.
Okay. Just a second. Yes.
Yes. Go to the first slide and
Let's go to the first slide indeed.
And full screen.
Okay.
Yes. So we have Michał Hordecki with the next talk. Michał.
Hello, everybody. Thank you very much for having opportunity to speak in this conference, and I apologize for not appearing at the proper time. My talk is about joint work with Robert Icqif, Martin Łobejko, Gerardo Suarez, and Marek Winczewski. Here you can see them, and they work all in ICTQT, our newly founded institute. And I want to talk about two properties of quantum open system description, which should be kind of which we want to have at the same time, namely positivity and proper equilibration, thermalization properties. So in general, quantum open system is the system which interacts with some large reservoir, and I will assume that this reservoir is just it is a single bath with some given temperature. And we also assume that the coupling between this system and reservoir is weak. This is so-called, here it is just parameterized by this lambda, and later we will talk about weak coupling regime and explain what is it. The reservoir is usually large, and of course we cannot solve Schrödinger equation for the whole system. That's why we need to have approximate description of the system itself. And it's usually provided in the form of master equation, where this LT is some generator in general time dependent. So here are two properties that we require, at least there are many others, but we require from such an approximate description. Namely, first of all, we would like to have probabilities of measurements of outcomes on such a system non-negative. And second, we would like to satisfy the basic Thermodynamics law that the system finally should simply relax to thermal equilibrium. And the positivity is equivalent to the famous Gorini, Kosakowski, Sudarshan, and Lindblad form. So when the generator has this form with this matrix being positive semi-definite, then we know the evolution will be completely positive, and it's vice versa. There is an interesting article about the history of this result by Kruszczyński and Pascasio, and in particular they say that indeed these results by Gorini, Kosakowski, and Sudarshan, and independent by Lindblad, they were submitted almost at the same time, like March 19th and April 7th, and published also within a month distance. So here is an historical photo of those three guys, and I do not have a photo of Goran Lindblad from the time, so I just took the present one. Okay, so let's pass to so that's about positivity. So we kind of know how the master equation should look like to preserve positivity of the density matrix. Now, how about the other requirement? So thermalization. For a long time, the state should reach a thermal equilibrium state. But now we should ask the question, what is equilibrium state? So we have joined the total Hamiltonian of our system H0, then of reservoir HR, and then here is the coupling between system and reservoir. So the first, like zeroth up to zeroth order, we would like to have that is the equilibrium state would be just the Gibbs state according to the H0, according to the Hamiltonian of the system. However, we understand that if we wait for a long time, this total system plus the bath should reach the total Gibbs state, right? And therefore the state of the system is not necessarily equal to this bare Gibbs state, but we should just partially trace over the reservoir the total Gibbs state, which is here, where this Hamiltonian is the total Hamiltonian. And in this way, but we can, of course, also, when we have so defined equilibrium state, which we believe that true dynamics would indeed tend to this state, we may associate with this a Hamiltonian and pretend that it is a Gibbs state to that Hamiltonian. And this state is called mean force Gibbs state, and the Hamiltonian, whose Gibbs state it is called mean force Hamiltonian. Just a second. And this mean force Hamiltonian differs from the original system Hamiltonian, and here by delta HMF we denote the correction. So now you see here the this expected equilibrium state is given by this. Here I still have partition function for the original one because we have some there is some gauge freedom, namely you can add a constant to the HMF and it will not change anything if you not just normalize it. So you can choose this more or less. So it just fixes the gauge. So there is a nice review article about this mean force Gibbs state and dynamical properties of the open system description here. So that's about our second postulate is that the states should equilibrate to this one. Okay. So now let me move to what kind of master equation do we have on the market, and there are essentially two kinds of master equations that are used very often. The Bloch-Redfield master equation and Davis master equation. Both are of the following general form. So here is the Hamiltonian of the system as interaction, but then there appears a term that is that comes from interaction with the reservoir. So there is some correction. That's how usually it is in the literature, that you add here this correction. There is a different also view where you shouldn't do it like that. But maybe since it's very widespread at the moment, I will not just go into that issue because it's anyway something to sort out, and it requires separate discussion. So typically you have here, when you derive the master equation from this total Hamiltonian description, you get here some dynamical correction to the Hamiltonian, and you have here dissipative part, and dissipative part now we consider weak coupling regime means that we only care about terms up to lambda square, where lambda is coupling constant. Usually in this description, the lambda is first order, just lambda, it disappears. It's about proper centering just. So here you may have, so this is a first order, but it will usually you'll put it 0 by just proper centering the operators of the interaction. These are okay. So this is dissipative part, and later now I will describe it in general without yet referring to particular master equation, but just this general form. So I repeat it here. The Hamiltonian correction, as I said, it will be in second order. It will be of this form, where these A's are jump operators, and they typically they describe jumps between the levels of the Hamiltonian of the system. So the dynamical correction is described by this coefficient, and the dissipative part is described by this coefficient. Because these guys are just fixed by this coupling operator A alpha and the form and the Hamiltonian H0, because these pi i's are the projectors onto eigenspaces of H0, which I didn't write here. So A alphas are fixed. And in this more or less, in this very general form, we have these two parameters, the parameter, this upsilon or curly y, it describes the Hamiltonian correction, and the gammas that describe the dissipative corrections. Dissipative part. Good. So now I explicitly here only took this second order correction because that's in this regime. This is important. The other vanishes, and the larger orders we do not take into account. And now let me describe how these two well-known master equations look like in this framework. So we need such a quantity which is refers to autocorrelation function of the reservoir, and it is something that it's some, like, so to speak, a partial Fourier transform, like half Fourier transform if t goes to infinity. But now t is just, for a while t is t, it doesn't go to infinity, so this is some function that somehow accounts for the reservoir properties. And we also denote by where here, this R alpha of us is just the evolution of these operators in interaction picture. So now Bloch-Redfield equation has the following expressions for those relevant upsilons and gammas. So this say Hamiltonian. So this is which is relevant for the Hamiltonian correction. It's given in this way by gammas. We can also this we also denote like that for the future purposes. And the dissipative part is equal to this. So it's if omega is the same, it's like imaginary and real value of this gamma. Now what happens now? Let's pass to the other master equation, Davis GKLS. We add GKLS because this equation is completely positive, so it satisfies the condition of Goryny-Kosakowski, Lindat, and Sudarshan. So how you get it? You get it by applying to the Bloch-Redfield equation a secular approximation. And then these coefficients become time independent and becomes much simpler. And so you finally have just such a, I didn't write maybe nicely, but then this S is indeed the imaginary part of gamma, and then this small gamma is real part of capital gamma. So what are advantages and disadvantages? So Davis GKLS master equation is completely positive, as I said. However, and it's extremely widely used in the regime where indeed it works, especially in quantum optics. Though it fails to describe dynamics for nearly degenerate levels. So, for example, in quantum optics, usually we have these big frequencies, and then it works very nice. Moreover, it's Markovian, so it will not describe some subtleties in the dynamics, some non-Markovian subtleties. Bloch-Redfield master equation is more accurate than Davis GKLS, just because you can derive GKLS Davis from the Bloch-Redfield. So, and it better describes some nearly degenerate levels where it's non-Markovian, where it really and Davis cannot do that. So, but however, it's not completely positive, so it may not preserve positivity. Okay, so that's this short characteristics of those two equations. So now, how about equilibration postulate for this for those two equations? So as we said, in true dynamics, the state of the system should approach mean force Gibbs state. It's also very useful to talk not about the states but the Hamiltonians, because we imagine that the state is a Gibbs state to some Hamiltonian, and then we can talk about Hamiltonians. So people define mean force Hamiltonian, and people also define steady state Hamiltonian. So in a weak coupling regime, we would like to have the following, that is steady state Hamiltonian, namely, so we imagine that the steady state is a Gibbs state to some Hamiltonian, and that Hamiltonian should be equal to the mean force Hamiltonian. In this way, we in this way, the dynamical property of the mass equation matches what we know that in true dynamics should be true, should hold. But because our mass equations anyway are up to second order, that's why it's reasonable to require just up to lambda square term. So Davis-Jacques equation, the steady state of it is just Gibbs state of H0. So we see that it's maybe 0th order. It's good in 0th order. For Bloch-Redfield equation, people, there is no up to now general answer, but for typical couplings, the postulate is satisfied for off-diagonal elements. So indeed, for off-diagonal elements, for some particular couplings, like via sigma x to bosonic field, or maybe in some other cases, indeed this is satisfied. In general, there's no general answer to that. And also it was noted that there are problems with diagonal elements. So it's for diagonal elements, there's problem with second order. Up to 0th order is fine, but second order is not yet resolved. And there is indeed a lot of literature on this problem. That's I pasted from the review paper that I mentioned, and here are some papers that treated this issue. So mostly like 10 years ago, but now there is some renewed interest in this year, and there is also some other papers that I didn't put here. So what's kind of state of art at the moment is that even for diagonal elements, even for I would say for off-diagonal elements, it's not known whether the equilibration postulates hold in general for Bloch-Redfield. Okay, so for general coupling, I mean, it's for this abstract coupling that I use in this paper, rather than for just particular couplings for bosonic waves and so on. There is also no general expression for and why? First of all, there is no general expression for second order mean force Hamiltonian, right? So we kind of do not have a general expression for this expected equilibrium, thermal equilibrium state. Okay, but that's one thing. But the other thing is that Bloch-Redfield is not completely positive. So we have a problem that we do not have a completely positive mass equation that would satisfy equilibration postulate. As if up till now, we do not know this. So we are in the scala of bad thermalization or Charybdis of lack of positivity. We do not have an for a while evolution that would satisfy both. Good. So in this talk, I would like to present some progress towards bypassing this opposition that we face. So concretely, we have obtained the general form of correction of this second order correction of mean force Hamiltonian for arbitrary coupling, right? So for the coupling, the abstract coupling that we have in this paper, in this talk, we have proved further that for off-diagonal elements, the equilibration postulate holds for Bloch-Redfield in this general picture, still off-diagonal, but now in most general coupling. Provided we have also provided the description of open system dynamics for again for off-diagonal elements where positivity and equilibrium postulates are reconciliated. So we propose we just look at a different description of open systems, which is given not in terms of mass equation to begin with, but in terms of like evolution already. So it's exponent to some generator. So later I'll show you. It's introduced in 1989 by Robert Icqif, and it turns out that leads to master equation that up to second order is just the same. It is up to second order. It is just Bloch-Redfield equation, right? So it differs than Bloch-Redfield in the upper orders, and therefore it is completely positive, and it has the same steady state as Bloch-Redfield, and therefore it has the same steady state as the mean force Hamiltonian. So this is already a partial success. For off-diagonal elements, we've been able to reconcile these two postulates. Let me make a, okay, so now let me go into more detail into these results. So first of all, let me just define this, how we get this steady state Hamiltonian. Okay, we write our general master equation. This is for general, so we do not now care what is this and what is here. We write it, and what's for the steady state, we require that this that this derivative is equal to 0. And if we solve it, then we write solution in this way, and we take the limit for t equal to infinity. So in this way, we recover the steady state Hamiltonian correction. Oh, I should divide it by here by z0. I forgot. Okay. So that was about steady state Hamiltonian. So this was the definition. Now, I would like to compare those for general master equation. So far, also, we didn't in literature you wouldn't find the general form of mean force Hamiltonian. So we have. Let me now say what, and we also have found it. So before I describe the theorem, let me now put in order 3 Hamiltonians that appear, 3 corrections. So the first one, which we denote here by ST, steady, is the one that describes steady state, the way I just shown here. And it is about the dynamical properties of the master equation. It shows to where what is the equilibrium, to what state it equilibrates for long time. Then we have thermal equilibrium state, which is not related at all to master equations. It's just describe thermal equilibrium state, and it's derived from the total Hamiltonian. This is mean force. This is derived from just partially tracing the Gibbs state for a total Hamiltonian. So that's static quantity. Is where I shouldn't. Why it's just a second. It's static. It shouldn't be any t here. It shouldn't be any t here. It's just static. Sorry. Then we have a Hamiltonian correction master equation. So we have simply this dynamical term in the commutator. So H0 plus this dynamical. So yeah, so our main question is whether these two are equal. Before doing this all stuff, we were thinking that maybe this also should be equal to those, but somehow it is not, and that's some funny thing that that the dynamical correction is not. But we think that mostly relevant is these two things. So that indeed we equilibrate to something. We equilibrate to something that is derived from the static picture, and we have proved the following. So we consider this general coupling that we have. For this arbitrary coupling, we this describes the correction for the steady state, and this describes the correction for the dynamical part, and we have such an equality. You see, these are the dissipative. These are the parameters that derive that describe dissipative part. So that's the difference between the steady state and the dynamical Hamiltonians. This correction, second order correction. Also, we have computed the general form of mean force correction, second order. and it's in this form. Where you see that these guys were appearing in the Davis equation, in the Hamiltonian correction in the Davis equation, and these and this is for time going to infinity, the dissipative parameters in both in the Redfield equation. Okay, so now I repeat here this theorem, and we looking at those, we can immediately obtain that for the Redfield equation, indeed these two Hamiltonians are equal. I say Hamiltonians because these parameters describe the Hamiltonians. So for off diagonal, we have general result for the Redfield equation. It covers the previous more particular cases proved in literature. Although we have it for different omegas only, and that relates to the fact that we only can control off diagonal terms in this second order. It's funny that for Davis equation we get that this steady state is actually dynamical. This also would like to have, but like it seems that more basic is this. So we prefer here Redfield, rather than Davis. Okay, so one thing is at least sorted out, that in very generally for Redfield equation we have this equilibration postulate satisfied up to second order. Well, okay, for off diagonal terms. Now, so as I said, we have computed general mean force Hamiltonian correction in second order for arbitrary coupling, and we have shown that equilibration postulate for Bloch-Redfield is satisfied for off diagonal elements. Now, what about complete positivity? Well, the problem is that Bloch-Redfield is not completely positive. So what we shall do, how we can reconcile these two things, complete positivity with equilibration? It's one would like to have something else. And there is something else actually, but a little bit work has to be done. It's not for free. So that's the equation derived by Robert Icqif in 1989. And it is already in this form. So you do not write master equation, but you just have a generator which looks like this, which looks like kind of similar like as in master equations. But you put it directly to the exponent. Okay. And here, this correction is precisely the same as in Redfield. You have here integral just because you are here on the exponent. So if you change it into the master equation, you would see that you just regain this dynamical correction. And okay, and here this in this dissipative part, that's the form of the coefficients. So this, so by this you can, it is as useful as master equation in the sense that you can compute from its evolution if you wish for some systems. It's completely positive. Unlike the Davis, it works well also the regimes in the regime of near degenerate levels. So here it's as kind of as good as Redfield, and it does not involve secular approximation. And this is what really, people complain that after secular approximation, you lose some information and lose some interesting phenomena. So similarly as in the Redfield, you here do not do that. So you do not lose. A digression here is, namely, we have recently used this cumulative equation. Let me say that it was also discovered independently by Rivas, but I didn't put dates here. It was just a couple years ago, and he developed it nicely. And also there is a very interesting article about thermodynamics in such a situation where we do not have Davis master equation where thermodynamics is so easy to formulate. But if you have this kind of equation, how to formulate all the thermodynamics laws. So in a usefulness of this equation shows, the digression shows in this particular situation where we have some near degenerate level. Here it's not in this picture, but here already you see it's. So suppose these two levels are close to each other, then for those two frequencies you can make secular approximation, but for this you shouldn't. And for short times, people know that for short time you can describe it by a Markovian mass equation, but with a different mass equation than for long times. And for intermediate times, you cannot use or Markovian mass equation because these must be non-Markovian effects. And this cumulant equation was found to nicely interpolate between those two regimes. Actually, in this situation, we've drawn here the Davis equation, which should work for this late times well, and the other mass equation that should work for the initial times. Much smaller than this one over delta omega. And then the cumulant equation was shown to nicely interpolate. So for short times, it behaves like that one mass equation, and for the other as the other mass equation. But of course, the main point of this paper was to do renormalization. Well, some regularization that removes the problem of divergences due to cutoffs. So there is some other story that I do not in this talk I do not touch. So I assume that I assume that there is no problem with cutoffs. That we simply have cutoffs. Like here we were able to face the situation where we do not have cutoffs, and then we want to have finite values. Okay, but that was the digression. So let me come back to how we want to reconcile this complete positivity with equilibration. So first of all, to be able to analyze the steady state, it's good to go to the master equation form. So what one has to do, one has to simply take derivative of our of this thing, and because this generated depends on time, then it's not so. Then you have to have some more complicated formula when you simply take derivative. Here you see that's the derivative of this generator, but also you have this ugly integral. And this is in the Schrödinger picture. So let's denote it by a cumulant generator for the master equation, LC. And the nice thing is now that if you compute this derivative, then it turns out that this is just the generator. This master equation is in the, just a second, tildes are in the interaction picture, but yeah, so this total equation is in the Schrödinger picture, but these k's are taken in the interaction picture here. So if you take this derivative, you just get the generator of the Bloch-Redfield in the interaction picture. So now you see that this master equation, its k is of order of lambda square. You see it has lambda square in it. So now this master equation have all orders. That's why it's cumulant equation. So it just takes second order, but it then because it's exponent, it builds all the orders out of this. So this is reminiscent of the cumulant equation in the for Gaussians, where we know that all the moments can be recovered from just second moment. So here, but we want to get a steady state only up to second order in lambda. So we expand this, and of course in second order we just take only zeroth order expansion out of these exponents. So we are left with the Redfield. So we are left with this, which is Redfield, Bloch-Redfield generator in interaction picture, but then we have here these terms that makes it just the generator of Bloch-Redfield in the Schrödinger picture. So in this way, we have so the cumulant equation is completely positive, and up to second order in lambda, it gives the steady state that is right one, which is equal to min force. But as we said, we base on this Bloch-Redfield calculation, where and also yes, where we cannot, we have problem with diagonal terms. Let me mention maybe one. Yeah, so let me just now summarize the talk. So we have provided general formula up to second order for mean force correction, which describes thermal equilibrium state. So that's a static property, and we have a nice, neat general formula for arbitrary coupling. Arbitrary coupling, not in it's weak coupling limit, so we just second order, but it's arbitrary in the sense that we have just abstract coupling, like some not some particular physical coupling to some bosonic buffer or something like that, but just completely arbitrary. We have provided relation then between steady state corrections, so the mean force corrections, and dynamical corrections for general master equation. So for this very general form that I gave you and that I showed, and for off-diagonal elements, we have reconciliated the requirements of positivity and equilibration by means of a cumulative equation that to begin with is already evolution, it's not master equation, so but is equally useful and gives the and here it's really reconciliate these two requirements. It is completely positive, but up to second order, its master equation agrees with Bloch-Redfield. The cumulative equation is derived independently of Bloch-Redfield, so these are not like they are neither is reducible to the other one by some approximation. Well, it is always, but one does not know which one is better. So how would further work? As I said, we didn't care about divergences. So without cutoffs, our formulas are often divergent. This is like ubiquitous in the literature. Nobody cares about cutoffs, where some people really put them by hand, or there are some natural cutoffs sometimes, but whether they are applicable, this is also this is disputable. So we so because we already work on that subject regarding cumulative equation, maybe it's also some future work to be done to look at all of that from this perspective. Second thing, we haven't performed renormalization. That is, we said that, oh, in the master equation, we have some additional dynamical term, which is the lamp shift, and we have bare Hamiltonian plus this additional dynamical term. Okay, I can discuss it later. One should rather have in this dynamical term the physical Hamiltonian that is measured, and one shouldn't have this. And the dissipative part should be based on the bare Hamiltonian, but rather on this physical Hamiltonian. And this issue we completely disregarded here, but it's worth to also consider. Last but not least, there is a problem with diagonal elements, simply because, as it was noticed in literature, it requires fourth order. And we have went into this fourth order, and we noticed that most likely there will be no good limit for the statistic. So simply we found some, it's not yet maybe finished, but it's very unlikely that we'll get something that is has a good time limit. And therefore, yeah, and that's something which we do not understand well, what to do with that, what is the physical significance of this. Because the true equilibrium state must be this mean force Gibbs state. It would be very like it is, because otherwise one presumably could draw work from the single heat bath, such things. So there in the literature there is some approach to get diagonal elements just by taking limit case. So you just take the two levels and you approach, omega to approach to omega prime. Yes, and in this limit one gets something. But and in our case, if we do that, we also indeed get the proper. So we take a steady state. Yes, we do this limit and we obtain diagonal elements for the steady state, and then indeed they are equal to the mean force. So in this way, we have it, but we don't like it because that's not really physically well motivated to do that, because who knows, we take this limit may not commute the long time limit and the limit of taking close and closer levels. Okay, thank you very much. That's it.
Thank you, Miha. Questions? Are there any questions? Hello. Yes, so Miha, so I have one question. It's about this in this block rate field. So maybe I missed something. So how was this? Why was this complete positivity lost? Was it because of some approximation, or was it because of the initial entanglement between the system and the environment?
Rather the first thing, because block rate field is very quickly obtained by just cutting Dyson expansion. So you just write Dyson expansion in lambdas, you cut it, so this is born approximation, yes. And already, and then you make just I think one more approximation, which is called there's one more approximation. And that's it. Yes, so simply when you build the master equation, you have to do some additional work to make it completely positive. You do not get it for free by just approximating the full dynamics. How it's done in Redfield. Redfield is very, very fast. You just end up, you just cut it, and almost immediately you get Redfield, right? It's while the Davies. So to get complete positivity, you have to do more approximations, yes, even more, just to get complete positivity. So this is the secular approximation, right?
Nice. And in this for this diagonal elements case, this there in your slide here that you said that there is no good limit. What type of limit are you talking about?
Because we want of steady state, so we take a long time, and we want to see, the rho of t, yes. So and it should go to some unique steady state. Okay, and for if you look at second order correction for that off diagonal, you just see that indeed they become time independent, yes, and you say, okay, that's my steady state. But for this diagonal terms, you have some oscillations. Always, it's not yet fully confirmed, but this is what we unfortunately expect. So then I don't know. Maybe then I don't know how to interpret. Yeah.
Any other question? Well, if not, thank you, Miha.
Thank you.
Thank you. And we go to the next speaker. Next speaker online. The next speaker was Lorenzo, right?
Hi, yes.
Yes. So can you share your screen?
Yes. Okay, can I start?
Yes. So the next speaker is this, as is Lorenzo Catani. Yes.
Okay.
Please start. Yes.
Thank you. So, of course, let me start by thanking the organizers for putting together this very nice conference and for giving me the opportunity to present my work. This is a work which is in collaboration with Matt Leifer, David Schmidt, and Rob Speckens, and you can find more about it in the archive. Basically, it is about disputing the common claims that quantum interference phenomena capture the essence of quantum theory. So here is the outline of what I'm going to talk about. I'm going to start with the motivation, and then I'm going to describe the basic phenomenology of interference in the setup of Mach-Zehnder interferometers that is traditionally regarded as problematic, in the sense that it is usually associated with some interpretational claims that characterize this phenomenology as somehow mysterious. Then I'm going to provide I'm going to describe the toy field theory, which is a classical statistical theory that reproduces this phenomenology while explicitly rejecting the interpretational claims. At the end, I'm going to spend a few words on which aspects of quantum interference are actually a manifestation of something that is a manifestation of a departure from the classical worldview. Cool. So the motivation behind all these kind of works is really to try to understand what is inherently non-classical about quantum theory. In particular, in this work, we focus on quantum interference, as it's quite common to claim that somehow quantum interference really captured what is inherently non-classical about quantum theory. In particular, I wanted to start with this very famous quote from Feynman when he introduces the two-slit experiment in quantum theory. And it says, it is a phenomenon which is impossible, absolutely impossible to explain in any classical way. It contains the only mystery. In telling you how it works, we will have told you about the basic peculiarities of all quantum mechanics. So basically, you can see the purpose of this work is really to dispute these kind of claims that the basic phenomenology of quantum interference resists an explanation in terms of a classical worldview. So the first question really is, so what is considered to be mysterious about quantum interference? So in order to do that, let me first describe the basic phenomenology of quantum interference. And I'm going to do this in the experimental setup of Mach-Zehnder interferometer that I guess many people are familiar with. So basically here the story is that we have at every run of the experiment a photon impinging a 50-50 beam splitter. After that, in the two runs of the interferometer, we put on the right arm, we put a phase shifter, and we assume that it can only make shifts of 0 or pi phases. Then there are two mirrors, or nothing really happens. And then the two arms reconvene in a second 50-50 beam splitter. After that, we have the two ports, the left and right port, where the photon can output. So let me stress again that we only consider cases where the beam splitters are 50-50 and the phase shifter can only do a 0 or pi phase. And the reason is that this is enough to reproduce the phenomenology of quantum interference that is traditionally regarded as problematic. So we don't need to consider something more complex. The other like operating mode, let's say, of the Mach-Zehnder interferometer is where instead of the phase shifter, we place a which-way detector on the right arm that is just going to tell which way the photon passes through. So now let me provide the quantum mechanical description of these two cases to see what is this phenomenology about. So I'm going to use the second quantized description. So where basically we associate a two-dimensional Hilbert space to each of the modes. In particular, so we use the Fock space formalism. So the initial state of the system is going to be the state 1, 0. So where basically this says that the left mode is occupied, where the right mode is not. Then we apply the 50-50 beam splitter. Here it means a unitary that maps this state to an entangled state of the two modes. In this case, first we consider the case where the phase shift is 0, so nothing happens. The state before the second beam splitter remains the same. We apply the beam splitter, and what we get is the state 1, 0. So basically, all the times the left port is the one that is gonna fire. Okay. Cool. Let us try now with the phase shifter applying a shift of pi. So at the beginning, we have the same situation. Then we apply this phase shift on the right mode, which means basically to flip the phase of the right mode. This results in a shift of the relative phase. So we have this other entangled state before the second beam splitter. We apply the last unitary and we obtain this other state. So basically, all the times we have output the right port. So you see, both these two cases were cases where we have like a maximum of the probability on one port and a minimum on the other. So basically, this is like a manifestation of constructing and destructive interference. That's why we say that this scenario really says that if you want, the quantum system behaves as a, shows a wave-like behavior. Okay, if you're familiar with the two-slit experiment, this is like in the two-slit experiment where you don't place any which-way detector and then you just witness an interference pattern in the screen at the end. Cool. So the other operating mode of the Mach-Zehnder interferometer is one where we put a which-way detector on the right arm. So let us describe this. So at the beginning, the same situation as usual. Then let us imagine now that the which way detector tells us that there is nothing detect on this path. So basically we post-select on the outcome 0, okay, on the right mode is not occupied. According to the rules of quantum theory, we collapse the state to the state 1, 0. So before the 50-50 beam splitter, that's the state we have. We apply the beam splitter, and what we end up having is a disentangled state of the modes, which means that half of the time you're gonna experience the left port to fire, and the other half of the time the right. So in this case, you see we don't have a maximum and minimum of interference if you want, but the probability is uniform, and so this is associated with a particle-like behavior. Okay, so in the two cases, the quantum system seems to behave sometimes as a wave, sometimes as a particle somehow. So just to say that with these two scenarios for the Mach-Zehnder interferometer, we can reproduce the phenomenology that is traditionally regarded as problematic. What do we really mean with this? We mean that this phenomenology is usually associated to the claims that say that quantum interference is somehow mysterious. So let us see these claims. So the first one is this wave-particle complementarity. So I already said it. It seems like that sometimes a quantum system behaves as a wave and sometimes as a particle. And you know, this really seems to be a manifestation of a departure from classical physics, because in classical physics, waves and particles are very two distinct entities. Instead, here it seems that the quantum system is somehow like a schizophrenic kind of entity that sometimes toggles between being a wave and sometimes a particle, without a possibility of a unified description of it. The other thing is the observer dependence of reality. It really seems that depending on what the observer decides to measure, then you know, the quantum system is a wave or is a particle. So it changes between the two entities depending on what the observer decides to measure. Lastly, it seems impossible to provide a local explanation of this phenomenology. Think, for example, when I don't know, let's say that the photon passes through the left arm, then how can it know if on the right arm there is a which way detector or not? It seems that it must know, because if there is a which way detector, then the photon ultimately can output in either of the ports. But if there is not, then it's going to always output on one port. So it really seems that there is like some kind of instantaneous causal influence from one arm to the other. Some other people try to explain it by saying that there is a backwards in time causal influence from the ports to the photon, and some other explanation. So we put all of this in the category to say that it seems impossible to provide a local explanation of this phenomenology. Okay, so now what I'm going to do is I'm going to describe the toy field theory, which is an alternative theory to quantum theory that reproduces the trap phenomenology, the phenomenology that is traditionally regarded as problematic about quantum interference, while explicitly rejecting these three interpretational claims. Okay, so I'm not gonna provide all the details about the toy field theory, but only what is the general scheme and how we apply it in our scenarios. Okay. Okay, so the toy field theory. So first, let me. So the way we define it is first to define what is the classical physical theory associated with it, meaning what are the systems of interest here. So the system here are two field modes, so the left and the right mode. And these systems at every time have well-defined properties that are occupation number and phase. So these are always well-defined simultaneously, okay? We denote them with n and phi, and they can take values either 0 or 1 each. We also assume that we are in the case where the sum modulo 2 of the occupation number is 1, meaning that either the left mode is occupied or the right mode is occupied. The dynamics in this theory is deterministic and local. And now, after defining the classical physical theory, we define the statistical theory associated with it. So we assume that it's possible that we don't know what are the physical states or the properties of the system. And so we describe this with some probability distribution over those. This is like when you define Liouville mechanics from classical Hamiltonian mechanics. This is all like standard. The new ingredient is that we also assume that there is a restriction or a constraint on what are the possible statistical distributions in this statistical theory. This is called an epistemic restriction that basically says what is the restriction on what one can know about the physical states of the system. And in this case, for example, for a single mode, it just reads by saying that no agent can have knowledge about more than one property. So either one knows the occupation number of a mode or the phase or the relation between them. But about the rest, the observer is completely ignorant, okay? So in short, the toy field theory is a classical statistical theory with epistemic restriction, and particularly this kind. It's like it's a statistical theory on discrete fields. Okay, cool. So let's see. This maybe was a bit too abstract. Let's see how it is in concrete terms. So you remember the input state of the Mach-Zehnder interferometer in quantum theory was 1, 0. In the toy field theory, this would be the state where we know that the left mode is occupied, the right mode is not, and we are completely ignorant about the phases of the modes. So associated to the quantum state, in quantum theory, there is this state of knowledge, okay, consistent with 4 possible physical states in the toy theory. How does the beam splitter works? Well, in the toy theory, it just follows the simple rule that we call the swap rule. So every time we have a beam splitter, what it does is it just swaps the value of the occupation number of left mode with the relative phase, which is just phi L plus phi R modulo 2. So in modulo 2 arithmetics, the sum is equal to the difference. And it's just that it leaves all the rest the same. So let's see it in action. So you remember this was the first stage of the Mach-Zehnder interferometer in quantum theory. In the toy field theory, we started with this state where we know NL is equal to 1 and R is equal to 0 and the rest is unknown. The swap rule just says that the value of NL becomes the value of the relative phase. And of course, we also know that the sum of the occupation number is always 1. This is true always. So now, just to soften the notation, let me call this state of knowledge associated with these values the notation NL equal 1, and the one about the phase, the relative phase being 1 is delta phi equal 1, just for softening the notation. Now, having this in mind, we can reproduce the phenomenology of the wave-like behaviors. You remember this was the description in the quantum mechanical terms. Now in the toy field theory, we're going to start with the state, which is knowing that the left mode is occupied. Then we apply the swap rule because we have the 50-50 beam splitter. This is going to maps to the state of knowledge where we know that the relative phase is 1. So the physical states have phases that are anti-correlated. Then nothing happens because we assume the case where the phase shift is 0. So it remains the same before the beam splitter. We apply again the swap rule, and look, you see that we find that the left port is going to fire. In the case where we put the pi phase shift, in the toy field theory, this corresponds to a local transformation of the phase of the right mode. So basically, it gets flips. And given that it gets flips, also the relative phase between the two modes are going to get flipped. But notice that this is just a local operation on one mode, okay? So before the beam splitter, we have this state of knowledge, we apply the swap rule, and we obtain that now it's going to be the right port to phi, okay? So we saw that we could reproduce both of the two cases for the wave-like behavior. About the particle-like behavior, let me introduce how it works, the measurement update rule for the occupation number. So basically it says that after a non-destructively repeatable measurement of the occupation number of a mode, one assigns 0 probability to the physical states that are inconsistent with the outcome of the measurement. Furthermore, the discrete phase of the mode is randomized. So basically, this update rule is constituted by 2 parts. One where you just learn, so you update your state knowing something more about in this case, the occupation number, so of the physical state. And then there is a part which is about the disturbance, okay? And this is needed in order to preserve the epistemic restriction, okay? Cool, so now let us apply it. So you remember at the beginning, we start with this state of knowledge, we apply the swap rule. Now let us assume that we measure on this arm the occupation number NR, and imagine that we get outcome 0, so we get that it is not occupied. Then the state we're going to obtain, so we're going to know that the right mode is not occupied and the left mode is occupied. But then we're going to also randomize the local phase of R, of mode R. As a consequence, also the relative phase between the two modes is random. And so when we apply the swap rule, we're going to obtain that we don't know where the photon is going to go. It's going to go with 50% of the time in one part and 50% on the other. So this is associated with this state of knowledge. Okay, so also in this case, we can reproduce the particle-like behavior. So I just showed quickly that we can reproduce the trap phenomenology of Mach-Zehnder interferometer. And basically, let me summarize it very quickly. So basically, we saw that every time you get to know which output port is going to fire by knowing what is the relative phase between the modes before the second beam splitter. So in the case of wave-like behavior, basically the relative phase before the beam splitter is always well specified because it came from the swap rule from the initial state, modulo some possible phase shift. In the case where we have particle-like behavior, instead we have the which way detector that induces like locally a randomization of the local phase of mode R. This implies a randomization of the relative phase and therefore also randomization of which output port we're gonna it's gonna fire. Okay. So and all this phenomenology is reproduced, but while rejecting the interpretational claims we said before, in particular wave particle complementarity. So the systems in the toy field theory are modes that at every time they have a wave-like property, which is the phase, and a particle-like property, which is the occupation number. But they have it at every time, okay? What changes, so the variability, depending on what we measure, concerns what we know about these properties, but not about the properties themselves that are always jointly well-defined. The observer dependence on reality. Again, what we measure informs, let us know more about one property or the other, but it doesn't say that the properties are not well defined at all times. So what is observer dependence is what we know about the reality, not the reality itself. Lastly, the failure of explanation in terms of local causes. This toy field theory is explicitly local. In particular, I think we saw well why when we put the which way detector that it randomizes the local phase of R. So basically you can imagine that half of the times it leaves it the same and half of the time it flips it. This information is propagated to the second beam splitter and only there is exchanged with the other mode, thus providing the output. So basically what was thought to be some causal, some non-local causal influence is just an inference now. It's about what's the state of knowledge. Cool, so in summary, we saw that the trap phenomenology of quantum interference can be reproduced in the toy field theory and so does not constitute, does not capture the essence of quantum theory. We can do the same also for other related experiments, Ellis-Weidman bomb tester, Willard-Ray choice experiments, and the quantum eraser. And so let me conclude by saying that the trap phenomenology of quantum interference does not capture the essence of quantum theory. With this, we also wanted to promote a more rigorous way of pursuing the research on non-classicality that should be, done by formulating proper no-go theorems. Examples of these are Bell theorem, Cohen-Specker. And then lastly, I want to say that there is still some project here to develop. And actually, I want to advertise some follow-up work we are working on, where we show basically which are the aspects of quantum interference outside the trap phenomenology that manifest a departure from the classical worldview. And this basically constitutes here a proof of contextuality. So stay tuned and thanks for your attention.
Thank you, Lorenzo. Questions? Yes, Stanislav.
I just wanted to ask whether the cosine square rule, does it also reproduce if you measure things rotated in a little bit, not by pi, but by different angles, does it reproduce the cosine square also?
I guess what you're asking is if you change a bit the setup, also allowing for non-zero and pi phase shift, if you can still reproduce the phenomenon.
Yes.
Yeah, so in general, not. Okay, and that's where we should look for like aspects of quantum interference that cannot be accounted in a classical worldview. But here the point really was to say that already the basic phenomenology of interference is enough to run the typical arguments that people point to when they say that quantum interference somehow is mysterious and capture the essence of quantum theory. So this aspect of the phenomenology does not actually constitute a challenge to the classical worldview. Instead, yes, if you consider more exotic scenarios where you get quantum interference, you can, for example, what I was saying is that we have this other result where basically you can show that these other scenarios require contextuality, for example.
Yes, thank you very much. It's very interesting. Yes, you highlight especially like common uses of interference, which are essentially not mysterious. Yes, I like it. Thank you.
Thank you.
Thank you. Other questions? So this epistemic restriction that you put, where you say that every agent must know only one property, where is it exactly used?
Yeah, so it's used in basically how it's defined. So the states of knowledge that we associate to, for example, what are the quantum states? It's defined in the measurement update rule. So that is just a consequence of this epistemic restriction. So basically, all the theory is based on this restriction. In particular,
how do you? Sorry, yeah. So
yes.
How do you? Sorry.
Okay, go ahead.
Sorry, there is a delay in the. So for example, how do you define a property? I mean, so can a single agent know about whether the particle is on the left side or on the right side, or you need two agents for knowing on the left side and for the right side?
You can know it, but if you know it, then you are completely ignorant about the phase of that mode. So what is the state of knowledge? It's just a uniform probability distribution over these physical states, and the physical states are defined by phase and occupation number. And let me also mention, maybe it's somehow useful for you, that all of this can be made very rigorously. Here I just told a story, but all of this, like for example, these properties can be written formally as points in the phase space. And the probabilities are just, uniform probabilities on the phase space. And the epistemic restriction just reads as saying that you can only know the observables for which, the symplectic inner product is 0. And where basically you can say vector.
I have a comment to make.
Yes.
Yeah. So there is a theory called Stekenstoy theory.
Yes.
There is also epistemic restriction, and that theory also reproduces so many quantum features like dense coding, teleportation, and many others. So maybe that is very powerful.
It's basically the same theory. What changes is that in this theory, like the systems are field modes, okay, and the properties that we consider occupation number and phase. But yeah, it's the same. It's the same theory.
Thank you.
Yeah, thanks for the comment.
Stanislav, you have another question?
Yes, I just wanted a short comment. Have you considered more strange classical systems that are more close to quantum ones? Like, for example, Moir patterns. Like Moir patterns, they exhibit wave-like behavior, but essentially they are like they are classical systems, and maybe there is something interesting there. I was just thinking in my meantime, that's a suggestion maybe you can look at.
Can you write in the chat what
yes, I will write.
But yeah, no, I don't know, but yeah, thanks for telling. Yeah.
Okay. So thank you, Lorenzo.
Thank you.
We go to the next talk. Thanks. Yes, I think Stanislav has written in the chat. Yes. So the next speaker is Tulja.
Hello. Yeah.
Yes. So please share your screen. Yes, we can see your screen.
Can you see my screen now? Yeah.
Yes. Please continue. Please start.
Yeah. So thank you for giving this opportunity. So today I'll be talking about our recent paper on Icqif. It's called Stochastic Approximate State Conversion for Entanglement and General Resource Theories. So this work has been done along with Alexander Stelzov, who is my supervisor, and Chandan Datta, who is working as a postdoc in our group. So in quantum information, that there are these mathematical structures called quantum resource theories, and we use them to understand specific type of quantum resources. And traditionally, they've been started with entanglement, and people also try to understand coherence or thermodynamics. You can view it as a resource theory, and many other quantum resources. So whenever one defines a quantum resource theory, one of the important problems is to understand how the state transformations in the resource theory occur, or if I give you a quantum state rho, how can you transform into another quantum state sigma with certain assumptions over the operations you can do, or certain restrictions over the operations you can do. So this is called the state transformation problem. So for formally, one can define a resource theory in this way. So when one has to define resource theory, one has to define these two objects. The first one is called set of free states. So it's a set of quantum states called free states, and then a set of quantum operations which are called free operations. So once you define these free states and free operations, you can define a quantum resource theory. So quantum resource theory is basically a tuple of free states and free operations. Additionally, satisfying this constraint that if you take a free operation and you act on a free state, you should get back a free state. So therefore, the set of free states is conserved by the action of these free operations. So if you define these free states and free operations satisfying this constraint, you define a resource theory. So let's assume you define a set of free states. You define a set of a subset of states and define them to be free states, and then you can take this set of maximal resource non-generating operations. So resource non-generating operations are the set of CPTP maps which map free states to free states. This is the largest set of CPTP maps which map free states to free states. So therefore, one can take any set of free states, and then one can define this RNG maps, and then one can define a resource theory. Or one can do something different. One can take the set of free states and define a subset of these RNG maps, and again define a resource theory. So why would one choose this resource non-generating operations, or why would one choose a subset of them as free operations? Defined on depends on sort of physical motivations, which I will show in this slide. So let's take separable states. You can take the set of separable states as a, so you say a state is separable state if it can be written in this form as a convex combination of product states. So these separable states are known to have no entanglement. No? These can be created locally with classical communication. So let's take the set of separable states. Once you define the separable states, one can define this resource non-generating operations as non-entangling operations. So non-entangling operations are the largest set of CPTP maps, which map separable states to separable states. But we see whenever one talks about resource theory of entanglement, they usually talk about LOCC operations, not about these non-entangling operations, because LOCC operations are more physical, no? Because they have a physical interpretation in terms of locality. Like if Alice and Bob are two parties separated, and they can do operations in the local on their local quantum system, then a set of operations which they can perform are these LOCC operations. Nevertheless, in this talk, I'll be mostly concerned about this non-entangling or this resource non-generating operations, because if one gives any no-go theorems by using this resource non-generating operations, then those no-go theorems also hold valid when you define a set of free operations which are a subset of RNG. So in the same spirit, one can also define stochastic resource non-generating operations as a set of so here when I say stochastic, I mean completely positive trace non-increasing maps. So epsilon is a CP map which has which is not trace non-increasing but not trace preserving. No? They're like quantum measurements. So all these CP maps which even probabilistically don't generate a resource. That means if you take a free state and then you apply this epsilon or this epsilon map, which is a resource non-generating map, we should get a free, unnormalized free state, in the sense that we don't even get a resource state even probabilistically. So this is sort of another way one can define a set of free operations, one if you allow stochastic transformations. So these stochastic RNG operations are the largest set of trace non-increasing operations which preserve the set of free states. Similar to before, again, one can define a subset of these stochastic RNG operations as set of stochastic free operations for your resource theory. So in this way, one can construct free operations for a set of given free states. Okay. So now I'll talk about measures on measures of resources. So for example, you define a resource theory, you have a set of free states. Then any state which is not in a free state, you cannot achieve by free operation, because if you give a free state to a free operation, you'll get back a free state. So any state which is not in the set of free states, we call it as a resource state. And if we would like to have some measures of resources. And when we want to say something is a measure of a resource, we want it to satisfy at least these two conditions. The first one is it has to be 0 for all free states, because free states have 0 resource. And this measure of a resource should not increase under free operations. So you take a row and you take an arbitrary row and you apply a free operation. The resource should not increase. So this is given by equation 6. And one way one can construct these measures are by using the following construction. You can take any distance measure between quantum states. And this distance measure doesn't need to satisfy the triangular inequality. It's like maybe it can be like something like 1 minus fidelity, or it can be trace distance. So you can take any distance measure satisfying these two constraints, that it has to be 0 if you take same states, and it has to be decreasing or non-increasing under CP-DP maps. So it's called the data processing inequality. So if you have any distance measure satisfying these two constraints, using the distance measure, one can create resource measures by calculating the distance of, for example, if you want to calculate the measure of resource measure of rho prime, one can calculate the distance of rho prime with a free state, and then you minimize this quantity over a set of all free states. So, and this construction satisfies equation 5 and 6. So therefore, it's a valid resource measure. As an example, one can see, as an example, one can say, let's take here d equal to 1 minus f. 1 minus f satisfies this 1 and 2 conditions, and you can create a resource measure out of it. And this is traditionally called as a geometric measure. So geometric measure is basically you take, if you have a state row, you calculate the fidelity of row with a free state, and then you maximize it over all free states, and then you do take the 1 minus of it. There are measures which are also motivated from a different sort of perspective. For example, there is this measure called generalized robustness, which is, for example, if you have a state row, the robustness of row is basically the minimum amount of noise it can tolerate before it becomes a free state. So we have a resource state. S is the noise. So what is the minimum amount of noise you can that the row can tolerate before it becomes a free state? This is called the robustness. So in this definition, you are minimizing over S and also over T, also tau. Tau is a quantum state. Now it has been shown that this robustness measure is also sort of a distance-based measure, but yeah. So one can also construct measures in different ways also. And what is one important feature of this resource measures is, so as we know from equation 6, that these resource measures don't increase under free operations. So therefore, if you have two states, rho and sigma, and the resource measure on sigma is greater than resource measure of rho, then we know that there cannot exist a free operation which takes rho to sigma. Because if there exists a free operation which takes rho to sigma, then m of sigma cannot be more than m of rho. So therefore, in this way, this resource measures give no-go constraints on things which are not possible. Okay, so coming back to the state transformation problem. So if you have two quantum states, rho and sigma, and if you say that they can be deterministically converted, which means that state transformation from rho to sigma is possible via a free operation. So there exists a free operation which takes you from rho to sigma. Then you can say that a transformation, a deterministic transformation from rho to sigma is possible. So you can consider this to be two entangled states, and this come out to be a set of LOCC operations, no? Or incoherent states, and you can consider this to be some strictly incoherent operation or something like that. Okay, but in any non-trivial resource theory, there will exist states like rho and sigma where they cannot exist transformation taken from rho to sigma. So they can exist this state, two states rho to sigma, where there doesn't exist any deterministic transformation. Well, what one can do is one can still do approximate transformations. So what one does is you take a state rho and then you act a free operation on it, take the fidelity of that with sigma, and then you maximize it over all the set of free operations. So this is the way to quantify how close to sigma you can get. Okay, well, you cannot get exactly sigma, but then you can quantify the transformation as how close you can get to sigma by using the set of free operations. So these sort of operations one calls them as approximate transformations. But here everything is deterministic. Everything you can do with probability 1, but with an error. Another set of operations which one can be interested in are so-called probabilistic transformations. So let's assume again a setting where there doesn't exist a free operation taking from rho to sigma. By free operation, I mean a deterministic free operation. Well, one can probably still attain sigma, not with probability 1, but with a probability less than 1. So these are called as probabilistic transformations. Here we don't compromise on error. We still want to attain sigma with error zero error, exactly sigma, but not with a probability 1, but with a probability less than 1. So what I mean here is one attains sigma from rho by using the so-called stochastic free operations. By using the stochastic free operations, you can attain sigma with probability less than 1. As an example, in entanglement theory, for example, you have a 2-qubit pure set or a pure set of arbitrary dimensions, and you want to achieve a 2-qubit mixed state. So you have a pure state and you want to go to a 2-qubit mixed state, no? And this is not always possible via LOCC, but you can always do it by using this SLOCC, which is basically stochastic LOCC. At the end of the LOCC protocol, you do a measurement, and with some probability you'll get an outcome, and you just take that outcome. And the optimal probability to go from a pure state to a 2-qubit mixed state is given by the ratio of geometric measures of psi by the ratio of by geometric measure of rho. So the ratio of geometric measures gives the probability of transformation from psi to rho. Of course, if this ratio goes more than 1, you take 1, because the probability has to be between 0 and 1. No? So the geometric measure is as I defined before, is basically taking 1 minus maximum fidelity of rho to the set of separable states. Here the free states are separable states. And this for 2 qubits, for any 2-qubit mixed state, the analytical expression is known in terms of concurrence of state. So here there's a mistake. The square is after C of rho whole square. And for any pure state, this geometric measure is basically 1 minus the square of the largest mid quotient. So lambda 1 is the square of the largest mid quotient, and 1 minus lambda 1 is the geometric measure of any pure state. So basically, what I want to say is the analytical expression for this is so how to probabilistically go from a pure state to a 2-qubit mixed state. So this has been shown by Vital in early 2000s. So what I'll introduce now is a general sort of transformation, which is called stochastic approximate transformation, which is sort of a more general transformation which I've defined before. So here, when I say stochastic approximate transformation, I'm interested in usually these two quantities. So the first quantity is called as FP. So what is FP is, I say that you want the transformation to occur at least with probability P, and then you say what is the maximum fidelity which you can achieve. So earlier when I defined approximate transformations, I wanted to achieve with probability 1, and then you optimize the fidelity, no? So here I sort of make the restriction a bit less and say, well, I can achieve the transformation with probability at least P, and then you want to optimize the fidelity. Basically, you take you optimize over all completely positive based on increasing maps, assuming that the transformation probability is at least P. In the same spirit, one can also define something, this quantity called as PF, which is sort of generalization of the probabilistic transformations I defined before. Earlier, when I defined probabilistic transformations, I want to achieve exactly the final state, then exactly the final state, and then I optimize the probability. No, but here what I say is I want to achieve the final state with at least a fidelity F, and then you want to say what is optimal probability. So in some sense, these two quantities are sort of dual to each other. No, if you find out this FP, you can invert that, and then you can find out PF also. So in some sense, these two quantities have the same thing. But yeah, so these are sort of generalization to the previous single copy transformations which I've described. Okay, once we have this, we have the first result of our paper, which is, so this FP and PF can be bounded by the robustness of the initial state and the geometric measure of the final state. So if you have two states, rho and sigma, and for any, you define a set of free states, no, and the free operations are basically the resource non-generating operations, so the largest set of free operations you can have. Once you have this, then I can say, if I want to achieve the transformation with at least probability P, then what is the maximum fidelity I can get? The maximum fidelity is bounded by this quantity, 1 by P times 1 plus robustness of the initial state times 1 minus geometric measure of the final state. And if this bound becomes not trivial, that means if this bound becomes trivial, in the sense that if this value goes over 1, then you take the minimization of that with 1. Similarly, you can also bound the optimal probability for a given field. So if I say that you should achieve at least with fidelity F, then what is optimal probability? And this optimal probability is also bounded by 1 plus R times 1 minus G by F. So these two conditions are valid for any resource theory. Once you define a set of free states, and these bounds hold, because this resource robustness and geometry measure basically depend only on the set of free states. As a special case, for example, if you consider in the first equation P to be 1, then you'll get this equation 16, which is basically the upper bound on the optimal fidelity you can achieve in deterministic transformations. Similarly, you can take the second equation and put F equal to 1, and then you can get a upper bound on the optimal probability you can achieve in any resource theory, in the transformation. Further, one can see that from this equation 16 that if you put rho equal to sigma, then this fidelity of rho to sigma will be 1. From there, you can attain this equation 18 with inequality 18, which is basically the inequality between the robustness measure and the geometric measure for any resource theory. So for example, so this robustness measure is upper bounded by this geometric measure by 1 minus geometric measure of rho, and this is valid for any rho and for any set of free states. So here in the slide, what I've shown is for general resource theories. Now, and these are just bounds on transformations. Now I want to show something analytical and for some standard resource theory, a concrete resource theory. So as I've seen before, we know that if you have a pure state and we want to do stochastic velocity, and the optimal probability to go from pure state to 2-qubit mixed state is given by the ratio of geometric measures of geometric measure of psi divided by geometric measure of rho. Now let's assume for this sort of scenario, we want to calculate the more general quantity, which is PF. So when I define equation 19, I want to attain rho with exact fidelity, and you are optimizing the probability. But now I want to attain rho, not exactly, but I want to go in a fidelity ball around rho. So the fidelity ball is given by F. Now I want to say what is the optimal probability. So if you see from equation 19, the optimal probability is given when the geometric measure of this final state. So the final state is not exactly rho, but in a ball around rho. So in a ball around rho, we want to go to that state which has the smallest geometric measure. So once we go to that state, the probability will be optimum. So that's how we can calculate this PF. So therefore, what we want is for the state rho, we want to know the minimum possible geometric measure in a fidelity ball. And this is sort of a continuity of geometric measure. And this leads us to the next theorem. So for any 2-qubit state rho, you can define a ball around a fidelity ball around, so given by this condition, so that the fidelity of any state in that ball with rho, this will be at least F. So in that ball, the minimum geometric measure is attained by a state, which is given by this following. The minimum possible geometric measure is given by the following expression in equation 20. So it's basically sine inverse of this root geometric measure of rho minus cos inverse of root F, and then you take the sine square of that. And if this thing goes more than 0, then you take, if the thing goes lower than 0, then you take 0, because geometric measure cannot be negative. So this equation basically gives the minimum possible geometric measure in a fidelity ball or round ball. And why do we want that? Because we want to go to that state in the ball. Then we can increase the probability to the optimum value, and that gives the value of PF. So once we have this, you basically need to substitute this 20 instead of G of rho, and then you will get the value of PF. So the maximum probability to convert a pure state psi into a 2-qubit state rho via LOCC or stochastic LOCC with at least the fidelity f is given by the following. So once you divide by once you divide by this following expression, you'll get this quantity. You need to just by doing some analytical manipulation, you can come to this following. So one basically needs to calculate this quantity m1, and if this m1 is greater than or equal to 0, it's 1, or otherwise it's given by this following quantity. And by inverting this expression, one can also obtain FP, which I've described before. And with this, I end my talk. And if somebody has any questions, you can ask me.
Thank you. Questions? So in this, I think it was the first theorem where you had you maximize the fidelity for a fixed probability and the other way around. So there was this the bounds. So do these bounds get better if you go to larger number of copies?
How do these bounds get better if you go to larger number of copies? Give me a second. So you're talking about this robustness and geometric measure bound, no?
Exactly.
Yeah. True. In many scenarios, this geometric measure sort of decreases as you go to larger number of copies, no? And of course, this one becomes more non-trivial as you go to larger number of copies.
Yes, but can you show that? I mean, asymptotically becomes an equality, or that cannot be shown?
No. Not always, but because these bounds are not very good for arbitrary. If you take arbitrary mixed state as a final state, these bounds are not very good. No, I mean, if you take a pure state as a final state, and then probably still these are not very good. But yeah, in some scenarios there are some non-trivial regions where you can compare it with other bounds. But for example, these bounds have already been derived last year, but assuming that the final state is pure, no. And they show that these bounds are not very good, even when you go to many copies also. Yeah.
Thank you. Any other question? Comments? Okay. Otherwise, we stop here. Thank you, Tulja.
Thank you.
And we go to the next speaker, which is Javid Naiku.
Yeah.
Yes. So, Tulja, if you can stop your sharing.
Yeah.
Yes. Javid, please share.
Yeah, sure. Is this visible?
Yes. Go full screen, maybe.
Okay. Am I audible? Yeah.
Audible, but
okay. Thank you.
Please go full screen if possible.
Full screen. Okay. Let me make it this way. Fine.
Yes. Please continue.
Okay. Thank you, Professor, and thanks to the organizers for arranging this wonderful conference and for the opportunity to speak here. I'll be talking about multi-parameter estimation perspective on non-Hermitian sensing. It's a work in collaboration with Yannick Kolodensky of Zend, who spoke earlier this afternoon, and Ravindra Chachlani of Adam Mickiewicz University, Poznan. It's essentially about looking at sensing properties in a system that's governed by non-Hermitian Hamiltonian, and this non-Hermicity is arising due to the open system effects. The motivation is twofold. Firstly, it's of interest to look at how the open system effects that are otherwise known to have a deteriorating impact on quantum properties in general can be used to do some useful work, and in particular quantum metrology. And there have been a few works in this direction. dealing with the single parameter estimation, where it's assumed that there is one parameter that's unknown and one wants to estimate it. But the real scenario, as I'll try to convince you, situation arises where you have more than one unknown parameters in the system and you would like to estimate them. And then one would like to ask what actually determines scaling in that case. And we'll see that the correlations among these different unknown parameters become important in deciding the scaling. And one would also see how the multi-parameter estimation affects the well-known single parameter results. So a brief and quick revision of non-Hermicity. I like to give this example by Carl Bender, where you consider a system with a total gain and you can describe it by Hamiltonian H1, where parameter B plays the role of an amplification factor in the time dynamics. And if you are a system with a total loss, net loss, then you can describe it by Hamiltonian H2, where now this B plays the role of a decaying or a loss parameter. However, if you allow for coupling between the two systems, you can describe it by Hamiltonian H3. And now you see that you can have real eigenvalues written here as E plus minus if the coupling strength dominates the gain and loss rate. Also note that the corresponding eigenvectors are not orthogonal, and at a particular point when this coupling strength becomes equal to the gain loss rate, the two eigenvalues become degenerate and the corresponding eigenvectors also merge at this point. Such points are called exceptional points, and one can have in general more than two levels and talk about an exceptional point of order n. So for an n-level system. The reality of the spectrum of non-Hermitian Hamiltonians has been discussed in this nice paper by Carl Bender and Stephen Washer, where they came up with the conclusion that you can have real spectrum in non-Hermitian Hamiltonians provided they possess a particular symmetry, which in this case is a combination of two discrete symmetries, the parity and time reversal. If your Hamiltonian commutes with this PT operation and also the eigenvectors or eigenvectors of PT operator, then you are guaranteed to have real eigenvalues. Later, these conditions were generalized and necessary and sufficient conditions were obtained for reality of the spectrum of non-Hermitian Hamiltonians. Well, non-Hermitian Hamiltonians have found tremendous applications ranging from electromagnetically induced transparency to single mode PT lasers. I'm surely missing a lot here, but what I'm particularly interested in is the sensing applications of non-Hermitian Hamiltonians. And there have been many works in this direction as well, notably by Warczyk, Ozheimer, Hodai, and I'll particularly talk about the last three works in some detail in a couple of slides. Now, what makes non-Hermitian systems better sensors? Well, if you have a Hamiltonian and you perturb it by parameter theta, then you can write a simple expansion. If it is Hermitian, you can write the expansion for these frequencies. But if it's a non-Hermitian Hamiltonian bearing an exceptional point of order n, you have to use something called the Newton-Poisson expansion. And for small theta, if you now restrict to the first terms in theta in 3 and 4, you conclude that theta to the power 1 over n dominates in comparison to the theta. That tells you that non-Hermitian systems respond drastically to the external perturbations in comparison to the Hermitian counterparts. So that makes them better. This one way of looking at this, sensing schemes in non-Hermitian system. Now I'll discuss the results of these three papers, which consider almost identical systems, two cavities, one bearing loss, the other having some gain, and they are coupled by some coupling strength. The first paper published in Nature Communication by Ashcroft's group, they came up with the conclusion that you can have enhanced signal output. Remember how these sensors work is that you probe these sensors by some input field and then let this field interact with your system and then measure the output field. So they came up with the conclusion that you can have enhanced output signal without being in the vicinity of exceptional point. And they also came up with the notion of non-reciprocity as a powerful resource in sensing. Non-reciprocity in this context means that this coupling is now direction dependent. In the second paper published in PRL by Manxing Zhang et al. From Liang group, they came up with the notion that if you have these two systems and bearing two modes, and you perturb these two modes in frequency by this perturbation parameter theta naught, then you can have quadratic scaling. And by scaling, I mean this uncertainty is varying quadratically with this parameter that you are estimating, provided you are at the exceptional point. The system has to be maintained at the exceptional point to have this according to their results. In this third paper published in New Journal Physics by Chen et al., they reported that you have this enhanced output signals, but not because of the exceptional point, but due to the fact that the Hamiltonian at this point becomes singular. So singularity of Hamiltonian is kind of doing the whole magic according to this paper. Now, here is our work in a nutshell. We consider the scenario where you have, apart from these frequency perturbations, one more perturbation parameter that is perturbing your coupling strength. So that would be the general scenario to consider. And what we see is that you have, when we compute the classical and quantum Cramér bounds corresponding to these quantities, we see that you have no scaling in the sense the uncertainties are independent of these parameters. If you don't have a singularity in your Hamiltonian, even if you operate at the exceptional point. So singularity seems to be crucial to have some scaling in such systems. Further, the quadratic scaling that was predicted in the single parameter setting that I showed you in the previous slide turns out to be very fragile in the sense that it really depends on how you choose this coupling strength parameter. Whether you choose it in a way that you maintain the singularity condition in this two parameter scenario, or you choose it in a way that you go away from this singularity condition. And I will show you that the conclusions are entirely different. And so in single parameter setting, it turns out that the scaling is primarily determined by the order of pole of the response function that I will introduce in next slide. However, in multi-parameter case, what we find is that it becomes really important to take into account the statistical dependence of these more than two parameters that you want to estimate, two or more than two parameters. Sorry. So here is the sensor model that we consider. It involves two cavities, as I showed you earlier, but this time in some little detail. You have mode A1 corresponding to frequency omega-1 and A2 with omega-2, and then these cavities are coupled to baths with operators B1 and B2, and then you probe these cavities via these probe channels characterized by operators A1 and A2. You can decompose these operators using input-output formalism. That kind of gives you a pictorial representation of what is happening. But a couple of important things to note. One is that when you solve for these time evolution of these A1 and A2 operators, what you get is that the dynamics is essentially governed by this Hamiltonian edge, and it is non-Hermitian. You can see the diagonal elements have complex entries. Second is that one is interested in sensing the system in a way that you send some input signal in these probe channels, and then you look at the output signal. And what we consider and is favored by experimentalists is that you use Gaussian input fields. And since the interaction we consider is really linear, the output fields are guaranteed to be Gaussian. And once you have Gaussian output fields, the only two things that you need to know is the amplitude and covariance matrix corresponding to these output fields. And when you solve for those, you obtain equations 5 and 6. And note that these output fields are completely determined by this function g that we call response function. And this g in turn is given by equation 7, which depends on this matrix M, which is nothing but the Hamiltonian written in the quadrature basis. So any uncertain parameter that is embedded in this Hamiltonian is reflected in this response function g, and hence in the output amplitude and covariance matrix. Sorry. Okay, so here I rewrite this Hamiltonian with now with these quantities gamma 1 and gamma 2 that play the role of loss and gain rates. And you see that it turns out that the exceptional point occurs for 2g equal to gamma 1 plus gamma 2, and this Hamiltonian is singular for all values of omega naught satisfying equation 10. In particular, note that if one is at exceptional point and also assume that gamma 1 is equal to gamma 2, then this Hamiltonian is singular for omega naught equal to 0. Now, how can you perturb this Hamiltonian? Well, you have two choices in single parameter setting. You can either perturb the frequency, you can by adding this theta naught parameter with identity, or you can perturb the coupling strength by adding theta 1 with sigma x to this Hamiltonian. Note that if you perturb this coupling strength, you are disturbing the exceptional point condition. And with this choice of parameters that I know that I give here in this box, that would imply disturbing the singularity condition of this Hamiltonian. So in multi-parameter case, then you can talk about having a Hamiltonian which is perturbed in a non-singular manner in the sense that you disturb the singularity condition, or it is perturbed by preserving the singularity condition of this Hamiltonian. So that's what I meant when I showed this picture, is that when you are estimating theta naught, it really depends on how you choose theta 1, whether you choose it by preserving singularity or you choose it by not preserving singularity. Accordingly, the response function that I introduced in the previous slide picks up these factors theta naught and theta 1, and then you can do the metrological things with this. So now, having these output amplitudes and covariance matrices as a function of these unknown parameters theta naught and theta 1, you can do the Gaussian quantum metrology. Well, you can choose an estimator and compute the covariance matrix, but then there is this fundamental lower bound given by quantum Fisher information matrix that you cannot beat. So what we do is we compute this quantum Cramér bound using the Fisher information as defined in equation 19 with this approximate expression by plugging in the output amplitudes and covariance matrix that I showed you in the previous slide. So here are the results. So I plot here quantum and classical Cramér bounds. I did not talk about classical Cramér bound, but one can actually show that it corresponds, it is actually the heterodyne measurement scheme that actually becomes relevant here and shows the same scaling as the quantum Cramér bound. And one can see that in the left plot, if you choose the parameter theta 1 in a way that you do not maintain the exceptional point condition or singularity condition, which are equivalent with the choice of parameters that I showed you in the previous slide, then it turns out that you at once lose the scaling. Now these plots are log plots, and they plot straight lines for any power functions. So this straight line, for example, here corresponds to theta naught square, and this corresponds to the case when it is independent of theta naught. So you at once see that when you choose a non-zero value of theta 1, which corresponds to these black lines, you immediately lose scaling. This Cramér bound becomes independent of the parameter. This uncertainty becomes independent of the parameter that you are estimating. However, if you engineer your system in a way that you maintain the EP condition and which is equivalent to the singularity condition in this case, then you can have a linear scaling, which is not surely as good as quadratic one, but you still have some scaling even for any non-zero value of this parameter θ1. So the conclusion is that this wonderful quadratic result that was predicted in the single parameter setting is quite fragile in the sense that it really depends on how you choose the parameter that is perturbing your coupling strength. So this is all numerics, but we have shown these results analytically, and it turns out that the destruction of this quadratic scaling actually comes from the fact that your quantum Fisher information is non-diagonal, and the diagonal elements actually tell you the statistical dependence of these parameters that you are estimating. So with this, I thank you for your attention.
Thank you, Javid. Questions, comments? So in this, when you first showed the perturbation part, so you had this, there was a θ naught I term. So that identity, that I is identity?
That I is identity. So you are just perturbing the frequency parts, which are real terms in this Hamiltonian.
So, I mean, the evolution operator, is it still an exponential IH?
Yeah, the total evolution is governed by this equation here, which apart from this part actually contains the contribution from these channels that you are probing it and also from the baths.
I see.
So yes,
so the evolution when you put the perturbation, the identity doesn't just come out in. Because I mean, I want to understand why is an identity term how can an identity term can be considered as a perturbation?
I think it should be looked as the uncertainty in the frequencies of the two modes, which I have taken equal in this case.
So this θ naught is a constant or is it disordered?
Θ naught is, I mean, you can keep it as a variable in this whole picture and then look at the scaling for different values. Yeah.
Nice. Okay. Thank you. Any other question? Well, if not, we thank Javid and all the other speakers of this session.
Thank you.
Thank you, everybody. And so the organizers, yeah, Devashista, if you have
for a long session.
Yeah, thank you.
Thank you.
Nice.
Okay.
Thank you.
Okay. So today's session is closed now. We will meet again at 11 a.m. tomorrow morning. Okay. Thank you all.
কি বলছো?